Yes, but you can actually run computers using renewables, and you can't do that with air travel. So that's a pretty big difference.
Right, but the renewable part is doubling or quadrupling the cost of the energy that we can afford. That's the problem.
Well, we can afford it without, I mean, if we want to save the climate, we can definitely afford it.
Oster Luan.
Yeah.
We're collecting a quorum, I think. We're almost at 9:30. Right, I think we're at 9:30. Let me just welcome everybody back. Just a reminder again for those who haven't sent Elizabeth their slide decks yet, please do that. You know, it'd be best if we had them before the talk in case there's some issue with presentation. We'll have a backup. But if that doesn't happen, please do send them after you've finished your talk so we can get them. We'll link them after the meeting. The meeting webpage stays up, and we link the slide decks and the YouTube video recording to the talk on the agenda so people can go back and review talks or catch talks they missed. All right, I think that was it from me. We have 6 talks this morning and then 6 more in the afternoon. And so we're over the hump. And Laura is going to run the show this morning.
Great, thank you very much, Frank. And good morning, everyone, or afternoon or evening, depending on where you are. So I'm Laura, so I'll be moderating the session this morning. So I want to thank again all the speakers and participants for joining us. It's been a phenomenal meeting so far. So I'm very excited for the 6 talks that we're going to cover this morning. And again, also thanks to everyone involved in the organization. It's been very smooth and very nice. Right, so for this morning, all talks are, we have a slot of 25 minutes. So it's 25-minute talk and 5 minutes question. So at the 20-minute mark, I'll, unmute myself if you're still talking to kind of, tell you what's going on. And for people who want to ask questions, if you can, if it's possible, if you're using the app, use the raised hand button in the app. And if you can't, then you can unmute yourself. Great, so our first speaker is going to be Elizabeth Jankowski, who's going to talk about effects of Eddy representation on vertical structure and energetics. So you should be able to share your screen, hopefully.
Yeah. Can everybody see my screen?
Yeah, it's perfect.
Okay, great. Thank you for the introduction, Laura, and good morning or afternoon, evening to everybody. So as we've been seeing in many of the talks so far, the representation of energetic transfers associated with mesoscale eddies is a major challenge in the development of ocean models. And so my talk will be specifically focused on looking at the effects of eddy representation on vertical structure and energetics. And this is a project that I'm working on with Laura Zana and Schaefer Smith as part of the Ocean Transport and Eddy Energy CPT. And all of the experimental results that I'll be presenting today are based on this idealized configuration within MOM6 that Alistair gave a great introductory talk to yesterday, which was Never World 2. And just as a reminder, I'm putting up 2 aspects of the simulation on this slide. So this shows the ocean depth. You can see that we have a topographic kind of ridge in the center of the domain and a channel at the bottom. And that corresponds to the ACC. And then the zonal wind stress is shown on the right. Okay, so as an outline of what I'll be discussing today. So again, we're considering an idealized 1-basin setup within MOM6. And the advantage is that we have these 4 different resolutions ranging from 1/4 degree to 32nd degree. And this allows us to compare the momentum, buoyancy, and energetic properties of the flow in a very systematic way, because all that we're varying across these different experiments is just the resolution. So some of the specific questions that we will address here. First, how do the Neverworld-2 experiments compare in resolving eddies? So both amongst each other, so how do we resolve eddies differently based on the model resolution, but also how does this compare to a state-of-the-art GCM, just to motivate the fact that in this idealized framework, we're resolving eddies in a similar way to what we may actually encounter in a GCM. And then the second question is, how does the zonally averaged isopycnal structure vary depending on how well we resolve eddies and just on the model resolution itself? Also, to what extent does eddy resolution affect properties of the kinetic energy? So we will think about decomposing the kinetic energy into barotropic and baroclinic components, and also its partitioning into eddy and mean. And then I'll briefly discuss the next steps, which are considering APE and energy budgets. Okay, to begin, we will look at the eddy resolution and how this compares to a state-of-the-art GCM. So as a metric for considering eddy resolution, I'm using this ratio of deformation radius. So this is just the first baroclinic Rossby deformation radius to the grid spacing in the horizontal. And so here I'm plotting this RD over DX for the quarter degree Neverworld-2 and for the quarter degree OM4, which also uses MOM6. So here, higher values of this ratio correspond to increased eddy resolution, because you can imagine that if we have a smaller DX value or a larger deformation radius, we would be resolving some of the length scales that are setting the eddy dynamics better. Here I'm considering this ratio of RD DX to be 2 as a rough cutoff between eddy resolving and not resolving. And what you can see here is that Neverworld-2 is broadly consistent with the more realistic OM4 and how this ratio looks like. So kind of to first order, we're resolving eddies in a similar way, although it does look like in some regions of Neverworld-2, this ratio is slightly higher. So maybe we're actually performing a little bit better than a more realistic model. So this helps motivate the use of this idealized kind of configuration, and in that it represents eddies in a comparable manner to a GCM. And I'd also like to mention that this is a somewhat conservative estimate, this use of this ratio. We also performed some QG linear stability analysis, which shows that the fastest growing modes are actually 2 to 4 times smaller than the deformation radius. So this actually kind of helps motivate the fact that in a current state-of-the-art model, most of our domain is not really resolving eddies, especially if we consider the fact that we actually need even higher resolution to capture some of the relevant energetic transfers associated with eddies. Okay, so just to compare this ratio across the different Neverworld-2 experiments that we're considering. So here I'm showing all of the resolutions ranging from quarter degree to 32nd degree. And you can see that in both the quarter and 1/8 degree, there are significant portions of the domain that do not capture the deformation radius adequately. Whereas for the 16th and 32nd degree simulations, most of the domain is at least capturing the deformation radius and maybe some multiples of it as well. And looking at a few other properties of these simulations, we found that the 16th and 32nd degree results actually converge on few important properties of the flow. And so we consider these to be the truth cases when we're evaluating some of our diagnostics. To give you a basic introduction into what some of the properties of the flow are, here I'm showing the 500-day zonal averages of the isopycnal surfaces ranging from quarter degree to 16th degree. And the top bar shows the wind stress at that location. What you can see broadly is that as we move into higher resolutions, the isopycnal structure becomes a little bit flatter, especially in these mid-latitude gyres and also in deeper parts of the ocean. And that's potentially because the available potential energy is lower and we're resolving eddies better. If we also look at just an example of a transect, this is showing the V velocity transect as a 500-day average in the ACC. You can also see that there is a great deal of standing meanders, and we can also see that the flow remains relatively strong even near the bottom, and this becomes important later in the talk. So this is also kind of emphasizing the fact that we may be seeing barotropization, which means that we see stronger velocities at depth with increasing resolution. Okay, so moving into some of the energetic properties of the flow, The first metric that I'm showing here is the total kinetic energy, shown as a zonal 500-day average across all of these resolutions. And here I'm plotting kinetic energy as in units of meters squared per second, and kind of normalized or weighted by the density and the size of the column. So here, the lowest resolution is 1/4 degree, and it's obviously has the lowest kinetic energy, which is something that we expect. And then as we move into the higher resolutions, they have higher kinetic energy, also as we expect. And we can see here also that the 16th and 32nd degree simulations look relatively similar, particularly in the ACC, although in some of the northern parts of the domain, they start to diverge a little bit. On the right, I'm showing plan view plots of the total kinetic energy, also as 500-day time averages, and this is on a log scale. And you can again see how the kinetic energy increases as we move into the higher resolutions. And the increase is particularly apparent in the northern part of the domain, especially kind of between 40 and 60 degrees, because that's also where the mean flow tends to be the weakest. And in the region where the mean flow is higher, in the ACC, the increase in kinetic energy is maybe a little bit less pronounced. So now we'll talk a little bit about trying to constrain the vertical structure of the energy in more detail. So we've seen that the kinetic energy broadly increases as we increase resolution, but now we'll try to apply a more sophisticated analysis. So this is quasi-geostrophic modal decomposition, which I've been working on with Jake Steinberg. And thank you to Jake for also providing the code to do this decomposition. So the idea here is that we are taking the quasi-geostrophic equations and we apply certain boundary conditions. So here we assume that we have a flat bottom. So near the bottom, the vertical velocity is 0 and also a free surface. And at every point in the domain, we compute the quasi-geostrophic velocity modes based on the stratification at that location and also the layer positions at each point. And so here I'm showing a sample of what this looks like at one location. So the first, or actually the 0th mode is the barotropic mode, and it's shown in purple. You can see that it has no 0 crossings, and this is the velocity mode that is constant with depth. Then the first mode is shown in blue. You can see that it has 1 0 crossing, and so on. So every progressively higher mode has more 0 crossings. And the idea is that we can represent the flow at each location as a superposition of these quasi-geostrophic modes. So after we compute the velocity modes at each location, we can reconstruct the flow as a sum of these QG modes of varying amplitudes at a given location. And this is an example of doing this at this location, kind of in the southern part of the domain within the ACC. The other interesting aspect to this analysis is that we can use different numbers of modes. So here I'm showing the U and the V velocity. So the U velocity is in blue. The raw model velocity is shown as a solid line, and the reconstructed velocity using these QG modes is shown as a dotted line. And likewise for V, which is shown in green. So you can see that even just using 2 total modes, so just the barotropic mode and the first baroclinic mode, we can reconstruct the velocity quite well. And by the time that we use 8 modes, it's basically a perfect fit here. Another example, this is a little bit farther to the north. So here with 2 modes, the match between the reconstructed and the raw velocity isn't as good. So we really need significantly more modes to capture the flow relatively well. So this is an analysis that we've done throughout the whole domain. And after doing this, we can then solve for the kinetic energy corresponding to each mode using the velocity amplitudes. So when we do this decomposition, we get basically a velocity amplitude corresponding to each mode at each point. And then we can just square this to get units of meters squared per second squared kinetic energy. We can then consider time averaged structure or time series of these baroclinic and barotropic components. Again, this allows us to also decompose into the barotropic 0th mode and then the baroclinic modes, which are the sum of the 1st to nth modes. And this is what I'll show on the next plot. So there's a lot of information here, but basically what I'm kind of looking at is this one location within the southern mid-latitude gyre. And I'm considering all of the available resolutions ranging from 1/4 degree to 32nd degree. And in each of these kind of pairs of plots. The top plot shows the modal decomposition averaged in time. So this shows the mode number ranging from the 0th mode, which is the barotropic mode, all the way to the highest baroclinic modes, which here is 12. And on the y-axis is the kinetic energy corresponding to that mode. On the lower panel, I'm showing kinetic energy for the barotropic modes and baroclinic modes. So barotropic are shown in blue, baroclinic are shown in red as a time series. So basically the top plot is just a time average of the bottom plot and showing all of the modes. So what you can see here, if we look at the quarter degree simulation, is that we see roughly equal partitioning between the 0th and the first mode. And that kind of indicates that the flow has relatively strong contribution that is coming from the first baroclinic mode. But likewise with the barotropic, if we look at the time series, we see that there's a lot of fluctuation in time across all the resolutions. And again, we see here that the barotropic and baroclinic kinetic energies are roughly comparable in magnitude. When we then move to the 8th degree, so here the deformation radius ratio to the grid spacing is 2. So we're still kind of in the gray zone or starting to resolve eddies a little bit better. We now see that, first of all, the kinetic energy has increased substantially. All of the y-axes here are the same. So you can really kind of compare across these resolutions easily. We see that now the flow is dominated by the barotropic component, and it's significantly higher than that in the quarter degree model. We also see these very strong fluctuations in time with some very strong peaks in the barotropic kinetic energy. As we look at the 16th degree and the 32nd degree, overall, the structure remains relatively similar. So we see that the dominant mode is the barotropic mode. We see a lot of fluctuation in time. And the main kind of point to take away from this is that as we moved from the quarter degree to the 8th degree, that's where we really saw a very large effect on the structure. So now this is another region in the domain. This is in the northwestern part. And here I think this barotropization signature is even stronger. So here we have relatively weak mean flow and a strong eddy signature. Also, if you recall in the plan view kinetic energy plots, that's where we saw a very strong increase in kinetic energy as a function of resolution. We also see that at this location, as we move from quarter degree to 32nd degree, our ratio of this deformation radius to grid spacing increases substantially. So now if we look at the modal decomposition, here I'd like to point out that the y-axis is smaller in this quarter degree simulation, and then for all of these, it's the same. So here we see that the kinetic energy is distributed quite substantially across a variety of modes, including having relatively strong peaks in some very high mode numbers. But definitely the first baroclinic mode is the dominant one. If we look at the time series, we see primarily just the baroclinic kinetic energy signature. The barotropic component is relatively weak. As we move to the 8th degree, we see that the flow is becoming increasingly barotropic and the kinetic energy increases. And then as, again, we move to the higher resolutions, this trend continues. So we see very strong barotropization and overall increase in kinetic energy. So we're hypothesizing that the reason that we see this big discrepancy between the quarter degree and the higher degree resolution models is that at low resolutions, we have energy that is trapped in the higher baroclinic modes. And because of the fact that we're not properly resolving eddies and some of the length scales associated with the eddies, we're not able to propagate this energy into the first baroclinic mode and then into the barotropic 0th mode. Just to show another region, this is in the ACC. And just to kind of emphasize the fact that this trend really is kind of dependent upon the dynamics. This is showing the same plots. Here we see that this ratio of RD to DX actually doesn't change as substantially at this location. There's also significant mean flow here in the form of the ACC. And this contributes to the fact that barotropization and kinetic energy do not increase as much in this simulation in this location compared to the other places that we looked at. So you can see that there is still some barotropization between the quarter degree and the higher degree resolutions, but it's not as significant as we saw in the previous slide. So this is a zonally averaged picture of what we just looked at. We saw that there's a great deal of variability between specific regions, but if we just look at the zonally averaged barotropic baroclinic energy decomposition, we can kind of see a more global view of this. So this is showing the 1/4 degree, 1/8 degree, and 16th degree results. And what I'm showing here is the kinetic energy fraction that goes into the barotropic mode. So that's shown in yellow, and the fraction that goes into the baroclinic first mode, which is shown in blue, and all of the baroclinic modes are shown in the dashed gray line. So what you can see in the 1/4 degree results, consistent with what I showed in the previous slides, is that the dominant fraction of the kinetic energy is going into baroclinic modes at 1/4 degree. However, as we move into higher degree resolutions, we see that the flow is becoming increasingly barotropic. So this yellow line is really starting to dominate throughout most of the domain. You can kind of disregard the regions near the equator because some of these dynamics break down there. But really, in the northern part of the domain, the flow is now dominantly barotropic, and also in the southern part of the domain. So as eddies are resolved, more momentum is being transferred downwards, leading to barotropization and this stronger barotropic component, and creating a more uniform flow with depth. So the next thing that we looked at was eddy mean barotropic baroclinic decomposition. So what I showed on the previous slide was just decomposing the flow into barotropic and baroclinic components. But now we're also defining a temporally defined mean and eddy component. So the mean is just a 500-day average, and the eddy is just a deviation from that. So just to help you visualize what's going on here, here I'm showing the barotropic mean velocity, which is in the dashed dotted line, and the mean baroclinic velocity, which is in the dashed dotted blue line. And then the eddy components are the parts that are fluctuating about that. So those are just the dotted lines. And so that's kind of what the breakdown is in these two plots. So here I'm just looking at 1/4 degree and 16th degree. The main trend that you can see here is that in the 1/4 degree, things look relatively messy, but there's also some partitioning kind of equally between the mean and eddy components. But as we go to the 16th degree, we see that the barotropic signature starts to dominate, as I showed before, but also it's really the barotropic eddy component, which is the dominant source of this kinetic energy increase. So that's kind of the summary here, is that the flow becomes dominated specifically by the barotropic eddy component, which is again, this part that's fluctuating in time, but constant in depth. Okay, so just to go over the contributions and next objectives of this work. So as we've seen, the dominant trend in the vertical structure, as eddy representation increases, increasing kinetic energy goes into the barotropic mode, particularly the barotropic eddy component. We are attributing this to the inaccurate representation of baroclinic energy transfers in the low resolution models, which is leading to buildup of baroclinic energy and lack of barotropization. And this is particularly apparent in regions that have kind of a strong increase in the ratio of RD to DX as we move across resolutions. So as the eddy resolution becomes significantly altered, then we really see the barotropization happening more strongly. And also in regions where there is a bit less of the mean flow signature, that allows us to also see this signature more clearly. The next steps are to consider the available potential energy, which we've already started to do. We know that it's broadly decreasing as a function of resolution, but we'd like to constrain this a little bit better and also look at energy transfers between kinetic energy and potential energy reservoirs. And the end goal of this is to apply these insights to developing scale-aware and energetically consistent mesoscale eddy parameterizations. So thank you for listening, and I'm happy to answer any questions on this.
Great, thank you very much, Elizabeth, and spot on the 20 minutes. So we have a few minutes for questions. So Takaya was first. So Takaya, if you want to unmute yourself.
Yeah, thanks for the very interesting talk. Can you go back 2 slides?
This one or?
Right, yeah, so I was just kind of trying to like connect this with what Hailu Kong presented like 2 days ago.
Yeah.
And the fact that the quarter degree model does relatively well in the Southern Ocean. Do you think that has to do with standing eddies due to the topographic ridge you have there?
Yeah, so by doing well, do you mean that the barotropic signature is relatively high here?
Right, yeah.
Yeah, I think it's partially due to the standing meanders and also partially because there's a very strong ACC in this region, and that has like a relatively barotropic signature as well. I mean, it has relatively strong velocities near the bottom. And so I think that's partially what's setting the fact that the barotropic energy is quite high here. But yeah, it's a little bit unclear because there's a lot of complicated dynamics in the ACC, both due to standing meanders, the mean flow, and potentially eddies being resolved or unresolved. As we saw, that's also the region where the RDDX values are the lowest. So it's actually questionable whether or not it's really resolving the eddies properly. It's just, it does have a barotropic signature.
Okay, yeah, thanks.
Thanks. Yeah, okay, so we have a couple more questions. So next is Steve.
Yeah, great talk, Elizabeth. This slide in particular, I think you discounted the tropics. You said that's different dynamics, and I agree there are different things going on there, but it does seem robust signal that you have higher baroclinic modes in the tropics, and I've, that's not a new result. I'm just wondering, I mean, there's just sort of, you don't need to discount everything there. I mean, there's some relevance to what you're showing here, right?
Mm-hmm. Yeah, no, I'm not discounting the results there. I'm just, I guess, saying that the eddies have a different structure and different dynamics there. So we don't necessarily expect to see the same barotropization signal. But yeah, I think it's definitely a robust signature that we're seeing higher baroclinic energy there.
Yeah, I mean, I think one of the important features of this model is that it has an equatorial region, and we need to, take care of, to think about that as well. Anyway, it's great. I really enjoyed it.
Thank you.
Thanks. Next up, we have Xiaoning.
Hi, Elizabeth. Thanks for the talk. I mostly just wanted to compliment you on the animation. It's really great. It's really helpful. And I also have
actually, that was Laura's idea. So it's really confusing. There's a lot of things going on here, and it's definitely good to have.
Right, and it's great to have. And another technical question that's kind of related to what Stephen was saying about the tropics. Is this idealized model like relatively easy to reconfigure to focus maybe on some other areas of interest? That this is maybe mostly with due to like software engineering other than the science question, but I was just wondering.
Yeah, so right now this is relatively idealized in the sense that, I mean, it has kind of, it's extending from -70 to +70, and it could really correspond to numerous regions in the world ocean. I guess the main reason it was developed with this type of topography was probably to correspond to the Atlantic, but it is relatively idealized, and I think it's pretty simple to change various parameters in the model, such as the topography or the wind stress. And maybe that's something that we will do in the future. But also it's nice to just have kind of one test case that we can really compare across many resolutions and not change too much. Yeah.
Thanks so much.
Thank you.
Yeah, thanks a lot. So I can see there are still actually 3 questions, but we're a little bit over time. Can we try to maybe take them quickly? So I think there's Frank, Dhruv, and Kailu, and we can try to do it quickly so we don't run over time.
Okay.
So Dhruv, so let's do Frank, Dhruv, and then I'll read the one in the chat.
Okay. Quickly, I guess I was wondering if you've considered investigating the role of the vertical resolution and the positioning of the layers relative to the modal structure and how that might affect the efficiency of the barotropization.
So yeah, the positions of, that's a good question. I didn't consider it too much yet, other than the fact that the positions of the isopiconals vary significantly across latitudes. And so I've kind of been doing that a little bit indirectly just by looking at various regions. But there are 15 isopiconal layers in this model. And I think it may be interesting to see also just if we change the amount of layers, if the dynamics change. But that's a really good point. Thank you.
Yeah. All right. Dhruv, can you try to do it quickly?
Yeah, I just have a quick question. This is a great talk. This is related to some work that Joel Lacaze has done over the last few years about the role of bottom slopes. And I was wondering if you have considered that impact in your results. Like, does the barotropic mode decrease as you have more slope?
Yeah, so that's a really good question as well, and something that I and Jake also have thought a bit about, and Hussam Yassin will be giving a talk kind of related to that question as well later. So I think the short answer is that we have significant horizontal velocities near the bottom, and so that kind of limits the choice of boundary conditions. So if we start to consider the effects of slope, one other option is to assume that we have zero horizontal flow near the bottom, but that isn't really consistent with the picture that we're seeing. So I think the model that we're using is a little bit more accurate here, and it seems to represent the flow really well. So something that we should think more about, though.
So there's one more in the chat, but I'd like to actually type it up, Elizabeth, so we're already kind of running 3 minutes over. So thank you very much. And so next up, Nora, you should be able to share, right? Perfect.
Yeah. You can hear me and see my screen? Perfect.
Yeah, perfect.
Yeah. Okay. So hi, everyone. Like Elizabeth, I'm a postdoc in the Ocean Eddy CPT. And today I'd like to share some ongoing work on diagnosing the energy budget of mesoscale eddies in our Neverworld 2 simulation. And before I start, I want to give a really big shout out to my collaborators, Ian Grooms, Scott Backman, and Malte Janssen. They've all made large contributions to what I'm showing today. So most global ocean models do not fully resolve mesoscale eddies, as you can guess from this left figure here. So we need accurate parameterizations to represent subgrid scale variability. And here on the right, I'm showing a schematic of the energy cycle, which shows exchanges between different energy reservoirs, potential energy, kinetic energy, and resolved and unresolved by a model. And these exchanges, these energy exchanges with the unresolved scales are pretty important for accurately capturing ocean transports and currents in models. So over the last 5 to 10 years or so, several studies have suggested new ways to improve mesoscale eddy parameterizations by including some of these missing pathways. So here I'm just showing one example, a schematic of the Miki parameterization that was developed by Malte Janssen and colleagues. So this parameterization formulates a prognostic equation for subgrid scale kinetic energy, and the ingredients into this prognostic equations into this equation are parameterizations of these different energy pathways that I'm showing by these colored arrows here. So goal of the CPT is to evaluate and maybe improve some of these new energy budget-based parameterizations. But in order to do so, we first have to understand this energy cycle and these exchanges between different energy reservoirs better. And this is what this talk is about. So we are diagnosing the energy budget of mesoscale eddies in our stacked shallow water model Neverworld 2. And I'll do this using a spatial filtering approach rather than a time or zonal average. And we're actually exploring this in a thickness weighted average framework, because we think that this might be a promising and maybe the most sensible approach, but I'll get back to this later. So Alistair gave a detailed overview of Neverworld 2 yesterday, but here's a quick reminder. Neverworld 2 is a MOM6 simulation in stacked shallow water mode with 15 stacked layers of constant density. Neverworld 2 has an ACC-like channel, a mid-Atlantic ridge, and extends over both hemispheres. And we have, as we've just seen from Elizabeth, we have Neverworld 2 simulation at different horizontal resolutions available, up to a 32nd, but in this talk, I'm using the 1/16th resolution run as my truth, basically. And yeah, we just heard that this resolution resolves mesoscale eddies in most of the domain. So here I'm showing a snapshot of kinetic energy vertically integrated in the 1/16th resolution run. And here you see that a lot of, this ACC region is very energetic, and here also the western boundary region. Okay, so on this slide, I'll explain how we do the spatial filtering. So in this example, I'm using a Gaussian filter, which filters the output, the model output from the 16th resolution run to a degree, 1 degree. And the field that I'm filtering here is layer thickness, in this case of the second layer from the top. And you see that this layer outcrops along the gyre boundaries. And you also see a lot of small scale structure, which gets smoothed out if you apply the filter. So we constructed our filters in such a way that they preserve the area integral. So the area integral of the unfiltered field is equal to the area integral of the filtered field if you integrate over the full domain. And preserving the area integral of thickness is equivalent to conserving the volume of our fluid. So that's a good property. And because of this property, I'll hereafter refer to this filter, to the spatial filter, as the area filter. And I denote the spatial, well, I'll denote the filtered field by an overbar and the superscript A. There's a second type of filter that I'm using in this talk, and it is the spatial and thickness weighted filter, which we apply to velocity fields. And this filter works as follows. We multiply the velocity by thickness, and then we filter the whole thing by the area weighted by the area filter, as over here, and then you divide the result by the area filtered thickness. So this is exactly what has in the literature been referred to as thickness weighted averaging. And Takaya talked about this yesterday too, with the difference that he used an ensemble average to define this bar operation, and we're using a spatial filter. So just to note, this filter is constructed in such a way that it preserves the volume integral. So the volume integral of unfiltered velocity is equal to the volume integral of the filtered velocity. And this is equivalent to conserving momentum in the model. And here you see an example of this filter in action. On the left, I'm showing zonal velocity unfiltered with a lot of sharp structure in the ACC here. And on the right is the volume filtered. I'm saying volume filtered because of this volume integral preserving filter property from now on, and with a superscript V here. So this is the volume filtered velocity field. And yeah, again, you see like a lot of the sharp structure in the ACC getting smoothed. So now that we have our filter operations, we can define and diagnose eddy kinetic energy in our Neverworld-2 model. So here's the definition of EKE. So we filter kinetic energy with our area filter, and then MKE is defined as this, and we filter the velocities with the volume filter.
What's that?
And then, so here I'm showing this decomposition. So here I'm using a filter that is that's filtering the 16th degree resolution to a half a degree. And here's the filtered kinetic energy. Here's the mean kinetic energy, and the eddy kinetic energy is the difference between those two. And you see, yeah, most of the kinetic energy is yeah, here in the ACC region and along the western boundary. So on this slide, I'm deriving an evolution equation for EKE. So here I'm just writing down the continuity and velocity equation in our stacked shallow water model. And for simplicity, I'm collecting all the friction and forcing terms and denote them by F. So to get a kinetic energy equation, you just take the dot of HU with the velocity equation, you multiply the continuity equation by U squared over 2, and you add the two. So this gives you your kinetic energy equation. In order to get an evolution equation for MKE, we have to look at the thickness weighted averaged equations. So I'm showing them here. The colored terms, the highlighted terms are the eddy terms. Just to note, the prime and the double prime quantities here, or the prime and the double prime terms, they have in reality more complicated expression, but in order to save space here, I'm using kind of a Reynolds average type notation. you can think of them roughly as the prime quantities are deviations from the area filter, and the double prime quantities are deviations from the volume filter. So the orange terms here are really the characteristic features of the thickness weighted average framework. In the non-thickness weighted average framework, you would get an Eddy term in the continuity equation, which we normally parameterize with GM, right? But in the thickness weighted average framework, there's no Eddy term here in the continuity equation. Instead, it moves down here to the velocity equation. You get this extra Eddy form stress. So now, to get an evolution equation for MKE, we basically do a similar operation as for kinetic energy, but using the thickness weighted continuity and velocity equations. So this is our MKE equation that we get. It inherits the Eddy terms from the TWA velocity equation. So now, in order to get an EKE budget, you filter this KE equation and you subtract this MKE equation. And I'm showing this result on the next slide. So this is the rather long and complicated expression for the EKE budget you get. So now the question is, what do all these terms mean? What are their characteristics, right? Where do they live on this diagram? Are they conversion terms between different energy reservoirs, or are they non-local transport terms? These are all questions that you have to answer if you want to parameterize these terms or evaluate parameterizations. So to not overwhelm us too much, I'll focus on part of the EKE budget in this talk. I'll look at the part here that contains all the contributions from the pressure gradient. So here on the right, I diagnose this yellow term in the Neverworld 2 simulation using a filter operation, filtering from a 16th degree to a half a degree. And this is also vertically integrated. So from now on, I will look at a 2D energy budget. So basically summing over all the layers, summing this equation over all the layers. So you see that most of the action is happening down here in the southern region. On the next slide, I'll zoom into this region and we'll try to understand this figure a little bit better. So here, the left upper panel, A, is exactly the term that I showed on the last slide, that yellow term. The panels B, C, and D are a decomposition of term A, which will hopefully help us to understand term A a little bit better. So term B turns out to be an EPE to EKE conversion term. It's pretty small in amplitude. It is actually exactly equal to if you write down the budget for EPE, it's actually exactly equal to the EPE tendency, but all changes in eddy potential energy get directly funneled into EKE, but it's pretty small. This second term, we label as an EKE transport, a non-local EKE transport, rather than a conversion between two energy reservoirs. You see that this term is the divergence of a flux. So I used the chain rule here to do this decomposition. And it seems that this term captures a lot of the features of this term A of interest. So yeah, including these dipole, these swirly dipole patterns throughout ACC. And then finally, term D is an MKE to EKE conversion term, the term that is associated with the eddy form stress in the velocity equation that we got from the thickness weighted average framework. And well, two notes. First, this is sign indefinite, right? So we can't think of this term as a EKE source term. And then maybe the second note is it almost seems like this term has some of the structure of C over here, but maybe values are of opposite sign and maybe smaller amplitude. Well, let's have a look at the evolution of these terms, the time evolution. So maybe let's focus on the two panels down here. I only plotted this yesterday, so I'm still trying to figure out what's going on. But maybe 2 notes. So first, there seem to be some standing features here, right? So where the top topography is steep, and that's totally possible because I've only used a spatial filter and not a temporal filter. And then the second note is the comment I've already made. There seems to be some sort of cancellation going on between those two terms. So it might be that this is not that there's still kind of a transport term in here, which we might want to separate out. So I think, yeah, more work has to be done. Here I'm showing a time mean of all these four terms. So I'm averaging over the 100 movie frames that I've just shown you. So again, maybe more work has to be done, but I just want to make the general comment that having such a decomposition is useful for developing parameterizations, in the sense that, for example, this EKE transport term C, we could try to parameterize by an advection diffusion process in eddy kinetic energy. And then we've also figured out that this term B is pretty small, so we could probably neglect it in a parameterization. So before wrapping up, let's just have a look at the bigger picture here. In the previous slide, I've identified and diagnosed several conversions between different energy reservoirs, including this pretty small conversion between EPE and EKE, and then this conversion term between mean kinetic energy and eddy kinetic energy. So if I fill in the budget terms, the conversions from the budget terms that I haven't shown today, this is roughly the picture that you get. There's no conversion up here in the potential energy budget. This one was pretty small too, so we can neglect this. So all the energy transfer is happening down here in the kinetic energy budget. The picture is pretty different if you look at the maybe more traditional, the non-TWA framework. The term that's kind of comparable or associated to this term is now up here as a conversion term in the potential energy budget, and then it gets like further converted to EKE. So this is kind of the picture that we have in mind when we think about the GM term in Miki, and then so what was I gonna say? Again, this difference has to do with the fact that in the non-TWA framework, there's an eddy form stress in the continuity equation, right? But in the TWA framework, this eddy form stress moves to the velocity equation. It's kind of this guy here. So actually, the current parameterizations that formulate a prognostic equation for the EKE budget, they are more over here. They kind of use this non-TWA framework, but we think that maybe this TWA framework may lead to a more consistent way to formulate such a parameterization, but we're still discussing this, and I'm taking questions on that. To summarize, I showed you some work in progress in which I'm trying to diagnose and characterize the EKE budget terms and conversions between different energy reservoirs in our stacked shallow water model Neverworld 2. And we're also comparing the TWA and the non-TWA EKE budgets. And then next steps are, of course, to evaluate energy budget-based parameterizations, and then a long-term goal is to think about what of this carries over to full ocean models from our stacked shallow water model. Thanks.
Wonderful. Thank you very much, Nora. So people have already kind of lined up for questions. So Hussein was first.
Hi, Nora. Thank you. This is very fascinating. I love this kind of work. My question is regarding the way you decomposed the eddy kinetic energy and the mean kinetic energy. Does it guarantee that together they give you back the total kinetic energy?
Yeah, exactly. That's exactly the point of this definition, that it conserves energy, right? That you exactly get this decomposition, right? That's the way we define EKE as the difference, right? There's an alternative definition of EKE where you kind of use the prime squared, right? Which does not conserve energy. Mm-hmm. On the downside, our definition can produce negative values, right, for EKE. That's the advantage of the other definition. And actually, you see that sometimes also for
Actually, your definition is positive. It's definitely positive. Do you see negative?
Yes, because see,
Where?
right, it's not guaranteed that this term is positive. So that's the difference between the.
It is.
How is it?
It is possible to prove. I can talk to you offline.
Yeah, I think it depends on the filter. Yeah, I think we can talk about this offline, right?
Actually,
it's going to depend on the filter and the weight of the filter.
But I'm wondering if you do you get back HU squared when you integrate over all space? Because now you add this with the mean kinetic energy, you get the first term with the big bar on everything.
Right.
So the spatial average of this, do you get back HU squared?
Oh yeah, exactly. That's this area volume, right? That's the fact that the filter preserves the area integral. This filter A over bar A preserves the area integral of the field. Okay. So that's the way we on purpose just constructed our filters to have that property.
Thanks.
Thanks. Okay, so next up was Steve and then Takaya.
Thanks, Nora. Great. Thickness weighted versus non-thickness weighted. Does that basically boil down to a momentum equation versus a vector invariant velocity equation? Is that, because MOM6 is coded not with the equations that you wrote down. They're coded with a vector invariant equations with a Montgomery potential and a potential vorticity F plus zeta. And I noted that you did your eddy decomposition. I think I asked you this before in a previous presentation. I was a bit confused. Can you comment on that? Because, just to let me completely formulate the question, the thickness weighting is more natural in the formulation that you presented. But my question is that's not the equations, the velocity equation you wrote there is not what we discretize in MOM6. So are you doing this diagnostics online or offline? And maybe you can comment on some of that.
Yeah, so no, I'm doing the diagnostics offline, but actually, I guess I only wrote it this way to save space. This is just the derivation of the continuous MKE equation. But when I diagnose these terms, I really take the terms that get written out by MOM6. So sorry, I realized this. You asked this before. I should have written this in with in the vector invariant form. But yeah, I think.
The thing is, when you write it in the vector invariant, you get vorticity fluxes that pop out, and there's a bit of a distinct interpretation, at least naively, I think. Maybe I'm wrong, but I would think that would play a role in the interpretation of the fluxes that you're looking into.
No, that's a good point. We should do this, and maybe it will actually clarify some things and how these terms relate to the terms that Bill Young finds in his paper. And yeah, thanks.
Sure.
Thanks. And Takaya, and then we'll move on to the next talk.
Thanks for the great talk. My question is rather technical, but I just wondered whether your because you use a spatial filter, does your filtered fields does the gradient operator commute with your filtering?
No, it does not. Exactly, it does not. So we're doing this because we think we're using the spatial filtering approach because we think it's more consistent with the idea that subgrid scale parameterizations want to solve, or want to address. But yeah, as you point out, there are difficulties with that. Yeah, the filter doesn't commute with derivatives close to the boundaries, and so that's why I said, right, that these terms here, they're written kind of nice and compactly, but they look more complicated because you have these non-commutation properties in there, so you have to, yeah, when you diagnose them, account for that.
Yeah, thank you.
Okay, I don't see any other questions. So thanks so much, Nora. That was great. A lot to think about. So next up, so there was a swap in the schedule. So Michele Busicotti, I believe you're next, right?
Yes.
So you should be able to share your screen. Want to give it a shot?
I'm trying. You should see the screen.
Perfect.
Okay.
Yes. Wonderful.
Okay. Great. Thank you very much, and good morning. I am, yes, Michele Buzzicotti. I am a researcher at the University of Roma Tor Vergata. And in this work, I'm trying to study the ocean, trying to characterize its mesoscale structure using a coarse graining approach. This work has been done in collaboration with Ben Storer from the Department of Mechanical Engineering of the University of Rochester, and also with professors Hussein Aloui, also from Rochester, and Stephen Griffiths from the NOAA. So what do we mean, what do we have in mind when we think about coarse graining? Let's see, our approach is, comes from the idea that is generally used
Did something happen? It's complete. I lost the Zoom connection.
Yeah, I think his internet.
I think his internet went out, right? I thought it was me initially, and so. But
yeah, we were all testing our connections.
Exactly, I was testing my connection, then I realized it wasn't me.
Yeah, it's not us.
Hey, Hussein, are you able to give it as a backup?
That's what I was about to say, Hussein. If you're still
Something
here.
happened. It's complete. I lost the Zoom connection.
Yeah, I think
Hussein, you're muted.
People contacting. I thought it was me initially, and so. But
yeah, we were all testing our connections.
Exactly, I was testing my connection, then I realized it wasn't me.
Yeah, it's not us.
Hey, Hussein, are you able to give it as a backup?
That's what I was about to say, Hussein. If you're still here.
Happened. It's complete. I lost the Zoom connection.
Let me.
Can everybody be muted? Everybody be.
I thought it was me initially, so. But
yeah, we were all testing our connections.
Can everybody just shut up?
Connection, then I realized it wasn't me.
Yeah, it's not us. Hey, Hussein, are you able to give it as a backup?
That's what I was about to say, Hussein. If you're still here.
Happened. It's complete. I lost the Zoom connection.
Everybody.
Okay. Is the echo wrapping around over? That was an interesting thing. And so, Hussein, are you the one presenting, or?
Until Michele maybe comes back online, I can continue from what he was, from where he went. So let me try to do a good job. I mean, this is not the slides this is a draft. I don't have the most recent slides that Michele had.
Oh, yes, I'm back.
Oh, perfect. Okay.
I'm back. Okay. Never happened during the conference. It happened now.
Okay, no worries. That's the world of Zoom that I'm in.
Okay. So I think I lost more or less the signal here.
Correct.
I was okay. So I was just, I will briefly restart saying that our approach comes from the idea of large, that is generally used in large eddy simulations, where coarse graining is used to scale separate the flow. Like, for example, in that case, you want to actually consider only the large scale of the flow without really considering what happens at small scales. This makes sense because if you think about the three-dimensional turbulence, what you know that you can observe if you look at the vorticity of the field is that the field is composed by small-scale vortex filaments, like the one that are here represented in orange, and the other scales that are a little bit larger, like the gray. And in this case, with this approach, what we want to do is to have a coarser version of our field, which means just to take a look at the gray structures. So how can we do that? To do that, it's generally how it is done. It is done by applying a convolution between the original field and the filter kernel. So in this way, we can define our coarse velocity field, which is defined by the U bar here, and the scale that we want to filter actually is included, is defined inside the definition of our filter. So this is generally what is done. What we have to do now to analyze the ocean currents, it's a little bit more complicated because our problem now is not on a flat space, but is on a sphere. So we have spherical coordinates, and the coarse graining in this case becomes a little bit trickier, especially if you want to have a coarse graining which preserve the commutation with derivatives. And how can we do that? This is well explained in the paper by Alui in 2019, where all the mathematical details are actually taken into account. So I go quickly to save some time here. Anyway, what I wanted to discuss, it's what kind of filter kernel we have used in our work. And this is a tanh filter that is, if you see in 1D, it has a shape like this, which is flat, and then it decays very quickly. And then this is the kind of structure of our filter that it has on the two-dimensional surface of the sphere. And so in this way, we can play with this parameter to change the filter scale. So to give you a quick idea of what it happens to a field when you coarse grain following this approach, this is an example. So here we have, let's imagine we have our image, which is our fully resolved field, and then we apply a convolution with the filter kernel, and our result that we have in the end, it's something that has that reminds only of the large scale structures of our original field, while the small scales are completely blurred. So this is an example. Let's go to see what are the data sets that we actually used in this work, in this analysis. And we used both observation data and model data. We used, for the observation, we consider the Aviso satellites measurements that are an L4 high processed data set. They are on a grid of a quarter of a degree, and the period of time we considered goes from 2010 up to 2018. So this is also the product ID that is available to be downloaded on Copernicus. On the other end, the model, the data that we used are the data from NEMO, that is a weakly coupled ocean atmosphere model that is that has a part of data assimilation of the nudging type plus a forecasting system. This is also a grid of a quarter of degree, and the period of time we analyzed here is a little bit shorter. It goes from 2016 to 2019. What is more interesting, I think important also for our work is to stress these few points, is that we considered only the surface layer of the ocean. So we considered a two-dimensional velocity field on a sphere, and we have used the geostrophic component of the velocity. So we have inverted the velocity from the sea surface height that was either observed or forecast or let's say modeled by NEMO. And we also split in this presentation at least our analysis, especially on two different regions. The one is the first is from 15 to 90 degrees north of the equator, and also the same one, 15 to 90 degrees south of the equator. So these are two regions that are highlighted in this picture. of course, we can extend this kind of procedure to analyze whatever region, small or also the full ocean that we are interested, depending on our problem. It is also interesting and important to stress one point of our approach, that is that we had to deal with continents somehow, because at some point when we are doing the coarse graining with our filter, at some point we will reach a place in the ocean that goes close to the continent. And here we need to do something. And what we decided to do is to treat continents as a zero water velocity. Let me stress this also, because this is not actually really a limit of coarse graining. This is our choice. And we choose to do that because this is a choice that is generally done also when you model sometimes the ocean. You impose the continents as a constraint on the velocity. And also the other reason is because the other way we could have used is to have a filter kernel which is changing in space when getting close to the continents. But in this way, if we do that, then we don't have to deal with zero velocity continents, but we introduce a space dependence on our filter kernel, which will break the incompressibility of our flow. So that's why we decided to treat continents at zero velocity and don't change the filter kernel. So, okay, let's see what is the main observable we want to look at, especially in this work. And we are interested in scale decomposing the total kinetic energy. So the kinetic energy is defined as usual. And let me stress that here I put the density of the flow of the water, but in practice we have considered this term as a constant. So the only really spatial dependencies comes from the velocity square. And as I said, introducing a filter scale, we can split the coarse energy from the fine energy. So the coarse energy has a definition which is quite intuitive, I think, because it's just the squared of the coarse velocity field. And this represents all the energy that is at a scale that is larger than the filter scale. On the other hand, we can also define the fine kinetic energy, so all the energy that is smaller than the filter scale. But this, it's worth to say a few words about this definition because it's a little bit less intuitive, I think, because we have applied here this further filtering approach, filtering procedure. So the fine kinetic energy is not defined just as the total energy minus the coarse, but we have to apply on top of the total energy, again, another filtering operation. And this is because if we use the more trivial definition, if you want, we get a quantity which is not positive definite. And this is something that it's better, we preferred to avoid because we wanted to, anyway, we had in mind something that was an energy, and so we wanted to have a quantity which was positive definite. And the reason is, it comes from the reason that this definition is positive definite can be explained following a Jensen inequality, but this is a simple mathematical proof that it's very similar to the one that is used to prove that variance is positive definite, for example. We just have to consider filtering as a weighted average. The other reason why we wanted to use this definition is because indeed, if we look at the total energy filtered and then we average on space this quantity, here the curly brackets means the spatial average. If we look at this quantity, we see that indeed it is equal to the total energy without spatial filtering. So it means that in some sense, spatial filtering the total energy conserves energy. So if we sum this definition of fine plus coarse energy, we recover the total kinetic energy as we are used. So let's look at some visualization to have an idea of what happens. Here, let me stress that I am showing also the velocity in the equatorial region, but this is obtained with a beta approximation, but we are not going to use this velocity in this work anyway. But what it's more interesting to observe is that here we have a snapshot in the Atlantic region where we see the total energy. Here we see the coarse and the fine energy. In this case, we can see that if we choose a filter scale that is smaller than our grid, then what we obtain is that indeed all energy is contained in the coarse component, while the fine is just simply zero. So it's more interesting to see what happens when we increase the filter scale, and we see that indeed the coarse kinetic energy becomes coarser and also a little bit less energetic. So indeed here the color bar are always the same, and we see that here the course is a little bit darker than the total energy, and indeed some energy appears to be in the fine energy, in the fine scales. What is a little bit, I think, worth stressing here is that indeed this definition of fine kinetic energy does not look really fine, small scales, and this is an effect of the applying the extra filtering on top of the total energy. So in some sense, this definition, so this extra filtering, what it's doing is just smearing a little bit the energy around. And so what we have is that in the end, the energy that we are observing here is just a region where the small scale energy is contained. If we really want to go and look at the small scale structures, we need to use the other definition that is not positive definite, but and here it's clear this effect, but what we can see is that indeed there are regions, even if small, where we have bluish values that are indeed corresponding to negative values of the energy, of this definition of fine energy. So this is even more evident if we go towards a larger filter scale. And this is again what we could obtain using the two different definitions of fine energy. So okay, now we have filtered just a snapshot in time, but what we can do, we can filter again at different scales, a time series, and we can see what happens to the seasonality in the ocean at different scales. And this is what we are trying to show here. Here it's the ocean energetic at the fine scales. So this is the fine kinetic energy averaged on space in the north equator, that is the solid line, and in the south of the equator, this is the dashed line. And what we have on top here in yellow line is the same quantity, but from a velocity field that is filtered at 200 kilometers. And then in green, we have the field that is filtered roughly 400, it's 360 kilometers. The vertical lines here indicate the month of May, sorry, and what is interesting to see, that was a little bit surprising for us, is that indeed what we see is that the growth of energy happens just at the end of the winter, and then it continues in the early spring, and it stays more or less for the full summer, and depends a little bit on the fluctuations every year, but this is the general trend. And this was a little bit surprising because we thought that the energy should have had the peak more in the winter, as it is more used to be observed, for example, a smaller scale, where you have more the interaction with the atmospheric flow, probably. So this is also an example that shows us the importance of having a way to clearly decompose the scale of the ocean flow to really access what happens at all different scales. Another thing that could be interesting to see is what happens to the percentage of kinetic energy, so percentage with respect to the total. And here we can see again the different filter scales, so 100, 200, and roughly 400. And here we have that what is visible is that the percentage of energy contained in the fine scales, so scales smaller than the filter, in the north of the equator is always smaller than the percentage of energy that is contained at the same scale in the south of the equator. You see that all the lines, the solid lines, are always a little bit below. So that suggests that actually there is not really an homogeneity in the flow between the north and south of the equator. And it suggests that in the north of the equator, there is more energy contained in larger scale structures. So now we can do we can scale decompose the energy even better. We can extract the energy spectrum of the ocean, and this follows from the idea proposed by Sadek and Alui in the paper in this Physical Review Fluids of 2018. And how can we do that? Well, the idea is simple, and we have to take the coarse kinetic energy up to a scale that here I indicate as L1, KL1. And then we take the coarse kinetic energy up to another scale, which is smaller, up to, for example, L2 here. And then we take the spatial average of these two quantities, and then we take the difference of the two. So in this way, we have a numerical way to implement a sort of to estimate the energy spectrum. In some sense, we have the energy that is contained in the band that comes from the difference of these two quantities. So in principle, when K goes to K1 minus K2 goes to 0, we have we recover the derivative of the coarse energy with respect to k. Here we use the log derivative, but it's just a choice. We can use also the normal derivative. This is an intuitive result that is, anyway, this is a good definition of the energy spectrum, and it can be proven mathematically that this is indeed a positive definite quantity. The result is not so trivial, but it is also well explained in the paper by Sadek and Alui, in the same paper of the PRF 2018. So let me show the spectra then that we obtained using this exactly this approach. And I want to stress, this is the spectra, first of all, obtained averaging the energy over the full region that is north of the equator. And what we observed are, I think at least are two things that are interesting worth to mention. One is that most of the energy you can see that is in the mesoscale is indeed contained between scales that are below 400 up until a little bit below 100. We have measured that actually 70% of the energy is contained between 400 and 100. So this gives us a really clear understanding, estimation of what are the characteristics structures, what is the size of the characteristic structure of the mesoscale in the mesoscale ocean. The other thing that is interesting, and we are still trying to analyze a little bit, is the presence of this kink of energy, and we are actually trying to understand how robust it is, and because it actually could suggest the presence of a superposition of different physics at different scales, but maybe it's just we still have to assess how this point here is robust. Okay, so this shows clearly the importance of having this scale decomposition. Now, what we try to do is what happens is instead, if we try to decompose the flow following a different decomposition, which is just the usual, let's say, mean eddy decomposition that comes from the Reynolds averaging. So in some sense, I can go fast. I think here we just want to define the mean kinetic energy that comes from the mean velocity field that is averaged on time over the full time window. And then we have the fluctuating energy that comes from the eddy field, which is obtained as the difference between the total and the mean flow. So let's see what happens if we do that, for example, on a snapshot of the ocean. And here we have the snapshot. Here we have the total energy. Here, and then we go to decompose this highlighted region into the three different components, which is the eddy component, which in this case we see it looks at least qualitatively extremely similar to the total. And indeed, we see that the mean energy that is below here, so this is a constant in time, term, which is, while these are snapshots, but this mean energy is indeed very as energy which is very low. It's much darker if you see the color. So most of the energy is removed by the time average. And what is also interesting is to see that actually in the mean energy there is not a clear presence of any clear structure of a characteristic size. So there are structures more or less of all sizes. And then here I show the cross term, which is also not positive definite, so it's a little bit difficult to interpret. Anyway, its average in time is 0. So to see what happens also when we average in space these quantities, here we see the evolution of the spatial average in time of the 4 different terms. We have that actually the total energy is pretty much the same as the eddy. So indeed we see that this decomposition is not really producing a clear decomposition, because I mean actually the mean is going to 0. And also the cross term, once averaged in space, it has fluctuations that anyway are of the order of the mean. And let's see, these are of the order of 0.4, while the total energy is of the order 20. So there is a factor 50 at least, roughly, of difference. So the total and the eddy are pretty much the same, while the mean and the cross term are almost negligible. Let's try to see why this could be. And
sorry, Michele, if you could try to wrap up
yes,
the next minute or so.
I'll wrap up some main thing, but this is still an interesting point, which we show that actually we can calculate the energy spectrum of the flow, which is time averaged. But this time we don't have the full mean flow, but we time average the flow using a moving time averaging window with the size of tau. So here we have the energy spectra of the different flows of the different flows that are time averaged with tau that is larger and larger. And what we see is indeed that not only the full energy is very much decreased when the averaging window is large, but also we see that the energy is removed more or less with the same speed at all scales. And to see that, we can look at the same curve normalized by the energy that is not averaged in time. So the first curve here, the dark curve, is 1 by definition. We show this quantity, while the other ones, they start to decrease with pretty much without any clear scale dependence. So this is just reverting this plot, and here we show, so as a function of x, all the different taus. And what we observed is that actually there is for small time windows, there is the energy is it's mostly removed at small scales that are represented here by now the light colors. While when we enter into the range where tau becomes larger, and larger at least a little more than 10 days, so it's not so large, all scales start to be depleted with the same speed. So just to conclude, up to here, I have shown data that are from the Aviso data set, so from observation. We wanted to see if this result is actually consistent. It can be observed also in the data from NEMO, from the model. I'm not showing the visualization, but this is the comparison. So this is the same plot, but calculated now from either from Aviso or from NEMO. And what we observe is something interesting. I think the first thing is that at small tau, we observe that there is something similar that looks at least qualitatively similar. So when we time average our velocity field and we calculate the spectrum, using time windows that are of the order of 10 days, we see that the energy is mostly removed at small scales, as we observed in the Aviso. But then when we go to look at the large scales and we start to average for longer times, we see that actually NEMO do not tend to lose energy as much as we have seen in the Aviso dataset. So what we obtain is something that is not almost zero and without a clear structure size as in the Aviso, but in NEMO we observe the presence of a very large coherent structure that is also much more energetic. And here we can actually understand when it happens and what are the scales where this effect is more evident. And this is, I think, an important observation that comes using this coarse graining approach, which actually allows us to compare and validate model or also observation data. Okay, so just to conclude, I hope I had anyway the time and I managed also with these problems to give you the idea that coarse graining is an important tool, I think, to analyze the structure of the oceanic currents. And it is actually a good tool also to flow decompose, the flow and to compare data that comes from model and from observation. One last thing, which is also introducing the next talk, is that all the results I've shown up to here are results that aim to show how much energy is contained at a given scale. But this is something that is a static information, if you want, because it's not telling us where the energy is going. What we can do with this approach is actually something more. We can try to coarse grain the equation of motion and trying to estimate actually the amount of energy that is transferred from a scale to another. And this is actually what Ben is going to talk about in the next talk that I hope you are going to enjoy. Thank you. Great. I'm sorry for the problems.
Yeah, no worries. Thanks, Michele. And again, Zoom issues happen. It had to happen at some point, so it's pretty normal. Just as a reminder, if everybody can stay muted, even if something crazy happens, Elizabeth and I will kind of figure out what to do next. So just use the chat. Okay. So even though we're a little bit behind, we still should take a couple of quick questions. So I see Malte first, and then Dhruv.
Hey, yeah, really interesting talk. So one thing I was wondering about your Aviso field that you're using, which you're calling the total velocity. Are you sure what exactly it is? Because it looks a little bit like, if you go, for example, to your slide comparing NEMO and Aviso, so that large coherent feature that you're talking about in the mean kinetic energy in NEMO is the Gulf Stream. And yeah, but it is certainly real. So it should show up in Aviso. if you
Well,
use
I
the
mean,
full
yeah,
velocity field, you might be using the.
Let me stress that these quantities are time averages. So the fact that we don't see the Gulf Stream in Aviso is because actually it has been removed by the time average. So if we see, for example, the Aviso data here, where we see the total energy, indeed we see the presence of this of the Gulf Stream.
Yeah, you don't see it much along the coast where it should be, where it's most stationary.
Well, that I mean,
so that's where it should show up
yeah.
fully in the mean flow, in a mean KE.
Yeah. Okay. So I'm not sure if what we do is that we take the data from the Aviso and we extract the velocity field just using the geostrophic approximation.
You might be starting with the anomalous Caesar-Versailles field.
Correct. Yeah.
Which is why you're
okay.
Basically, if you do long enough time average, your mean flow seems to disappear, which would be consistent with that.
Okay.
Might want to double check that.
Yeah, we'll double check. Thanks for sure.
Thanks. Dhruv, do you want to ask a quick one?
Yeah, one of my questions was actually the same one. So, just to carry on with what you're discussing, when you get the Aviso field, there is two variables. There is ADT and SLA. I think you're using SLA. Try to use ADT that has the mean field in it, and I think that should.
Now I think maybe it's not, but it might be. I mean, I'm not 100% sure. We need to double check also
Anyway, that's just
thanks for the
The more important question I had was to do with the little kink that you see at about 50 kilometers, and I was wondering if using your way to extract the spectra, you can do it in wave number and frequency space. So K and omega, like you're kind of doing with tau, right? You can go to frequency instead. And when you do that, there's a signature of waves or something, it should really, jump out.
We for sure we didn't. I didn't try. I think I'm not sure. It's not. I'm not really sure if it's possible to be done with the same approach, also extracting the spectra in frequency, in temporal frequency. Maybe Hussein, you know better. I don't know if.
So maybe we can carry this offline. Yeah. So maybe move to the next talk and then
something that
come back to it.
Think a little bit about, but I agree it would be interesting anyway. Yes.
Indeed, yeah, it's a very good point. Yeah, thank you very much for the talk.
Thank you.
Okay, so next is going to be Ben Storer, who's going to kind of continue along those lines of course, grading and seasonality. Ben, I see you. Okay, great. You should be able to share, hopefully.
Okay, let's just see. And is that coming through?
Perfect. Go.
Okay, so yeah, as was mentioned, we're kind of continuing on the same line as Michele was talking about, kind of taking this same course grading technique, but now we're looking at energy transfers between scales, so energy going from small scales to large scales or vice versa, looking at how that depends on length scale that we're using to study, and also some flow parameters like whether you're strain or vorticity dominated, and working with the same group of people, so myself, Michele from the last talk, Hussein and Louis, and Steve Gravis. So just to outline the data set we're working with, so I'll be using the NEMO data set. This is the same NEMO that Michele mentioned. So it's kind of an assimilation analysis forecast, global, quarter degree. I'll be using the 5-year period, 2016 to 2020. It's available through CESM with the product ID available there if anyone's curious about it. And it's a weakly coupled ocean atmosphere. For our purposes, we're just going to consider just the surface layer, so we're ignoring anything at depth. We'll doing the same thing as Millie, where we're saying land is a zero velocity ocean for the main purposes of you get commutativity with derivatives. And we'll be doing averages over geographic regions of interest. In particular, we're going to this is the region I'll be highlighting out for what I'm going to call the Gulf, the Croatia region that we're subsetting, and our ACC region. Our equatorial band of plus minus 15. And when I say north equator, I mean everything above that 15 north, and south will be everything below 15 south. So it's going to be the the geographic divisions that we'll talk about. We'll do a lot of averages over those regions. I guess just to kind of bring back in mind what coarse graining is essentially you pick some length scale in meters and you're smoothing or blurring your field, which is effectively a locally weighted average in space. That's done in such a way that it will commute with differentiation so that we maintain, for instance, incompressibility. And doing this, we can extract large or small scale energy as a function of space, time, and scale. Spatially, you take your data and you just gain one more dimension, which is length scale. So if you flow having lots of different size features and you want to pick some filter scale L, you get things that are larger than your filter scale and things that are smaller than your filter scale. And just as a sample illustration, if we create some artificial dimensionless signal here in green, we just have some kind of noisiest signal, a sample filter kernel in purple, which is the same tangent object Michele was using, but now this one is defined to have a width of 1. We apply our kind of moving weighted average, we obtain this smooth yellow curve. So essentially, this local averaging done in a kind of consistent way to enable differentiation. There's a few different things we'll be measuring using this, so we'll split the definitions here to be concrete. So the first thing, of course, that we have is our coarse velocities, our solenoid components. Using those, we can extract a large scale or coarse kinetic energy, which is just the kinetic energy of those coarse velocities. After that, we also define a small scale energy. We'll be doing it the same way as in Michele's, where it's the difference of kind of the filtered energy minus the energy of the filtered velocities. And this choice is done to maintain a positive semi-definite field. So now we have energy on this larger side and energy on this smaller side. That when added together and averaged over the whole domain will return the total energy. Next, we'll have this energy transfer term, which we'll call pi, which is the product essentially of a large scale strain, excuse me, and a small scale stress. And it's signed, essentially its idea is energy leaving this large scale and going into the small scales through the nonlinear interactions. So it's a measure of this direct cascade term. And the last term we'll be using is the Kubo Weiss parameter, which is essentially just going to tell us whether you're strain or vortex dominated. But to give kind of more kind of intuitive definitions for all of them, large scale KE is just your energy at scales larger than your filter scale. Analogously, small scale KE is energy at scales that are smaller than your filter scale. So if you filter at, say, 100 kilometers, large scale is energy at things bigger than 100 kilometers, and small things smaller than 100 kilometers. Pi tells us if it's positive, you have a direct cascade. So energy is moving from big to small. And if it's negative, you get an upscale cascade, so small to big. Whereas Kubo Weiss, positive strain dominated, negative vortex dominated. These are kind of the main parameters we'll be looking at. And if we go back to our sample signal, this green one, with our sample kernel, we get our large scale energy in yellow and our fine scale energy in red. And we just get that they are both positive semi-definite, with large scale energy kind of mostly growing. We have these broad features, and small scale energy growing when you have these sharp drops. So we have this division into large and small scale. So where we do kind of a lot of quantitative analysis, we first want to ask qualitatively what's going on with these, what kind of story do these different fields tell us. So we're just going to zoom in on one region of interest so we can see the details a little better. We're plotting here just 1 year averages of each of the fields, with each row being for a different length scale, 100 kilometers in the top row, down to about 460 in the bottom row. So we're getting larger filter scales as we go down. First column is our large scale energy. Second is our transfer pi. And the right one is our Kubo Weiss parameter. And so in terms of kind of the story that we get broadly out of these, if we first look at our large scale energy, we have more of these features at the beginning. As we go down to larger scales, as expected, of course, it blurs out. It's a broader feature, but also the magnitude's going down. So it's a common color bar within each column. Within each column. And this makes sense. If you're saying energy above a scale L, then as you move the L up, some energy gets left behind. So this kind of KE story is expected and consistent. Next, if we look at our pi, we see at the, say, 100 kilometer scale, it's broadly dominated by negative or inverse cascade values. So we have that these this on the smaller scale end, you have a more active inverse cascade across this 100-kilometer scale. But as we go towards larger scales, you get more of a balance between these positive negative regions, so that this net inverse cascade is weakening as you go to larger and larger scales. And the other one, the cube of ice, where here red is strain dominated, blue is vortex dominated. We see that at the smallest scales, it's a little more, seems to be a little more vortex prone, but there is still substantial straining regions. And as we go larger, this kind of seeming parity between the two becomes a little more pronounced. So there's not necessarily as great a bias as there is in pi, where we see a substantial blue dominance. And so some questions we might get from this then is we can ask, how does KE and pi differ if we're looking at, say, strain regions versus vortex regions independently? If we do that, what sort of temporal structures do we see? And also what kind of regional variations do these features have? So before we dig into those, we'll quickly look at just the overall time space averages, just give us some point of reference. So on the left column, we'll be plotting the same kind of spectrum idea that McKelly had, which you can think of as being k times the energy spectrum, or the log k derivative. And on the right is this pi density, so the cascade density, with north of the equator on the top, equatorial band in the middle, and south at the bottom. And just highlighting 500 kilometers in red and 200 in blue. And the main idea here, the main story we're taking away is pi is broadly everywhere negative. So we have this inverse cascade going for all the scales that we're looking at. And it broadly peaks around the 200 kilometer mark. So later on, we'll be pulling out some specific scales. So 200 kilometers ballpark is where the strongest pi is happening outside the equator. Equator tending toward larger scales, which isn't too surprising. And also energy peaking around, say, the 200 or 150 kilometer mark. So as we have an idea of, if we pull out those scales, we're looking at roughly the most energetic. Like with the data McKelly was looking at, the Aviso side on the NEMO, we also see this kind of 80 kilometer or so minimum, like a local minimum. So people have thoughts on causes or implications of that, I'd be very happy to hear those. But so we have our reference point telling us that 200-ish kilometers is broadly where the strongest cascade and energy are occurring. So now we can do this partition. But before we want to break up strain vortex regions, we should ask ourselves, is this a silent partition? Does this actually make sense? Let's do that first. In this top plot, we're plotting essentially an area histogram. So the horizontal axis is the cube of ice parameter. And we're asking how much or what proportion of the area is within each cube of ice value for straining regions and solid lines and vortex regions and dashed. And the three different area components we're looking at in the different colors. And the main the broad story here is there's not a huge disparity between strain and vorticity, areas not too far off parity. But the main thing is, as we go towards smaller magnitude, there is a fairly quick drop off and percent of area, telling us that there is a bit of a distinction between positive and negative values. One kind of curious thing that we don't quite have much of an understanding for why this is going on or what it means, but is that I have this fairly consistent slope of magnitude 1 on the small cube of ice side, and that's fairly consistent depending on scale and time and region. So if anyone has any thoughts on this afterwards on what this might mean or what this might be happening, I would again be very happy to hear any thoughts. But the main takeaway from this is that if we look at our course energy plotted in green and our energy cascade plotted in purple, it's localized in a cube of ice space. That is, if you look at these small magnitude values, there's very little going on. So this tells us that it's a reasonable idea to use a cube of ice to partition space. There's no false dichotomy around 0, and so that part is comforting. It tells us we can reasonably proceed. So since we know we can now do this partition, we can ask, well, what percent of our energy or of our cascade pi is occurring in strain or comparatively in vortex regions? And how does this change with scale? So on the right, our first column is looking at this north of the equatorial band region, so north of 15, and south, right, south of the equator. And in each plot, we're doing 3 lines. So green is that full area. Yellow is focusing on just the currents. So for the left column, it's Gulf Stream and Kuroshio. And on the right column, it's just the ACC, with purple being the rest, or what also is called just the open ocean. You see everything outside those currents. But this first row, we're plotting the net proportion of pi, or this cascade, that's occurring in strain regions. So we saw that basically across all our scales, we have a net inverse cascade, and it's true across both strain and vorticity regions. But if we look at how much of that's actually occurring in strain regions, we see that we're actually getting a majority between 70 to 80% occurring in strain regions. And that's broadly consistent across scale, especially if we consider that this band of scales here is the most dominant pi. It has the cleanest kind of 70 to 80% band. And that's consistent north and south, and what we're looking at currents or outside the currents. So kind of the straining regions have these most efficient pi. And just to clarify, the envelopes on them show the temporal variation, the first and third quartiles. Now, instead we look at how energy is divided across them. We have in the middle row how large scale energy is partitioned, and in the bottom row how small scale energy is partitioned, with, for reference, these red lines showing 2 kilometers. We have that we're much closer to parity. It's much closer to 50% of the energy is in these straining regions, and so by comparison, 50% in the vortex regions, especially if you're looking at things, say, above 200 kilometers. Below that, you start to become a little more vortex dominated, but even at, say, 100 kilometers, you're only around, I still have about 45% in strain regions. So even the strain regions have this much higher proportion of the net cascade, they have about parity or about half of the energy in the actual energy in strain regions. So we have this cascade term pi, which takes energy from, in this case, small scales up to large scales, because we're inverse cascading. So we're going to define, as we're going to call a cascade efficiency term, which is the relative strength of pi to the energy that's available. So the strength of the cascade relative to the amount of energy available to be cascaded. And so we can ask then, what kind of regional or seasonal structures does this cascade efficiency present? So we'll start off looking at these top panels, where we've broken it down for each of the regions of interest, so the Gulf Stream, equator, north-south, Kuroshio, ACC, for strain-dominated regions on the left, vortex-dominated regions on the right. And the axis here is this cascade efficiency of pi over fine KE in units of per year, where since pi is negative, an inverse cascade, we're having a negative efficiency term. But greater magnitude value means a greater relative strength of cascade. So 2 main things pop out. The first one that we see, if we look at just the magnitudes between the plots, is that straining regions have a greater efficiency. And this kind of intuitively makes sense from the last panel we looked at, where we saw most of the cascade happens in strain regions, but strain regions only have about half the energy. They must be more efficient at their cascading, having here magnitudes of between, say, 4 to 8 versus just 1 to 2 on the vorticity side. But perhaps more interesting is that if you look at, say, the Gulf Stream, which is this first column, and the Kuroshio, which is this column, they're significantly more efficient, to have much higher relative cascades than the rest of the areas, including the ACC, the equator, or just hemispheres in general. It's most prominent in straining bands, but there's still somewhat of that pattern on the vorticity-dominated regions. There's just more overlap in these intervals, so we can't quite have the same statistical strength to make the claim on the vorticity side. What we also notice for those same 2 regions, Gulf and Kuroshio, that they have much greater annual variation or temporal variation. So we'd like to ask, was this temporal variation kind of a noise signal, or is there actually some coherence to it? And so to look at that, we'll drop down to these bottom panels. What we're doing is we've taken these 5 years, just averaged together to get a single kind of year average signal of the normalized variation. So basically, how much are you deviating from your mean value? Where since we have a negative efficiency ratio, we're going to have negative values being a stronger relative cascade, positive for a weaker relative cascade. And the equatorial bands themselves in the Kuroshio have kind of the cleanest signal, although it's still somewhat present in the Gulf Stream, where we see that your local summer, so here we have June, July, May, in the Northern Hemisphere, several months for the Croceo, tend to give you a relatively stronger cascade efficiency, or relatively stronger cascade than you see in winter. Gulf Stream is not quite as clear, and the ACC has no particularly coherent seasonal signal, which is somewhat consistent with other properties of the ACC that we've been looking at. So with the last bits we had, we were looking over the last few bits, we were looking at how different properties change scale to scale. Now we're kind of curious to see if we compare one scale to another, how do their temporal signals actually compare? Is there any significant differences between scales? So we're going to pick out a few in particular. So these top right piece comes from the NEMO data set we've been looking at. This bottom left piece comes from the visa that McKelly was looking at. And what we're plotting is north and south outside of those dominant currents. In green, we have this cascade term. In yellow, coarse energy, and in purple, fine energy, all kind of divided around 167 kilometers. And similarly here, we have fine energy in green and coarse in yellow. And the broad idea we're seeing here is that the increases in coarse energy tend to happen on a lag, or kind of occur later than the increases in small energy. It's substantially more clear in the Aviso data, but still fairly present in the NEMO, where we see this yellow curve tending to happen a bit later than the green and purple curves. So we'd like to quantify that a little bit, get an idea of how big is this lag that we're actually seeing. And so what we're going to do is we will take this green pie curve and just essentially just time shift it by varying amounts, basically half a year in one direction, half a year in the other direction, and track the correlation coefficient of that cascade with respect to small scale energy and large scale energy, and plot those and find when is it most strongly correlated. So we'll start with our small scale energy. The axis here is days of offset, with positive numbers meaning that pi comes later, and negative numbers meaning that pi comes earlier. And starting with a 100 kilometer scale down to about a 280 kilometer scale, we see that broadly speaking on small scale KE, they're all roughly centered around 0. And so there's no significant lead time one way or the other that this inverse cascade and small scale energy are more or less in phase together, with a -1 because pi is negative valued. And this is consistent whether you're looking at the currents or outside the currents. In contrast, if you're comparing with large scale energy, we see that there is this consistent shift of about 30 days towards one side, so that large scale energy happening about 30 days later than your small scale energy or the cascade up from the small scales. This is particularly strong when you're looking at, say, these purple curves, which is outside the currents. So this yellow currents curve tends to be more zero-centered than this outside of currents. And broadly speaking, once you pass about 250 kilometers, this signal weakens. So we're seeing that outside of, kind of looking at this outside equator part, large scale energy, so scale larger than 250 kilometers, lags behind your smaller parts and your cascade by about 30 days. And the 30 days part being just a rough estimate. So just to kind of summarize those points, so the bulk, about 70 to 80% of your energy cascade is occurring in the strain dominated regions, even though energy is roughly on parity between the two. The Croceo and the Gulf Stream has substantially larger cascade efficiencies than any of the other regions. That's consistent both in straining and vortex regions, though less clear in the vortex regions. Your cascade efficiencies generally tend to strengthen in your local summer. And outside of dominant currents, energy at large scale, so above 250 kilometers, lags about 30 days behind your small scales or your upscale cascades. I'll just finish on those two questions I had, if anyone has any thoughts on them. This 80 kilometer-ish energy minimum, and this log slope of 1 in a cube of ice space. So if you have any thoughts on what's causing those, I would be happy to hear them. Otherwise, I will stop there. Thank you.
Okay, well, thank you very much. Fascinating talk. A lot to think about. So Bob was first.
Thanks. I really enjoyed your talk, Ben. One thing that kind of struck me a bit, you're doing this as an analysis of a 1/4 degree ocean model. And when you pick out the Gulf Stream and the Kuroshio as having very different efficiencies than the other parts of the ocean, it strikes me that perhaps it could be because we're resolving different dynamics. So the Gulf Stream and the Kuroshio are much more subject to barotropic instability, perhaps than areas in the interior. So I think it would be really interesting to repeat this analysis with a higher resolution model, a 1/10 of a degree or a 1/12 of a degree or something like that, where we have a bit more confidence that we are resolving the spatial scales associated with, say, the smaller baroclinic instability outside of the Gulf Stream and Kuroshio, just to see if this same pattern of a remarkably different efficiency continues to show up in those higher resolution simulations.
I agree. And so there is actually a analogous to the NEMO data set we have. There is a 12th degree that's published also on the same CMEMS. The main reason we haven't done it yet is with core graining. So if you double your grid points in each direction, you actually get 2 to the 4 times increase in runtime because it's a kind of a 4 deep for loop. So the main problem is that we need substantially more runtime to actually process the data. But I agree, efficiency would let us push down to actually resolving more of those scales. It'd be interesting to see how many of these features kind of persist at smaller scales, or if this efficiency changes scale to scale.
Thank you. Dhruv?
Yeah, one of my first questions you already answered. And it was kind of related to the last point that you raised, which was that what's happening at these smaller scales. And just to say like what was said in the previous talk as well, that's kind of where you're running into the filtering or the interpolation scheme of a VSO. And so if you go to higher resolution model, you can really start to figure out if that's like a real signal or an interpolation signal.
Right.
The question that I have is, the question that I have is kind of separate, and it has to do with what the role of vertical velocities is, and the fact that you're only using the kind of the surface velocity field in trying to estimate the cascades of energies. And so do you have any comments about like the role of vertical velocities or kind of the vertical structure below the surface and how that impacts these calculations?
Yeah, so I guess the shortest answer is not really, because I haven't looked at it very much. So in terms of the vertical velocity component, my intuitive answer would be that it's just magnitudes wise, it won't be as such at the scales we're looking at. The dominant parts will be coming from the horizontal pieces, but we haven't actually quantified it to be able to say with any certainty. And in terms of the depth structures, it's one of the things where so there's no reason why we haven't done them was mostly a process in the top layer for the sake of if you do a 1/10 of the levels, it's 10 times faster. But it would be nice to, after this, kind of once you have this piece finished up and put together, then compare with what depth dependence is there. So the short answer is, unfortunately, I don't really have much of an answer for you, but it is something that we would like to see. It's just a matter of processing time.
Yeah, that's good. Thank you very much. Yeah, fascinating. Many things coming up. So we're going to move on to the next talk. And so it's going to be Jake. He's going to talk about some scale-aware eddy energy from satellites.
Thank you. I'm going to share my screen. Okay, can you guys see that? Yeah, that's working?
Go ahead.
Okay, cool. Well, thanks first to the organizers for, I think, lining up these talks in this order, because my talk employs a lot of the similar analysis that has just been talked about in the previous 2 talks, and I'm excited to collaborate with everybody. But I focus my analysis on a long track sea surface height measurements. So I'm kind of going to go through a similar procedure that has been described in the past 2 talks, but I think I see similar results in an exciting way. So I am a member of the CPT, specifically the observations group, and kind of what has motivated this work is to try to use observations to inform the development of eddy parameterizations as are aligned with the goals of the CPT. Like I said, to date, I have focused on long track measurements of sea surface height because they span the globe, They offer a really long time series, but then specifically they offer horizontal resolution much finer than that of the gridded Aviso fields, which are a 1/4 degree. But what I've done is kind of develop a tool that I intend to use for in situ data and hopefully can be used by a larger community. Okay, so my outline is I'll describe the long track measurements that I'm using and why I prefer them to Aviso gridded products. I'll define the use of a spatial filter, again, to partition energy into what I call mean and eddy components, but it's really just splitting energy above and below the filter scale. I'll show how I can generate some rough 2D map. Again, we are using a long track data, so it's not gridded in the convenient sense. But then finally, I'll say how I've been using these tools to explore spatial and temporal patterns of mean and eddy kinetic energy. And then at the bottom here, I've kind of starred my goal is to repeatedly show that this analysis permits the estimation of EKE in a scale-aware manner. And hopefully the intent was to be able to use this to compare to models of a given resolution such that we can generate or estimates of resolved or potentially unresolved kinetic energy in a model across a variety of resolutions. Okay, so here are the details of a long track measurements that I'm using. I'm considering measurements of a long track absolute dynamic topography, which is the difference between the sea surface height measured by the altimeter and the geoid, which is the surface that the ocean would take under the influence of rotation and gravity alone. So this really represents the total contribution to sea surface height, the signal that we're interested in, all currents, eddies, everything that's time variable and not. So this is a video of the collection of JSON2 data that along track are processed to a horizontal resolution of order 7 kilometers. And for the JSON satellite, which I'm showing in this video, tracks are occupied every 10 days. And I'll use the word cycle to mean when a single track is repeatedly occupied. So I've highlighted a section of a single track, this yellow region, and I'm showing just the values of ADT that are collected. This is one cycle, and a second cycle will show up as the video progresses. But because of the altimeter noise limitations, we have an effective resolution of order 50 kilometers, depending on the satellite that we consider. Certain satellites get us a better 10 or 15 kilometer improvement in that resolution, but we still kind of expect to adequately resolve the mesoscale eddy activity that we're interested in. Okay, so initial processing of all of these tracks adopts this following procedure. I first take in a long track gradient of ADT to estimate cross-track geostrophic velocity, where this expression at the left, where eta is ADT, and I'm ignoring the sign because I'm just interested in the magnitudes of these velocities. And in the main panel, I'm showing cross-track geostrophic velocity as a function of a long track distance for cycles computed along a single track over a 4-year period. Those are all the gray lines. And I've highlighted a single cycle, just as this example, where I'm applying then a spatial filter. And here I'm employing 3 different spatial filters. Their kernels are shown at the right. And the actual filtered field, where the black line is the unfiltered data, and then the blue, red, and green are the filtered fields using a boxcar, a Gaussian, and then what I call a sharp filter, which is a filter that I've worked with Ian Grooms and company and on the CPT to kind of present a different approach to how you filter. And so yeah, what do I want to say next here? Yeah, the filter scale is in this example is chosen as the filter factor is a unit of 10, which is 10 times greater than the grid scale. So in this case, going from a 10-kilometer data on a 10-kilometer grid to a filtering factor of 10, which would correspond to 100 kilometers. And so, yeah, part of this analysis is intending to show that the choice of the filter that you use can have a marked effect on the partitioning of variance across scales. Okay, so then once we filter the data, we can now define what I call mean and eddy kinetic energy. Mean kinetic energy is just the square of the filtered field, and the eddy kinetic energy is the difference between the total variance or total resolved kinetic energy and the filtered kinetic energy. The middle panel shows EKE for this single track that I've highlighted using these 3 different filtering kernels. And then finally, the lower track, just as an example, shows why this sharp filter, this different filter that I'm employing, does a better job at minimizing this last term in lower expression for kinetic energy, which follows from a traditional definition of eddy velocity with this U prime. And I'm only showing it here to show that the use of this sharp filter, the reddish orange line, minimizes this cross term, or the term that you want to ideally ignore. And so moving forward, I principally use the sharp filter because it does the best job of passing all wavelengths greater than the chosen filter scale. Okay, so then this is kind of our coarse approach, or crude way of getting from a set of 1D tracks, which are shown in the upper left, down to a map, a 2D map of kinetic energy. So here I'm showing that for the JSON2 or JSON3. This tool I'm building is kind of able to incorporate any satellite that you prefer. So again, this is an arbitrary choice, but I define a latitude and longitude grid where boxes are 6 degrees, and by moving around the globe, taking averages in these boxes, we can get a smoother map of total kinetic energy, mean kinetic energy, or eddy kinetic energy. And so that's what the colored map in the lower right shows. I've noted a few sections that are those colored boxed regions of blue and red and green, and I'll come back to them later, but I just wanted to introduce them for now. Okay, so thus far I wanted to step back and offer a short review to restate this analysis framework and try to present it as a tool that can hopefully be used. So far we've filtered cross-track geostrophic velocity. This can also be done with sea level anomaly itself, a less processed data set. And you can do this using a filter of your choice. I kind of built this to employ 3 different filters, a general boxcar, again, a Gaussian, and then this sharp filter that we're developing. The other thing that I didn't explicitly say is that I'm using a fixed value in my filtering factor, going say from a 10-kilometer grid to a 100-kilometer grid. But I've also built this tool to accommodate filtering from say a 1/4 degree to a 1/2 degree, where the filter length scale would actually change with latitude. And then a third option is to filter to the local deformation radius. And so once your filtering process operation is complete, we can then compute and define mean and eddy kinetic energy, and then begin exploring the partitioning of variance. And so a key point to make is that all of this analysis and data, this framework I've constructed, are accessed from Pangeo in a manner such that any user might be able to use it, not have to download their own data, and start from the same plane and hopefully be more transparent. So the upper figure that I'm showing is the same total kinetic energy going from all these tracks to a gridded map. And the lower figure is having applied a sharp filter with a filtering factor of 14 to get us from a 10-kilometer grid to a 140-kilometer filter scale. And then the define EKE. So this map shows the difference, or shows really kinetic energy at scales less than or equal to 140 kilometers. And you can see general patterns that you would expect of Western boundary currents and the ACC, and it's not that exciting of a map, but it permits you to define and constrain energy within bands that you're interested in. So far I've shown how you can filter to one filtering factor, but like the past 2 talks, and I asked what if we filter at one location across a range of filtering factors and kind of come up with a spectral analog. This is the result of applying a sharp filter using 30 filtering factors at one location, going from 60 kilometers up to 300 or so. And yeah, this is the figure on the left is kind of like a cumulative spectrum where I'm plotting the mean kinetic energy, or the filtered field. And as you, again, would expect, as you move from right to left, as the filter scale increases and variance generally decreases. The triangle that's on the farthest right is the total unfiltered variance that's resolved by the satellite. And so again, like as in the previous talk, we can say, what if we difference these adjacent mean kinetic energy estimates and define energy within bands? And this is kind of, again, a bit of a initial or crude way to show it, but this is then that difference where I'm normalizing the bands by their width in wave number space. And you can see kind of this, a similar shape again to the previous talks, but you can see what energy falls within each band. And I've shaded this gray region as that kind of bounding the mesoscale-ish, going from 60 to 300 kilometers or 250 kilometers, I believe. This is kind of akin to the true energy spectrum you might compute. But again, I've built this tool to kind of permit the user to define any band that they're interested in. And so then this is, I was showing that for one location. This is now the 5 locations that I had identified in my initial map, and I'll show them again. But now I've quantified the fraction of energy within this band, this gray shaded region, and you can see a lot of different structure in these different regions. I've chosen them to represent regions associated with different levels of eddy energy. If we step back and look at a more global map, this is another way of asking, how can we use this tool? So here's one example where I'm showing the fraction of total summer kinetic energy within the 80 to 250 kilometer band. This is a time average over a summer period. We could likewise ask, what is the most energetic band? Or we could look at the rate of decrease in variance across bands. So kind of, I'm building this tool again to be versatile in what you can do with it. But going back to those 5 sites of interest, this is what I was most excited to see this result, again, similar to those that were just shown. I'm now looking at the partitioning of variance in time. So I'm showing 4 sites that they're colored by location with that key in the upper left. And I'm showing the mean annual cycle of eddy kinetic energy at 3 filter scales. The middle and right columns, again, show those locations. And the 3 filtering scales I'm considering are the 80, 140, and 300 kilometer scale. And what I think is pretty neat is you can again see how energy at the small scales peaks earlier in the year than energy at larger scales. So that's really like if you consider this green region when the solid line peaks compared to the dashed or the dashed line, with the key being up here where 80, the EKE at the smaller scales is that solid line. And this has been shown in model results, like again, that was the 2 preceding talks. And it seems like in the AVISO data as well, but I wanted to use data that had higher horizontal resolution to kind of get down to the smaller end of the mesoscale where we can. So then from this, what I wanted to ask was, okay, well, what is the peak EKE month at different scales? And so this is my attempt at a map of that. Of just that. In the top panel, I'm showing the month at which EKE is a maximum at scales smaller than 80 kilometers. And the middle panel is showing the peak month between scales of 80 and 250 kilometers. And then the lower panel is the difference between them, asking again, like again in the previous talk, what is the lag between the peak in energy at larger scales or medium scales and that it's smaller? And you can see wherever there is red, that larger scale energy peaks earlier in the year than smaller scale energy. And it's kind of patchy because I've excluded regions where the seasonal change is only a small fraction of the mean kinetic energy itself. So I'm trying to select regions where we do see seasonality. Okay, and that's generally what I have. I wanted to conclude and say, yeah, I've developed this hopefully as a tool that we can use to kind of quantify energy within bands and compare this to models of various resolutions, again, with the intent of developing and testing and improving parameterizations. We can employ various types of filters and different filtering frameworks. And then these are those 2 figures of how I've used that thus far. And one of my next plans is to actually apply this to in situ observations, like Dhruv had asked a question about, specifically the oleander line, where I intend to again filter. This is all filtering in a 1D sense, so we can do that with any ship track. And with that, I will stop. Say thanks.
Thank you very much, Jake.
I'll turn on my video.
And question, well, Dhruv is first, and then Hussein.
Hey Jake, that was a great talk. I have a question that's to you and to, I feel like, a lot of people at this meeting, which is that I think a lot of people have shown this like summer peak in kinetic energy. And I don't know, I've never seen this feature kind of discussed before. And I'm just wondering, like, what does the literature say about this, or like, why is it there? You know, in contrast to kind of like the peak EKE being in winter, which is kind of what we have started to think about now that people are working more on sub-mesoscales and stuff.
I think, well, if I'm interpreting your question the right way, it makes me think of the Bo Chu paper from 2014, where he showed like EKE at smaller scales peaks in mid to late winter, and the larger scale mesoscale energy peaks kind of in the spring or early summer. You're asking why you see a peak in kinetic energy in the summer months, is that right?
Yeah, I think that kind of answers my question. I was just wondering, like, if that is the mechanism that we think is really responsible for this.
That's at this point my understanding of it. I'm still a little new to thinking about these things, but yeah, traditionally, yeah, the thought I imagine is, yeah, energy moves from smaller to larger scales with some lag, and like the previous talk showed, it was only order of a month, but this result shows that it could be delayed even longer, I think, depending on where you are.
Thanks, Jake.
Yeah.
Hussein, you are next.
Jake, again, very fascinating talk. You can see so much overlap, which I wasn't aware that you were pursuing this kind of. I was wondering why you chose to do a sharp kernel or a filter. Why not one of those nicer ones? The sharp has negative parts of it, which are ugly.
Yeah, I had kind of, like I had mentioned, been working with other members of the CPT to develop this filter or use it in a way. And my taking to it has been that it is the sharpest, right, in spectral space, in that it will pass all wavelengths greater than whatever the filter scale is. And I thought maybe by using it, I would see a sharper break in energy partitioning across scales. And I'm not specifically taking, you know, global budgets and such, and I don't know the carried through effect of permitting potentially negative EKE. But when you define, you know, just mean kinetic energy as the filtered square of the filtered velocity, I actually never compute EKE and just look at kind of how variance decreases with increasing filter scale.
You showed that cumulative energy, course, or filtered cumulative energy increases monotonically as you make your filter scale smaller. We showed in 2018 that that's not the case if you use a non-positive filtering kernel. So you get a negative spectrum. You can get a negative spectrum.
Yeah, part of this work has been, I guess I should follow up with that, but has been to kind of really compare the two filters. Like I compared this to the Gaussian and a boxcar. And I guess I should look into it a little more.
Thank you.
Great.
Can I just jump in and ask, in your opinion, you would advocate for not using such a sharp filter because of the issue of negative?
I don't know if I have time.
If you can maybe quickly, so we can move on to the last talk.
My view is Fourier world doesn't matter when you're working on Earth, because you can never do a Fourier transform. So why bother? Why don't you take a kernel that has a characteristic well-defined length, width, and take that as a scale rather than worry about Fourier? That's my
sense. Thanks.
Thank you very much. Yeah, and I think it's a very important kind of discussion we had many times during the CPT, and it's still ongoing. So definitely appreciate Hussein's kind of, you know, input and many of the great work before. Okay, I don't see anything else. So Jake, thank you very much for the great talk. And so our last speaker is going to be Yiming, who's going to talk actually about LC interaction. So we're moving now into the coupling. And yes, I see you. All right,
yeah,
that's good.
You.
And you should be able to share, hopefully.
Mm-hmm. Can you see my slide all right?
Yes, great. Go ahead.
Okay, so hi everyone. My name is Yiming. I'm a graduate student at NC State. And this is the work I have been doing with my advisor, Dr. Stu Bishop at NC State, and Drs. Frank Brand, Scott Bachman, and Carr. So here we are interested in diagnosing the global EPE budget and evaluating the importance of the mesoscale air interaction in moderating the energy conversions in the baroclinic pathway. So as we know, the eddy heat flux is one essential part in eddy energetics. So I plotted a global map here showing the meridional component of the surface eddy heat flux, which is represented by the covariance between the V anomaly and temperature anomaly. So from the basin-wide view, we can find the sign that the heat transport induced by mesoscale variability is mainly hovered in both hemispheres. But regionally, it's not surprising that the strongest eddy transport occurs along the most energetic currents in the mid-latitudes like Crucial and ACC region. However, within where we have strong zonal-like jets, we see prominent wave-like spatial patterns with positive and negative flux alternatively occurring. So this phenomenon swamps the general actual covert structure, but we can remove these signals in some way. And this is one part of this work I will talk about in detail later. Okay, so because our focus of this work is on ocean mesoscale, so we know this spatial band is critical in ocean dynamics, biogeochemistry, and the overlying atmosphere. So here are some examples to demonstrate this role. I'm not going to introduce this one by one, but one point I would like to point out is the Eddy's contribution on the ocean heat transport, which is related to our work. So this work by Volkov et al. 2008 showed the eddy transport can explain over 60% of the total heat transport variance at some latitude sections. So that means the mesoscale plays an important role in redistributing heat globally. Okay, so this diagram in McWilliams 2016 shows the ocean general pathway. So for large and mesoscale currents, the flow is largely rotational and balanced. So within this balanced regime, the instability is the driver for the variability. So we have the barotropic and baroclinic instability at the two major processes. And in this work, I will focus on the baroclinic pathway to examine the mesoscale sources and sinks of eddy potential energy. All right, so to do so, the eddy potential energy equation is one approach to get the answer. So to start with, we can make some assumptions that are typical for previous traditional theoretical studies within the QG framework to make things easier at first. So we assume the system reaches at a steady state and there is no diabatic forcing. So the advection is also neglected here by the ideal velocity. Then we get the adiabatic eddy potential energy equation as shown in the Marshall and Shields 1981. And here I would like to clarify that we only consider the thermal contribution to the ocean buoyancy field in this work. So that means we are actually using the temperature variance equation as the proxy for the EPE equation. All right, so in this simplified equation, there are three major terms. The first term denotes the mean advection of eddy potential energy. And we have the other two terms related with the horizontal and vertical eddy heat fluxes. So in Marshall and Shields' paper, the eddy heat flux was further decomposed into the rotational and divergent component. And it's shown there is a balance between the rotational flux acting on the mean thermal gradient and the mean advection. So in theory, this relation holds well only if the mean velocity is aligned with the mean temperature field in the vertical, and also the rotational flux needs to be correlated with the EPE distribution. And I think this schematic picture can demonstrate this relationships well, which shows the rotational flux, which are the arrows here, can circulate around the EPE contour. And what's more, the regional analysis based on CAS observation by Bishop et al. 2013, they further tested this relation in the Crucial extension, and it's shown that the velocity field is equivalent barotropic, and the rotational eddy heat flux can follow the temperature variance contours. All right, so based on these two conditions, the rotational flux related energy conversion then can nearly balance the mean advection of the EPE. Okay, so if we subtract this balance from the adiabatic EPE equation, there are two terms left as a 1-to-1 balance of the energy flow. So the essential of this modified equation indicates how the mesoscale draws energy, background mean potential energy, and converts it into eddy kinetic energy. So we have the first term here, which we call the baroclinic conversion, which is the transfer of energy from the mean potential to eddy potential energy. And the following process is denoted by the potential kinetic energy conversion, which is the following transfer into EKE. All right, so to isolate the two different components of the baroclinic conversions I just mentioned in last slide, a Helmholtz decomposition needs to be applied on the eddy heat flux field. And we believe the rotational flux will dominate the total field of eddy heat flux and could make the extra transport unclear. So this feature is demonstrated in the global map I have pointed out in the first slide. We have seen the wave-like feature is prevalent in the western boundary currents and ACC. And also Jane and Muratsky 2002 also gave one example showing the importance of removing the rotational component from the total flux in an idealized zonal jet with strong meanders. So in this case, they show the meandering structure actually dominates the eddy energetics. So this makes the actual dynamics unclear. And this is analogous to what occurred in the Crucial, Gulfstream, and other strong zonal jets in the nature. And on the right, I show the mathematical expression of applying this decomposition on the eddy heat flux. So essentially, we are solving the equation 3, this Poisson equation of the globe. All right, so next I show how we apply this method in extracting the global mixed layer divergent flux based on the observational data. So the mixed layer eddy heat transport is estimated at this equation. So the geostrophic velocity comes from the altimetry data, and the temperature is based on the NOAA OIST. And both of these have a quarter degree resolution, and the period we use in our analysis is from 1993 to 2017. We extract the eddy component of these variables by removing the monthly climatology, and also the H here represents the climatology of mixed layer depth from the MIMOC. Okay, so with that, we obtained the mixed layer eddy heat transport and decomposed it into two components. So this is the mixed layer eddy heat transport in total averaged over 25 years. And after the decomposition, we partitioned it into rotational flux, which contains most of the rotating structures, and another divergent flux that we think is the dynamically important components. So I also show the, sorry for that. I also show this is the zonal integral of these three components. So the total is shown on the black line, the divergent is in the red. So we can see that the divergent part can capture the most of the energy in the total flux with a small contribution from rotational components. So that suggests for the rotational flux actually doesn't contribute to the global budget, but it will affect the regional energetics. So we can zoom into one region to see more details. So here, from the perspective of the baroclinic conversion, the rotational fluxes acting on the mean thermal gradient can capture most of the wave-like structures. Here is the example for Crucial and the upstream. And the rest divergent conversions has more smoothed spatial structures and mostly conserves the original total conversions globally. However, for regional analysis, we think it's necessary to remove this pronounced rotational structure. Okay, so now we can go back to the balanced adiabatic EP equation. So from last slide, it's shown we can estimate the upper ocean baroclinic conversion, which is the first term here with the available observations. However, to estimate the other part of energy flow, which associates with the vertical flux, is not easy and restricted by the limited observations. So next, we utilize the high-res pop model to diagnose this relation. The model is forced by Charlie 55 product and has a nominal 10th degree horizontal resolution, and the data is saved at 5-day frequency. Also, a 20-year period is used in this work. So here are the two vertically integrated terms in the equation from the pop model. So with the decomposition method, we can decompose the flux on a final grade, and the divergent BC rate is shown on the left. So the conversion from the EPE to EKE is shown on the right. So from here, we can observe a strong spatial coherence between the downgradient horizontal and upgradient vertical heat flux. So this implies this relation seems to stand well from a geographic and qualitative sense. So here I also show the zonal integration. This gives a more quantitative sense of these two terms. So we see a magnitude mismatch between these two terms with a stronger conversion from mean potential energy to EPE than the following transfer into EKE. So that means the adiabatic EP equation misses some pieces of the real story, and we think the diabatic process must play a role here. Part of the EPE that would typically be available for conversions to EKE. Okay, then we can go one step further to look at the full diabatic EP budget. So besides the mean advection, the baroclinic conversion, PAC term, there are three extra terms compared with the adiabatic equation. They are eddy advection, diabatic mixing, and horizontal diffusion. So so this term I want to emphasize here is the role of mesoscale airs interaction. And this has been emerging as an important term in modulating the EPE variability in recent studies. So like MITE or 2016, they performed a regional numerical study to suggest that the mesoscale damping can destruct more than 70% of EPE through interacting with the atmosphere in the crucial region. And also, Bishop et al. 2020 showed this effect acts as a global sink of EPE based on the observations. So this plot on the left shows the covariance between the temperature anomaly and net heat flux anomaly. And we can see this sink term basically concentrates in the mid-latitude and the equatorial regions where we have strong eddy energies and energy conversions. So to close this budget, we want to answer how important this term is relative to the dominant processes globally. Okay, so here are the global budget terms. So all maps here are the vertically integrated terms from surface to peripheral. And the numbers shown on the corners are obtained with the global volume integration. So the first one shows the tendency, which is very small when taking a time average, and the direction and the rotational BC rate are spatially coherent, and we can examine this from a regional map later. And next, we have the divergent BC rates. and the PKC rate and the vertical mixing, and plus the residual is quite small. So among these, the dominant balance is shown in this red square. So the PKC term to a large extent can balance the BC divergent rate, and the diabatic mixing can moderate part of the EPE. Okay, so now we can zoom into a region to have a better idea of how each term is related with each other. So here I show the rotational BC rate can correspond with the direction of EPE from a spatial sense, and these two can qualitatively balance each other as was proposed in Marshall and Schultz's work. So a point for attention here is we also include the Eddy advection term, which we think is not negligible in the western boundary currents region. And then after extracting the divergent Eddy heat flux, we can find this downgradient flux is aligned with the vertical flux, and the corresponding conversion rates also can connect with each other spatially. Also, the vertical mixing has structure like this, but the magnitude is quite smaller in the manner of full depth integration. Okay, so as for the vertical distribution of each terms, we can find more structures and connections between each other. So the advection can compensate with the rotational conversions to a large extent, and the divergent BC rate and PKC vertically correlates in the ocean interior. And we have the mixing constraint in the upper ocean. And again, the dominant terms on the second row with diabatic process modulating the energy conversion. Besides that, a zonal integral of some of these terms are shown on the right. So as you can see, the BC rate generates large amounts of the EPE, and most of them will be transferred into EKE through the paraclinic instability, and part of those will be dissipated. All right, to summarize, so in this work, we apply the Helmholtz decomposition on the surface Eddy heat flux field from the satellite observations with the quarter degree observation and the full depth field from a 10th degree pond model. And we show the divergent Eddy flux and its related energy conversions nearly conserves the regional energetics globally, but with a clear and smooth spatial pattern. Also, the global sources and sinks of EPE was diagnosed through a temperature variance equation based on the model output. We estimated the energy conversions through the paraclinic pathway. It found the conversions from the mean potential energy to EKE is not 100% efficient with strong dissipation from the diabatic processes. And we found this effect can destruct about 40% of EPE that should be available for transferring to EKE. And the mesoscale interaction contributes to about 10% of the EP destruction. Yeah, so basically, we found the efficiency of the paraclinic instability is about 60% globally. So with this, with this conclusion, I would like to call back the original study by Might et al. 2016, where they got a way less efficient energy conversions, about 22% in the crucial extension, although they only analyzed one dynamic region. So we think the reason for this discrepancy is that they only focused on the upper 250 meters where most of the diabatic processes occur. So from this vertical structure of the dominant terms I have showed, the Eddy situation can reach to about 1 kilometer, but the mixing process barely can penetrate below 200 meters. So globally, we think the efficiency is way larger than 22%, and it's about 60% in this first top model we used. Yeah, okay, so with that, I'll be glad to take any questions.
Thank you very much. Yeah, that was a great talk, very interesting. So I can see already, yeah, Richard, I think your hand is up.
Yes, it's Justin. Yiming, I liked the talk, and I just missed the last bit in the last few slides, which was the term that was the air-sea interaction term. Did you show it explicitly, or did you put it all in with the mixing term?
Right, I put them in the mixing term from the model output. I just showed one. Again, there is only one global map from the observations here.
Okay.
Yeah.
So, well, another quick related question. That I think that's from observations. How well did the model compare with the observations for that term?
Well, I think Stu's paper talked about some comparison between the observations and, but it's a coupled model. Yeah, that is one term I should look at with the Foster model as well. Okay. But I think, yeah, it shouldn't be a very large discrepancy between the observation and the Foster model.
Okay, yeah. I'm a co-author of that paper, so I should know. All right. Thank you, Yiming.
Yeah, thank you.
Thanks, Justin. I don't see any other question. I'll ask a quick one, if that's okay. So it was, yeah, very interesting, really fascinating work. So for the model, you're using 5 days output, right?
Right.
For the diagnostics. Do you think it matters if you use higher frequency? Do you think it would actually kind of, enhance the signal that you would get?
Yeah, that's
I know it's hard to know because it's a lot of data as well that don't exist. But if you have a feel, I'd be curious to hear.
Yeah, that's a very good question. So actually, we do miss some part of reliability below 5 day, but that part is we think is smaller than the dominant processes. So if we just use the 5 day outputs, the residual is about like less than 0.1 terawatts globally. So this number is quite weaker than the energy conversions and the mixing terms we showed. Yeah, but yes, you are right. If you use a high frequency data, I think it will be better. Okay,
Thanks. Okay, so we had one last question from Malta.
Hey, yeah, interesting talk. Sorry, this might be a really stupid question. In parts because I must admit I had to step away for a little during the talk, but I'm wondering how you separate between the vertical mixing versus surface fluxes, because kind of as you're marking it here, it's a heat flux convergence term that enters in the budget. Not a flux, the surface term is a flux. So does that make sense?
Well, yeah, so for the budget result I showed here, we didn't partition the ARC term and with the vertical mixing, but with the model data, we can absolutely partition these two parts by into like ARC interactions contribution, this diffusive term and also the KPP term. Yeah, but for just based on this new paper, the ARC interaction contribution from the CESM model is about the 0.1 terawatts. So I just use this to quantify this term in our analysis. But we can definitely look into all these different contributions from the vertical mixing terms I highlighted here, for sure.
Okay, I think I'll just have to read the paper. Just follow quite the equation right now. Thanks.
Wonderful. Well, thank you very much, Yiming, for your talk. And so before we close and pass it on back to Frank, just wanted to thank all the speakers again for phenomenal talks and all the participants, especially during the interesting Zoom craziness. That was the first. I mean, I had many Zoom interesting things happening. That was one of the first. So that was definitely interesting. But there's a lot of discussions. There's still actually a bunch of comments in the chat. So people, read them or go through it. And, there'll be, I believe, again, the recording will be up by tomorrow. So again, reach out to speakers if you have questions. And again, I want to thank, the Ocean Modeling Working Group for, inviting us with the CPT to jointly host this meeting. It's been phenomenal. And there are more talks this afternoon at 1 Mountain Time. And so I'll pass it on to Frank if there are any more
just
items
close it
on the agenda.
out. Just let people know that this meeting room will stay open through the break. So if you'd like to continue discussions or socialize or whatever, feel free. I want to give Elizabeth a break. She offered to set up breakout rooms, but I think we should tell Elizabeth to take a break. She's been doing a phenomenal job and got us through that meltdown. So yeah, so we'll see people back at 1 o'clock.
Hey, Elizabeth, are you in here?
I have to step out at 2 o'clock, Frank. I have an SSC meeting. So
SSC. Man, don't they know we're busy right now?
no, I had to organize it around this time, unfortunately, because we need to run the evaluation teams, the names by the SSC before we discuss them on Monday at the atmospheric model working group meeting for the DICOR evaluation. So that was
What evaluate? I thought you were talking about like the SVT or something. What is the?
Oh, no,
What
that's
does the SSC have to do with that?
Yeah, that's separate.
Okay. I'll make a quick announcement before we sit. What do you know the dates of the annual workshop off the top of your head?
Yeah,
June,
I can just a second. So it'll be.
And in the tutorial.
Yeah, I can give you both of them.
Or maybe just the deadline to
the
apply for
workshop is the week of June 14th.
Okay. When do you, are the applications for the tutorial
We
open
have
yet?
a tutorial is about to be opened. I think Elizabeth has the latest information, or Gustavo is the chair, actually. So.
Hey, Gökhan, the tutorial application is open.
Open. Okay, so they are open
Okay.
apparently.
Okay, and that's in early August, usually first week of August, something like that.
It is. Yeah, for some reason it's not showing up on this. Oh, because I'm up. Why isn't it showing up?
Elizabeth got it. 9th to the 13th.
Okay.
The tutorial application is going to close March 1st.
Okay. Thanks, Ryan.
Gökhan, was there a page you were on that the tutorial information was missing from, or?
No, it's my own calendar.
Oh, okay, okay.
It has nothing to do with.
Yeah, I can't really help you with that one.
Yeah, I thought I put it in, but it's missing for some reason. I need to put it in.
Okay, cool.
Elizabeth, maybe you could just put the CESM events webpage link in the chat, and I'll just refer people to that. That'll be the place to watch for things.
Sure.
I don't know whether it's worth mentioning, Frank. We are encouraging applications, particularly from minority serving institutions. So if anybody knows of any interested people and all that stuff, if they can pass along the information, we'll have a bigger outreach effort, especially after COVID, but we are just trying to sort of word of mouth as advertisements at this point.
People are starting to arrive. Give it a minute here.
Frank, will there be any other opportunities for discussion in this meeting? In particular, I note that adjourning at 3:30, between now and the time we adjourn at 3:30, we don't, but would it be worthwhile having some discussion after that?
Yeah, we can stay on for people who have the fortitude, and I was thinking about that.
Okay.
Do you have some specific items you want to bring up?
Well, the one that seems to have bubbled up, and maybe this is kind of more of an inside thing. There was a proposal in the chat about a coupled ice ocean around Greenland that might be worth discussing, or I mean, it's up to you.
No, I think that's certainly one option. The other was that we kind of had to cut our discussion a little bit short yesterday, and you and others sort of responded in the chat afterwards about prioritizing our next steps. And I have a charge from GoCon to provide him with the outcome of our meeting on that topic. So I would welcome any further discussion on that.
Okay. So I'm happy to stick around after the end of it.
Okay, I'll announce here. Well, we're at 1 o'clock anyway, so let me just say a couple of words before we launch into our talks. First, I'd like to extend my thanks to all the CPT folks and the folks from the other MOM6 modeling efforts for participating. And CESM Ocean Model Working Group's remit is to develop and maintain the ocean model component for the broader CESM community. And I think a very important part of that is for us to stay engaged with the people doing fundamental research on ocean processes. I think some of the most important advances we've made in the last 15 years in the CESM ocean model have come from CPT. So I think this is a really critical thing for us to for us as CESM to stay involved in, and also I think for our community that I think everyone, whenever you have a chance to talk to program managers, just tell them how important these CPTs are for our community. Yeah, and then just administrative things. Let people know, especially those who haven't traditionally been involved in CESM. We hope that you will continue to stay engaged with us, and our annual workshop will be the week of June 14th. There are much shorter working group sessions, typically a half a day there, but you'll get a broader overview of basically the entire project. There are plenary sessions and then breakouts for working groups and some cross working group sessions. So that's all being planned right now. And then also, if you have students or postdocs who want to begin using CESM, our annual tutorial will run the week of August 9th to the 13th. The registration for that is open now through the 1st of March. Both the annual meeting and the tutorial will be 100% virtual again this summer. Yeah, and just as probably most people just heard, I think, although we don't have a discussion scheduled at 3:30 Mountain, we'll stay on, and there are a couple of items that have bubbled up in the chat and at various times that we can sort of flesh out over the remaining time that people have the endurance to stick with it. So with that, I think we'll start up the talks, and Wenda Zhang, are you ready?
Yeah.
There you go. Looks good.
Okay, great. Thanks. So good afternoon, everyone. I'm Wenda Zhang. The topic of my talk is vertical structure of tracer diffusivity in an idealized basin circulation model. This work is done with my advisor, Christopher Wolf. So the mesh-scale eddies play an important role in the tracer transport and mixing, and in the climate models, the tracer flux due to the mesh-scale eddies is typically parameterized by the diffusivity. And in the oceans, observational studies have been trying to estimate the diffusivity in the global ocean. Some may be based on the tracer method, which is to evaluate tracers using the surface velocity field from satellite altimetry. And some may use the Lagrangian method by tracking the surface drifters over the ocean, and some of many other methods as well. But a common feature of these global estimations is they only estimate the diffusivity at the surface, while the estimate for the subsurface diffusivity or the vertical structure of the diffusivity is still an open question. And then this recent study by Groiskamp et al., they made a step further. They combined the mean flow suppression theory with vertical mode theory to reconstruct the vertical structure of the diffusivity. So the most novel part in this, in their method, is they applied a vertical structure function for a vertical mode, which they called the first surface mode. So with this, they can reconstruct the vertical structure of the eddy kinetic energy, and combining with mixing length, which they assume it to be the Rossby deformation radius of the vertical mode, and a mean flow suppression factor. With all these, they were able to reconstruct the vertical structure of the diffusivity, and they showed that this compared well with two existing observations. One is in the North Atlantic, one is in the Southern Ocean. This red curve is their theory, and these black dots are the observations. And also with this, they were able to estimate the diffusivity in global ocean at 4 depths. However, to further apply such kind of theory, several assumptions behind it still need to be verified. The first one is, in this theory, they simply assumed that without the mean flow suppression factor, the mixing length would be a constant over depth. How well would such theory apply to the full water column? That's the first question. The second one is, they assumed the vertical structure of EKE can be reconstructed by such a single vertical mode. How well would this be applied to broader flow regime? That's the second question. And the third one is they simply estimate the diffusivity as a scalar, but we know the full diffusivity is actually a tensor. So how would such a theory apply to the other components of the diffusivity tensor? That's the third question. So in this study, we explored these 3 questions in an idealized numerical model. This model is an idealized configuration of MIT GCM. It's in a double hemisphere domain. So and it's on a beta plane with flat bottom. In the southernmost eighth of the domain, there is a channel which is like the Southern Ocean. This figure shows the mean SSH field in this model. So we can see there's subtropical gyre in both hemispheres, and there's a subpolar gyre in the northern hemisphere, and the circumpolar current in the channel, which is like the ECC. And in the vertical, we have 20 levels. This figure shows a snapshot for the eddy field. The color is the vorticity, the shading is the SSH. So this model resolves the mesh-scale eddies in nearly all the latitudes. Then to diagnose the diffusivity tensor in this model, we applied a multiple tracer inversion method by this Bachmann et al. Study. we advected a total of 27 passive tracers in the model. They were divided into 3 groups. Each group contained 9 tracers with these 9 different initial distributions. And each group of tracers is relaxed to the initial condition with a different relaxation timescale from 1 year to 6 years. And with all these tracers, we can solve for this diffusivity tensor in a least square sense, like this form. And before the calculation, we coarsened the mean field into 152 kilometer grids. So to test how well this diagnosed diffusivity performs, we used it to reconstruct the buoyancy flux as a test. The buoyancy is not used in the tracer inversion. So here we use the diffusivity tensor to reconstruct the heat flux and compare that to the diagnosed heat flux. And the difference is normalized by the diagnosed heat flux. This is the relative error. And this figure shows the relative error with respect to the different relaxation timescale. Each timescale contains 9 tracers, and the last one simply used all the 27 tracers. So we can see that the error is generally small, and it's not very sensitive to the relaxation timescale. And in the later results, we simply used all the 27 tracers for calculation. This is an example of the reconstructed meridional heat flux, and it compares very well with the diagnosed heat flux. So the reconstruction is good enough. Then let's look at the diffusivities. In this study, we are interested in the diffusion of the tracer. So we would focus on the symmetric part of the diffusivity tensor. The symmetric tensor can be decomposed into 3 eigenvalues with their corresponding eigenvectors. Here shows the distribution of the 3 eigenvalues at a certain depth. So the black arrows shows the horizontal directions of the eigenvectors. So the first 2 eigenvalues are mostly horizontal or mostly along the isopycnal. And the third one is mostly vertical, but its value is much smaller than the first 2. And in this study, we mainly focus on these 2 horizontal eigenvalues. The first one is mostly zonal, or mostly along the mean current. The second one is mostly meridional. We are interested in the vertical structure of these 2. So here we picked 4 windows to look at the vertical structure. One is in the circumpolar current, one is in the subtropical gyre, one is in the western boundary current extension, and the last one is in the transition between the subtropical and subpolar gyres. So we average the diffusivity in each window, and here are the vertical structures of these 2 diffusivities. So we can see the first eigenvalue is it's several times larger than the second eigenvalue. So which means the mixing is anisotropic, and especially in the upper levels. And these 2 have very different vertical structures. So what determines these different vertical structures? Firstly, let's look at detail about the first eigenvalue. We called it the major diffusivity. As we saw before, it almost decreases monotonically with depth. And we found that it follows the variation of the RMS eddy velocity pretty well. So that suggests this diffusivity might simply follow a mixing length theory. So here, this RMS eddy velocity is diagnosed from the model, and this mixing length, we assumed it to be constant over depth. So it's gotten from fitting, and the fitting result is shown by this dashed line. So we can see generally the mixing length theory does a good job in capturing the vertical structure of this major diffusivity, especially good in this channel. Well, the problem is in these three regions, this mixing length theory tends to overestimate the diffusivity in the deep levels. This dashed line is the scale height of stratification. So it's like the bottom of the thermocline. So above that, assuming a constant mixing length works just fine. Below that, it seems that assuming a constant mixing length might overestimate the diffusivity, so that the mixing length might not be simply a constant there. We haven't figured out why. We would appreciate if any of you have suggestions on this. Then let's look at the second eigenvalue, which we called the minor diffusivity. So the most obvious feature for it is it tends to have a subsurface maximum. And we found that this is consistent with the mean flow suppression theory proposed by these previous studies. So this theory describes the diffusivity using this formula. So except simple mixing length theory, and the diffusivity is also modulated by the eddy propagation relative to the mean flow. So this U bar is the mean flow, which is a function of depth. CW is the eddy feed speed calculated by this formula. This mixing length is it's simply borrowed from the major diffusivity fitting. There are two unknown parameters here. One is this mixing efficiency. The other is this decorrelation timescale. We simply got them by fitting. So the dashed line is the fitting result. So still, generally, this theory does a good job in capturing the vertical variation of the minor diffusivity. The problem of it is the same as the major diffusivity. So in these three regions, it might overestimate the diffusivity in the deep levels. So still, this suggests that using a constant mixing length over depth in the denumerator here might not be an ideal choice. But in this study, we are interested in trying to reconstruct the vertical structure of diffusivity. So we still assume the mixing length as a constant over depth. So if all these parameters are constant, only the IMS eddy velocity and the mean flow are a function of depth. This mean flow, we assume it can be resolved by the coarse resolution models. So if we can reconstruct a vertical structure for this IMS eddy velocity, we would be able to reconstruct the vertical structure for this diffusivity. So how can we reconstruct the vertical structure of the IMS eddy velocity or the EKE? This GROISCAM study, they applied a vertical mode called the surface mode to reconstruct the EKE structure. This mode is solved from this vertical structure function. This is derived from the linear QG PV equation. The traditional solution for this is to assume the vertical velocity to be 0 at both top and bottom. But this surface mode theory, recently promoted by these studies, it instead of assuming vertical velocity to be 0 at bottom, it assumes the horizontal velocity to be 0 at bottom. So solving this, you can get a series of the surface modes. And then this study showed that the first surface mode tends to explain most of the variance of the current meter observations. So in this previous study, they used this single first surface mode to reconstruct the vertical structure of EKE. In this study, we also solved this equation numerically. So here are the first surface modes in these four regions. But a problem of this solution is they assume the d phi dz to be 0 at the surface, which means they assume no buoyancy anomaly at the surface. However, from the SST observations, we know that the eddies tend to have strong buoyancy anomaly at the surface, and that might make a big difference. So To account for that, we seek another different solutions, which is the SQG solution. The previous studies have found that the eddy flow can be decomposed into two solutions. One is the interior solution, which assumes zero buoyancy anomaly at the boundaries, which is what we saw before. The other solution is the surface solution. Instead, it assumes the interior PV to be zero. So the flow is mainly driven by the surface buoyancy anomaly, and it is described by the SQG dynamics. So in this study, we solved for this SQG solution based on this interior PV equation, and it's solved in Fourier space. Here we simply assume the SSH is dominated by this surface solution. So the surface spectrum is simply from the SSH. And we also assume the buoyancy vanishes at the bottom. So here shows the Eddy energy spectrum from the SSH fields in these four regions. From the surface spectrum, we can solve this equation numerically in depth to get the spectrum at each level. And then we can reconstruct the EKE. So with the SQG method, the spatial mean EKE is from the spectrum at each depth level. While for this first surface mode, the EKE is estimated as the surface EKE times the square of this vertical structure function. These dashed lines in the figure shows the reconstructed EKE by these two methods. The blue line is the diagnosed EKE. So we can see for the SQG solution, except in the channel, it does a pretty good job in capturing the vertical EKE profile, especially in the upper levels. While for this surface mode, there are two possible shortcomings. The first one is it's zero at the bottom by its definition, but we can see in some regions like these two, the eddy flow doesn't really go to zero in the deep levels. So this can be a big deficit. And the second one is at the surface, because it assumes zero buoyancy anomaly, so it's kind of flattened at the surface, while the real EKE simply decreases nearly exponentially over depth. And that is better described by the SQG solution. So with these two EKE profiles, we can fit them to the diffusivity to see how would they reconstruct the diffusivity. So firstly, let's look at the major diffusivity. So here we applied these two reconstructed EKE from these two methods to this mixing length theory. The fitting curves are shown by these two dashed lines. So for this SQG reconstruction, except in the channel, it's just like the fitting result using diagnosed EKE. While for this surface mode reconstruction, so in the strong current regions, again, we can see it might underestimate the diffusivity in the deep levels, because the diffusivity there is not exactly zero in the deep levels. But it's not bad in these two gyre regions where the diffusivity is close to zero at the deep levels, but it can have bias in the upper levels. Then let's look at the minor diffusivity. So again, we fit these two reconstructed EKE to the mean flow suppression theory, and the two dashed lines are the fitting results. So again, the SQG method, a reconstruction looks just like the fitting result using diagnosed EKE. Surprisingly, it's even better in the channel, although it doesn't reconstruct EKE better there, but it's a perfect fit for the diffusivity, which is a little strange. For the first surface mode, like the major diffusivity, so it can underestimate the diffusivity in the deep levels in these strong current regions. But it's tend to be fine in these dry regions where the diffusivity is close to 0 at the bottom.
About 2 minutes, Wenda.
Okay. Oh yeah. So this is the summary. So in this study, we found the mixing length theory, assuming a constant mixing length over depth, works fine for the major diffusivity, but it's mostly fine in the upper levels, but it can overestimate the diffusivity at the deep levels. The minor diffusivity is like that, except it's modulated by the mean flow suppression. And we found for both two diffusivities, the EKE plays an important role in their vertical structure. And we found the vertical structure of EKE can be better reconstructed by the SQG method than the first surface mode. When it comes to the reconstruction for diffusivities, the SQG method is like the mixing length theory. So it works well in the upper levels, but tend to overestimate the diffusivity in deep levels. While for this surface mode, it might be fine in the gyre regions where the diffusivity is close to 0 at the bottom, but it can underestimate the diffusivity in the other regions. So we need to acknowledge that in our model, we have a flat bottom. So, but this surface mode theory studies have shown that it's more prevalent on the rough bottom. So we are planning to add topography to our model to see how that affects the vertical structure. And the second question is for the mixing length and decorrelation timescale, we simply got them by fitting. If we want to apply this to the observations, we need a good estimate of them. And that's still an open question. And that's all. And thank you for listening. And I'm glad to take questions.
Thanks, Wenda. Questions? Malta.
Hi, thanks. Interesting talk.
Thanks.
I have one question. The mixing length and decorrelation time scale, like a sort of a maybe naive argument, but not crazy, in my opinion, my experience, is that the two should be related via the eddy energy itself, via the AKE itself. Have you tried that? Does it work? I mean, I guess it would change the story a bit because then it would have vertical structure too.
Yeah, so yeah, like what you said, if you show, if you assume the decorrelation time scale to be equals to like IMS velocity, to be equals to mixing length over the IMS eddy velocity, that can be an approximation. So that in that case, it will have a vertical structure. And we found that doesn't work well. So it's better to assume it as a constant over depth. So I think that might be good.
Well, more tunable parameters. It's good to fit it.
Yeah.
Thanks.
Thank you for your questions.
Thanks.
Okay, Bob.
Thanks. I really like the talk. It's a nice exploration of different theories. But one question is, why do you need to choose one? And thinking, for instance, about the surface mode, the complement to the surface mode, and this is going back to Joe Lacase's work in the 1990s and further, there's a bottom trapped mode that is the complement in the case of rough topography, which isn't really usually thought of as kind of an eddy stirring, but more of a wave-like mode. But if you start to introduce things like bottom drag to break geostrophy, then that bottom trap mode can also act to drive irreversible mixing. And it seems to me like you have a lot of the ingredients here if you allow yourself to take combinations of these to do better than any one by itself.
Oh. So do you think it's necessary that we have a topography so that we can include all those bottom trapped waves effects?
Well, that's something that would come in if you put in topography, is you would get topographic philosophy waves that are viscously damped, and that could also drive mixing. And you can have leakage of energy between the different modes. They're not pure modes depending on the topography.
Yeah, that's correct.
but similarly, the surface QG modes and the surface mode, I don't know why you couldn't have things that are mixtures of them that be able to do. I mean, you're basically at that point opening up the possibility of combining them, and you're giving yourselves more degrees of freedom, and you can't possibly do worse than picking one or the other end limit. But it may be worth kind of exploring whether combinations of these different modes might not do an even better job.
Yeah, that's a very good idea. Yeah, actually, yeah, some studies have been trying to like combine these SQG solutions, interior modes. Yeah, it's possible to do. We haven't tried that because simply we just found that like in these regions, a single SQG that just does well. So, but yeah, it's possible to combine them to see if it's better. So, yeah.
Okay, Dhruv, fairly quick.
Hey, it's great work. I had a question related to the antisymmetric part of the tensor. So most of the work that you have shown has to do with the eigenvalues of the symmetric part. I'm just wondering if you have thought about what the role of the antisymmetric part is and kind of like what the scalings might be for that.
That's a very good question. We haven't tried to look at that. So it might be, it might be different. For example, like this mean flow suppression theory, maybe this won't simply apply to the advective part of the tracer, the tensor. So yeah, so it might be different. So yeah, we can look at that in the future.
Okay,
thanks.
Let's move on. Next up, we have Hussam Yassin.
Yeah, hi everyone. Can you hear me?
Yep.
Okay, good. Great. Okay, so I'm going to talk about some work I've done with Steve Griffiths on discrete normal modes in quasi-geostrophic theory. It's based on these two manuscripts, which are available on arXiv right now. Sorry. Okay, so just a quick review. So how do you get the normal modes and what are they? So you usually get normal modes by considering a perturbation to a background state with no vertical shear for this presentation. And we ignore background shear just so the normal modes are discrete. And so if you do this, you get an eigenvalue problem in some space F. And then the normal modes are the resulting solutions of this eigenvalue problem. They're the vertical structures of the waves resulting from this problem. And they form a basis of F. So the simplest example here is a two-layer quasi-geostrophic fluid, for instance. The background space is, it's a two-dimensional space, right? You have two layers, and then you get two modes, right? You get a barotropic mode, and you get a baroclinic mode, right? And these two modes form a basis of this two-dimensional space, right? You can represent every possible QG state in this two-layer fluid as a sum of these two modes. Right, and so it gets more complicated once you have continuous stratification and it becomes an infinite dimensional problem, right? And so these normal modes are they're useful. Oceanographers have found them useful for a variety of purposes. You have like turbulence arguments like in Charney 1971 or Smith and Vallis 2001. They're used in observations and as in Wunsch and Lapierre, for instance. And so I'm going to focus on the slide on a specific question. So what mode does the altimeter signal reflect, right? And so Wunsch looked at this question in 1997, and he partitioned the kinetic energy from moors in the ocean. And he found that most energy is found in the 0th and 1st baroclinic mode. Then he goes on to conclude that the altimeter signal corresponds to the 1st mode, which in turn corresponds to thermocline motion, right? Then later on, Lapierre looked at this question in 2009, and he noted that the baroclinic modes all satisfy the same upper boundary condition of vanishing vertical shear, right? And this means that the baroclinic modes should be unable to represent surface buoyancy. And so he said the baroclinic modes are actually incomplete. And then he goes on to say that the altimeter signal actually should reflect surface trapped SQG motion instead, right? And so this talk, I'm going to basically look at what completeness means, and then basically show you why the baroclinic modes are in fact incomplete and how you can get bases that are actually complete for continuously stratified QG theory. So the first step is to actually define what space we're actually working with, right? Because completeness turns out to be a relative property. And so the way you do this is by considering PV, because given the PV, you can always reconstruct the whatever quasi-geostrophic state you're talking about. So you have the PV has there are like two types of PV, right? There's the volume PV, which is this Q, which consists of the Coriolis parameter, relative vorticity, and vertical stretching, right? And this volume PV is a function of space of 3 dimensions, right? So the Q is spread out through the volume D, right? But you also have these two other types of PV, which are the surface PVs, right? I'm going to denote them by R1 and R2, right? And the surface PVs, they have a contribution due to topography, and then they have a contribution due to the vertical shear or the buoyancy gradient, essentially. And so the R1 and R2 are basically defined only on the upper and lower boundaries, right? They're functions of 2 spatial dimensions, right? And then if you want to get the total PV in a volume, you'd have to integrate Q over the volume, and then R1 and R2 over the areas, and then you take the sum. Okay, so then the quasi-geostrophic phase space is basically, you first define the PV distribution as in Brotherton, right? You have this PV distribution, which is a sum of the volume PV and the surface PVs multiplied by a delta function, right? And then the PV phase, the QG phase space is essentially the space of all such PV distributions, right? So this phase space, to specify a point in this phase space, you need to tell me what the volume PV is Q, and then you need to tell me what the surface PVs are R1 and R2, right? It's not enough to specify the volume PV, for instance. I need all 3 functions, right? And then the stream function perspective basically is the space of all stream functions induced by these PV distributions. Okay, and so we want to see what this means for the vertical structure, right? So we take, just for simplicity, we consider a doubly periodic domain, and then we assume solutions that have this sinusoidal structure in the horizontal, right? So then the PV distribution now takes this form. Now it's a sum of a function of Z, right? This is the vertical structure of the volume PV, and then 2 numbers, right? R1 and R2, which tell you the surface PV at the upper and lower boundaries, right? So you have to say this carefully, right? So to specify the vertical structure of a quasi-geostrophic state, you need to know what the vertical structure of the volume PV is, and the vertical structure of the volume PV is an element of L2, where L2 is a space of square integrable functions, right? And then you need to also know what R1 and R2 are. And R1 and R2 are just numbers, right? They depend on time, but they don't depend on space, right? So the space of all possible vertical structures in QG is L2 plus C, right? You need to know a function, which is a vertical structure of the PV, and then you need to know the surface PVs on the upper and lower boundary, right? It's not enough just to specify Q, for instance, right? So the space is L2 plus C. Okay, so why are the baroclinic modes incomplete? Okay, so just to review the baroclinic modes very quickly, they're just the vertical structures of Rosby waves in a quiescent ocean with no topography. And you can express the baroclinic modes either in terms of a stream function or the vertical velocity. So on this slide, I'm showing the stream function formulation. All the baroclinic modes, as I've said before, satisfy the same boundary condition, right? They have a vanishing vertical, it's basically a 0 vertical velocity boundary condition. And then here are the first 6 modes. Everyone's familiar with this. This is in constant stratification. And you can see that the 0th mode has 0 internal zeros, the first mode has 1 internal zeros, and so on. And so you can also write the baroclinic modes in terms of the vertical velocity, right? And yeah, and so they all satisfy this W equals 0 boundary condition. Okay, and so a standard result is that the modes, the stream function modes and the vertical velocity modes, they form an orthonormal basis of L2, right? But we've already seen that the space of all QG vertical structures is actually this L2 plus C, right? There are two more dimensions in the space, right? So we're really missing 2 degrees of freedom. The baroclinic modes are missing 2 degrees of freedom, and I'll show exactly what those 2 degrees of freedom are in a few slides. Okay, so in linear theory, the baroclinic modes are the vertical structure of Rossby waves, and in linear theory, you can write down this general Rossby wave solution, right? And only in linear theory do the baroclinic modes have an actual physical meaning, right? Because in linear theory, you have each term in the sum has a vertical structure multiplied by this sinusoidal time dependence. So if you have if you have a barotropic component in this sum, that will tell you that you have a barotropic Rossby wave that you have some coherent barotropic motion in this situation, right? Yeah, but this only applies if you're in a linear ocean with no buoyancy gradients at the boundaries and no topography, right? In general, we're not really talking about waves. We're talking about eddies, right? And so we're not really the modes. When we expand things in terms of modes, we're just using them as a mathematical basis, right? They're no longer waves, right? So we can try to use the baroclinic modes either in their stream function formulation or their vertical velocity formulation as a basis for QG theory. So let's test this out. So let's say we're given a QG state with the vertical structure is capital psi, and the vertical structure is capital W. Then we define these 2 expansions in terms of the baroclinic modes. So psi exp is the expansion of capital psi in terms of the stream function baroclinic modes, and W exp is the expansion of capital W in terms of the vertical velocity baroclinic modes, right? And then we ask the question: when is the stream when are these two when is the original function equal to its expansion? And similarly with the vertical velocity. And so this is what you get, for instance. So this is a busy slide, so I'll go through it slowly. So here in panel A, here I'm showing this function f, and below it in panel E, I'm showing this derivative, df dz, right? So first I'm going to pretend this f is some, it's a vertical velocity, right? And I'm going to expand it in terms of the vertical velocity baroclinic modes, and that's what I show in B, right? And you see that the expansion doesn't converge to the original function, right? And that's because all the vertical velocity baroclinic modes have to vanish at both boundaries, right? And if we take the derivative of this expansion, it also doesn't converge to the derivative of f, right? Because again, the original expansion didn't converge. But if we now let's suppose now that f is a stream function, right? It's some stream function, right? So we try to expand it in terms of the vertical velocity, in terms of the baroclinic modes, in terms of the stream function baroclinic modes, right? And what you get, and you find that actually it does converge everywhere to the original function. But if you take the derivative of this series, it actually does not converge at the boundaries, right? It'll converge everywhere else, but not the boundaries. And so this leads us to the missing degrees of freedom in this expansion. So if we're given an arbitrary vertical structure, capital psi, you can, and you expand it in terms of the baroclinic modes, you can differentiate the series in the interior of the interval, and then you'll recover the PV implied by this vertical structure. You'll recover the volume PV, right? But we can't differentiate the series at the boundaries, right? So because we can't differentiate the series at the boundaries, we've actually lost the surface PVs, R1 and R2 in the projection process, right? So because the baroclinic modes aren't complete in this larger space of QG vertical structures, when you project a vertical structure onto the baroclinic modes, you actually lose information. Okay, and so now that we've seen that the baroclinic modes are not complete, so how do we get complete bases for QG theory? And then you do this basically by including a restoring force in the eigenvalue problem at the upper and lower boundaries as well, right? So when you do this, you're actually activating the SQG dynamics at the upper and lower boundaries, right? And so one way to do this is by adding a buoyancy gradient or some topographic slope at the boundaries, and then you get what I'm calling here the generalized Rhines modes, right? Because if you if you ignore one boundary, you essentially recover the Rhine's problem. And so what happens now is you get this this eigenvalue problem where the eigenvalue also shows up in the boundary conditions, right? And this tells you that this eigenvalue problem is an eigenvalue problem in the larger space L2 plus C2, right? And so this eigenvalue problem, in this eigenvalue problem, you have these parameters gamma I, which basically are the ratio of the buoyancy gradient or the topographic gradient at the boundary to beta. And they have some angular dependence as well. And so what do they look like? Here are some examples. So for this particular example I'm showing, you see that if, for example, you put the parameter theta to 180 degrees in the definition of the gammas, then you get something that looks like the baroclinic modes, although they're not baroclinic modes because the vertical derivative doesn't go to 0 at the boundaries. But otherwise they look like the baroclinic modes. The nth mode has n internal zeros. But at some other angle, for instance, now you see that you have 2 modes with no internal zeros, not 1, right? And then if you go in this third case, for instance, you see that the 0th mode has the 1 internal zero, then the next mode has no internal zeros, and the next mode also has no internal zeros, and the next mode again has 1 internal zero, right? So so they have some different properties from the usual baroclinic modes. And so so these generalized modes, they actually form a basis of this larger space L2 plus C. And what this means in practice is that given some arbitrary vertical structure, we can expand this vertical structure in terms of nodes, and then this expansion will converge everywhere to the original function, and then we can take the derivative of this function everywhere. So we can take the derivative of the series everywhere, and it'll also converge the derivative of the original function. So the baroclinic modes did not satisfy the second property, right? And so just this, you've already seen the middle part of this plot. So I'm going to try expanding this function f in terms of the generalized modes, and then it converges just like the baroclinic modes. But now if I take the derivative of this expansion, you see that the derivative of the expansion also converges everywhere, right? And so you can write down. So again, so you can given this series expansion, you can now recover the volume PV, and then you can also recover the surface PVs as well. And this lets you write down, this lets you expand the PV distribution in terms of these modes as well, which isn't possible using the baroclinic modes. And finally, I just want to comment that the baroclinic modes can be misleading, I guess, if not used properly. So suppose we have a realistic ocean with strong surface QG dynamics and weak interior dynamics. So we have a large surface PV R2 at the upper surface, and then we have a small Q, for instance, right? Then we, given some vertical structure in this ocean, if we expand it in terms of baroclinic modes, that might lead you to think that, for instance, this motion is due to the volume PVQ, whereas in this case, it will actually be all due to the surface PV R2. So to summarize, the baroclinic modes are incomplete, and information is lost in the projection process as a result of this incompleteness. There are infinitely many complete modes in QG theory, and there's no real physical reason to prefer one set over another. And by infinitely many complete modes, so I showed how the modes depend on the angle, but you don't really need to keep the angular dependence. You can choose a single angle, and that will give you a complete set of modes. And so you get infinitely many, essentially. Finally, so in a nonlinear ocean, I don't think modal decomposition provide really any additional physical insight. And as I showed in the last slide, they can actually be misleading. And the question I posed at the beginning of the presentation of what mode the altimeter signal reflects is actually an ill-posed question, right? Because this question doesn't really have a unique answer. There is no unique decomposition into normal modes in nonlinear theory. And this is the end of my talk. Thank you.
Thank you. Questions for Hussam? Dhruv.
Hi, that was a great talk. I was kind of looking at this and thinking about the talks that went earlier in the morning. And Hussein made one comment, and he said that we shouldn't be using Fourier basis when we are thinking about the horizontal flows. And now you're kind of suggesting that the vertical modes might be misleading too. So do you have some sort of ideas about like what should we do if they're misleading?
I think just recognizing the fact that they are misleading and that they're not unique or special. I don't have any. I mean, I'm just exploring the properties of the various nodes that you can use, for instance. But yeah, I don't know.
Okay, thanks. Great work.
Hey, Schaefer.
Just to reply to your very last claim about what mode the altimeter sees, one metric was simply, yes, there's many possible bases. One way you might assess it is the same way one would take, deal with EOFs. And I mean, which one captures the most of the energy with the least number of modes, right? That's a reasonable approach.
Yeah, exactly. So, but then you're basically choosing the free parameters using observations at that point, right?
Fair enough. It's a free parameter, right?
Yeah,
the point is to tune it to be appropriate to the situation, the particular flow at hand, right?
Right. No, I agree. I guess my last point was basically it's about the original baroclinic modes, I guess, or
sure.
I don't know. Yeah. Okay. But I got what you mean. Yeah.
And I know I owe you a reply about your papers, but I have to ask, since you've given this talk, that there's this other set of modes that, the Smith and Vanessa 2013, which is almost identical to this. There's one free parameter.
Yeah, they're identical. Exactly.
Oh, they are.
They are identical. Yeah. So So they end up. So yeah. So the manuscript basically is building on top of that work. It ends up being a special case.
Okay. Thank you.
Yeah. So everything I've said here applies to the Smith and Vanessa modes as well.
Okay. Well, thanks.
Okay, Hussein.
Hey, Hussam, great to see you, first of all. Thanks for the talk. I totally agree with what you're saying. I would just be maybe more less harsh about saying that model decompositions do not provide any additional physical insight or be misleading, because think of Fourier series or Fourier modes. Yes, the system, a wave equation, they are the eigenmodes for the wave equation, for example. We still use them for turbulence and highly nonlinear system. They do provide us some way to an orthogonal basis. So they can be useful. It's just with caution, rather attribute more physical meaning to them than what they deserve, I suppose.
Yeah, I agree with that for sure. Yeah.
Okay. I don't see any further questions, so thanks again. Can we stop sharing, Hussam? Oh, Steve had a question. Go ahead, Steve.
Great talk, Hussam. The talk that we just had a minute ago before you, did you see that talk? And if you do you think that the discussion, the modal decomposition that you're providing is basically moving in the direction that Hallberg was suggesting, to combine the surface modes with the interior baroclinic modes for doing the stuff that the tracer fitting that this talk before was? Did you see the talk?
Yeah, I saw the talk. Again, there are free parameters in these modes, right? So you'd have to determine what the free parameters are, right? And by choosing the right free parameters, you'd be including the surface degrees of freedom, I guess.
Mm-hmm.
But I don't know how you'd have to use observations or models to determine the free parameters.
Okay, I think we need to move on. Abigail, you're up next. Hussam, if you could stop sharing.
Yeah, hold it here.
Yeah, thanks.
Great, is this coming up?
Yep, great.
All right, so hello everyone. My name is Abigail. I'm a PhD student working with Baylor Fox Kemper at Brown University. Today I'm going to talk about some recent work we have on modifying the mixed layer Eddy's parameterization, also known as the mesoscale parameterization, and doing so by determining frontal width by boundary layer turbulence. And I'll just note that this is work that's done in collaboration with Baylor, of course, Leah Johnson from our group, Luke Van Rokel from LANL, Jim McWilliams from UCLA, Peter Sullivan from NCAR, and Paul Hall from Brown University as well. So unlike a lot of the talks we've heard this week that have focused more on the mesoscale, which really dominate horizontal transport and fluxes in the ocean, which is why they get so much attention. My talk is focused on the smaller scales that are almost always parameterized, which are the submesoscale and boundary layer turbulence, and they really dominate the vertical fluxes in the ocean. And boundary layer turbulence tend to mix and deepen the mixed layer, whereas submesoscales, so mixed layer eddies, tend to re-stratify and shoal the mixed layer. And it's this interplay between these different processes that effectively set the mixed layer depth that we all care about for different climate variables such as atmosphere-ocean interactions, et cetera. So our work is focused on really updating this parameterization to better capture the physics that's involved. So a short overview of the current parameterization. So similar to the GM parameterization, the mixed layer eddies parameterization is described by an overturning stream function that gets incited by baroclinic instability, except it's confined to the mixed layer itself. And it acts to slump isopycnals, which are essentially submesoscale fronts. So in this figure over here, we can see a submesoscale front described by a sharp temperature gradient. And we've got instabilities that form along this front, which are the mixed layer eddies, which can then be captured by this overturning stream function that's attempting to slump this front and re-stratify the mixed layer and essentially show the mixed layer depth. This overturning stream function gets then converted into velocities, which is calculated in the model. And in Fox-Kemper et al. 2008, they write down the form of the stream function, which is described by a constant. Delta S is the grid scale. LF is the width of the front, which is going to be the focus of this talk. H is the mixed layer depth. And delta grad B is the buoyancy gradient of the resolved model. So this might be a little counterintuitive because we want to capture the buoyancy gradient of the front. But in this paper, they argue that the buoyancy gradient times the grid scale over the frontal width will scale like the submesoscale front buoyancy gradient. So this is really one of the main reasons why frontal width is so important to capture, because what it's really doing is it's capturing the subgrid process that we can't resolve. And then in the denominator, we've got the Coriolis force, and this tau over here is an artificial timescale factor that gets used in order to avoid problems near the equator. And I'll get back to that also a little later. And UZ is a vertical structure function that vanishes below the mixed layer. So it effectively confines this parameterization to the mixed layer itself. So you can see that the parameterization strongly depends on frontal width. The narrower the front, the sharper this stream function is going to be. And currently, the frontal width is set to the deformation radius, so NH over F. And actually, since this parameterization was set up, numerous papers have shown that this is actually not necessarily a very good expression for frontal width. There have been found various different frontal widths that are way below the deformation radius. And in addition, including this stratification term over here is also not very robust across models. So there's a lot of motivation to try to find a more of a physical constraint for frontal width. And like I mentioned, there have been several papers that have discussed really what type of mechanism is associated with fronts and can determine the width. And the community has really established that this must be determined somehow by boundary layer turbulence. But it still hasn't been clear really how to set the scale and what really determines this. So this is going to be the focus of this talk. And in fact, this is all the focus of my PhD. So I've been studying a lot the interactions between submesoscales and boundary layer turbulence. I've thought of this in terms of a theoretical perspective where turbulence is very weak. as well as in a more realistic large eddy simulations where turbulence is very strong and how they interact with submesoscale fronts, where there's winds and waves and instabilities that are present. And in these studies, as well as Jim McWilliams and Peter Sullivan have several papers also related to fronts and boundary layer turbulence. It's really something that's come across these different studies is that vertical turbulent fluxes are able to generate, form the fronts, so frontogenesis by vertical turbulent fluxes, whereas halting the front at a constant width or weakening the front, also known as frontal arrest, is made possible by horizontal turbulent fluxes, also found to be horizontal shear instability. And we want to utilize this understanding of frontal formation and the interaction with boundary layer turbulence to come up with a scaling. So back in 2015, Jim McWilliams described what's known as the turbulent thermal wind balance, which essentially really captures what submesoscales are about, because we're not purely in GFD, QG world, where we would expect a pure thermal wind balance to exist, where we've got buoyancy gradient equals vertical shear. And we're not purely in boundary layer turbulence world, where we have the Ekman balance that's described by this vertical viscosity, eddy viscosity. So in submesoscales, we really think of all these processes kind of being of order one. So we get this three-way balance, which is known as the turbulent thermal wind balance. And if we acknowledge that this is really the governing equation of the front, and it's capturing all the leading order dynamics in this three-way balance, we are looking for a scale that will represent this balance. And what we've done is we've followed through, and I'm not going to go through all the math, but if anyone's interested, I'd be more than happy to walk through it. We followed through these scaling arguments by insisting that also boundary layer turbulence scalings and also QG scalings are consistent within this equation. And we've come up with a new formulation for this frontal width, which now consists of terms that are actually associated with boundary layer turbulence. So CF is just a constant, which I'll talk about in a little bit. And now we've got U star cubed and W star cubed, which are the turbulent velocity scales associated with turbulent friction velocity and turbulent convective velocity. And this is really inspired by EPBL boundary layer scheme, for those of you who are familiar. And what we've got here, we've got the Coriolis term also, and HBLT is the boundary layer depth. So instead of being defined by the deformation radius as in before, we now see that we can relate the frontal width to be associated with turbulent properties such as turbulent velocity scales and boundary layer depth. And if we follow this through and go back to the original stream function expression, we can see that we no longer need this artificial timescale, because now our Coriolis force is in the numerator. So this is also exciting, because this means that we are eliminating another parameter that really doesn't have any physical meaning to it. And we can see that we now have this, we have the boundary layer depth in the numerator, and then the denominator, we've got our velocity scales. And it's just important to note that these can be easily obtained from any boundary layer turbulence scheme in the model, whether it's KPP or EPBL. As long as we define them as public, we can just extract them from the already calculated variables in the model and use them to define our frontal scale, which then gets inserted into the submesoscale parameterization. And what we're working on now is trying to validate this and see, first of all, whether this makes sense, but also what would we expect this constant to be like across various different settings that we might expect that could occur, for instance, in a global climate model. So we're looking at large eddy simulations with varying turbulent properties. These are large eddy simulations that have a front that's being strained by a larger strain field. And it's also in the presence of boundary layer turbulence with varying U star and W star, so varying winds and convection. So we've got a convection case, smaller mixed layer instabilities, Stokes and wind, no forcing at all the forcing together. Also hoping to start looking at turbulent thermal wind LES by Peter Sullivan and Jim McWilliams. And in all of these simulations, we're measuring how wide are the fronts, how deep is the boundary layer, and putting this all together in the frontal width scaling. And it turns out that this constant is closely related to the turbulent Richardson number. And it turns out that this turbulent Richardson number is very close to a quarter in most of these simulations, which is also not surprising because we know that horizontal shear instability has been found to be associated with the arrest mechanism of the front. So it's really what's setting this frontal width to be a constant. So this is what's great really about this this new scaling is it not only captures the formation of the front by boundary layer turbulence, it's also capturing the arrest of the front by boundary layer turbulence by including this horizontal shear instability parameter. So just as a sanity check, you know, this is great in theory, but does this really make sense? Is this realistic? So Leah Johnson from our group has taken the scaling across different settings and tested to see are we going to get a frontal width that makes sense to us. So I've got 3 different cases here, which I also call them the COVID plot because it at least looks like what I would hope the COVID plot would be. And on top here, we've got NSF, so reanalysis with observed winds. Instead of boundary layer depth, it's using the mixed layer depth climatology. Here, this is GOTM, so it's the turbulent model in the case study of Bay of Bengal with observed surface fluxes and CV mixed turbulence scheme for the boundary layers. And ECHO model, so this is MIT DCM constrained by observations and also uses mixed layer depth. But the point is that in all 3 of these cases, they might not be exactly the way a climate model would calculate them, but what we would get for our frontal width is roughly a kilometer-ish, which is what, when we think about submesoscales, this is really what we think about. We think of the order of 1 kilometer, could extend up to 10 kilometers, could go down to several hundreds of meters. But this is really what this distribution is showing, is that this is what we would expect our submesoscale fronts to look like. So this is very reassuring. And what we're working on now is also testing this in CSM and trying to come up with what this might look like for this new scaling. So what's plotted here is the mixed layer depth. It's not the LF, it's the mixed layer depth that's resulting from the parameterization. Sorry. So the top panel is including the new LF scaling in the submesoscale parameterization. And we've got summer for both hemispheres and winter for both hemispheres. The middle plot is the old parameterization, so the old LF, which is the deformation radius, also for summer and winter in both hemispheres. And the bottom panel is the difference between the 2, so new versus old. So the first thing that's important to note is that this didn't break the model, which is very exciting and not at all obvious. And also that the patterns seem relatively similar. So this is also good because there are a lot of features about this parameterization that are important and that we know that work. But some differences that might be worth noting is especially in regions that we care about, like the equatorial Pacific and Southern Ocean and the Arctic, we do see that this new parameterization is making a difference. So specifically, we're seeing a shoaling here near the equator, and we also see deepening and shoaling in various locations in the Arctic and the Southern Ocean. And I don't want to talk right now about what this means, and this needs more work. I mean, this is really we're just starting to look at this, and we haven't tested yet the sensitivity of this parameter, and we haven't really looked at the full impact of what this is. But this is something that we're going to be looking at right now. So far, I'll note that this was done in POP, and I've used the KPP scheme to extract the boundary layer turbulence variables that are important, but this can be easily transitioned to MOM6, which I hope to be doing soon. This is a fully coupled run, but I'm also starting to look at forced GRA simulations as well to see what that would look like in that scenario. So this is pretty much all I've got. So to summarize, the mixed layer Eddy's submesoscale parameterization represents the restratification process of adjusting submesoscale fronts. The parameterization depends on frontal width, but the current form has been shown to be too simplistic. And what we've done is we've developed a new scaling that relates frontal width with boundary layer turbulence by building on the turbulent thermal wind balance. And this modified parameterization utilizes variables from the boundary layer turbulence scheme, U star, W star, and the boundary layer depth. And currently we're working on validating this using large Eddy simulations of submesoscales and boundary layer turbulence over a variety of different scenarios for turbulence and frontal width. And also working on testing this in CSM and estimating the climate sensitivity and impact of this modification.
Great, thanks, Abigail. Already a couple questions. Takaya?
Hi, I think this is great. I guess just one simple question I have is, now that you bring the Coriolis parameter to the numerator, does that mean like the restratification becomes weak near the equators in the new formulation?
Yeah, it means it will vanish near the equator. Yeah, okay. I don't know yet what that means physically, but that's what's going to happen. Yeah.
Okay, thanks.
Okay.
Yeah, Abigail, could I ask a question? My hand raiser thing doesn't work, so I don't know that I should break in or not. But in your numerator, you have the U stars, U star cubed and W star cubed. Are you assuming that any kind of surface wave or Stokes is combined within U star, or does your coefficient changes depending on the waves, or do you think another term would be added with a Langmuir number or something like that in that numerator?
Yeah, that's a good question. That's a good question. That's something that we've been thinking of but haven't actively tested yet. And I don't know the answer to that right now, but I do know that Langmuir, its dependence on U star means it's going to deepen as U star increases, whereas the submesoscale, it might mean the opposite, because the submesoscale parameterization will show the mixed layer. So it's hard for me to say which one will have a stronger dependence and what that would look like, but that's definitely something we're going to be interested in finding out.
Thank you.
Thank you.
Where's the moderator? All right, I'll moderate. Peter, you're next.
So Abigail, that was a very clear talk. I was also going to ask about what happens at the equator, because the length scale is there proportional to 1 over f squared. So it's getting larger and larger as you go to the equator.
Yeah, so well, the thing is also is that H, boundary layer turbulence, also has a dependence on F in there. So it's not clear that it would be a 1-to-1 increase. Yeah, I don't have a clear answer to that, because you've got this boundary layer turbulence depth in there as well, which has a dependence on F, which is another reason why it's more appealing to write the total stream function. But I don't have a good answer to. I don't expect the frontal width to increase to infinity as you get near the equator. So there must be some limiter eventually that would kick in.
In the numerator there, the formula you've got, can you really tell that to be different than, say, m star u star squared plus n star w star squared?
Not necessarily. This was really inspired by EPBL and in the hopes that we could also just extract that exact formulation from that parameterization. But I'm not set on having it in this exact format. This is coming from parameterizing the fluxes themselves that are within the viscous term in the thermal wind balance. So it could be either way, really. That would be something to test as well.
Okay, now that I'm realized that I was muted, I'll return to moderator status. Steve, go ahead.
Thank you. With this slide, Abigail, great talk, by the way. Another sanity check that I wonder if you've thought about is the case where you have very, very small forcing, where U star and W star are very small, if not going to zero, but you still have a numerator that's not going to zero.
Yeah. So
I'm looking at the stream function here.
Yeah, so it's possible to add like a minimum value for U star and W star, but then again, your boundary layer depth will also go to zero if you've got no forcing. So they might cancel out some way in some limit, and maybe it would be smartest to set this as a constant in that case.
Sounds like you're getting back you're putting back a tau somehow.
Yeah. But maybe it would be more linked to CF over F or something like that.
Yeah, great, thank you.
Yeah, I mean, the fact that it runs right now in the model is reassuring in that sense.
Yeah,
that it didn't break. Yeah.
But the Hallberg rule is that models are, what is it? Something will always go wrong.
Murphy's Law machines.
They're Murphy's Law machines, yeah.
Okay.
Yeah. Just keep that in mind.
Yes, thank you.
So we'll let Bob expand on that. Go ahead, Bob.
I think that particular statement is self-explanatory. But part of the justification for that tau that we put in the denominator, and it was hand wavy at the time, was that if you have a horizontal component to rotation, that might also inhibit the vertical scales. That there are other subtle things that can come in. Obviously, you've done a fantastic job of kind of cutting through a lot of that hand waving waffle to come up with something that I think is a fantastic new contribution. But there were a few other aspects of that original thing. For instance, the assumption that you can scale from the model's resolved gradients down to the frontal scales in order to estimate what those frontal gradients are. Or, for instance, the vertical structure associated with mu. Is there a follow-on study in which you clean up some of those other pieces as well, maybe, I hope?
I haven't revisited that yet. My focus has been on LF so far, but I assume, when we're in the process of actually writing up a manuscript, we'll probably be looking at some of those other, as Baylor says, finicky pieces. But yeah, I'd be happy to communicate with you about this offline and maybe also some concrete suggestions.
Yeah, that'd be great. Thanks.
Okay, one more quick question, Tony.
Yeah, I just, Abigail, very nice talk. I just want to make a bit of an anecdotal point. Using our data assimilation, we looked in the tropics in particular, what the increments look like with and without submezzo. And when we turned submezzo off, the increments were much smaller, indicating that was something that was better. So I think your new scaling probably makes more sense, at least in terms of what I can see from the increments that we see from the data simulation.
Because it would shut off at the tropics.
Yeah.
Yeah, great.
Okay, and Abigail, you might want to follow up in the chat. There were some additional comments, but I think we need to move on.
Take a look. Yeah, I'll stop sharing. Thank you, everyone.
Yeah, and then next up is Dhruv. You're muted, Dhruv.
I said I'm having some trouble sharing my screen. I think I need to quit and come back. It's giving me some error.
Okay. Let's see, maybe
It says it's because of the recording. Some preferences.
Does somebody else have his talk he can show? You can drive it, Frank?
Let me see. Did you send your talk in, Drew?
I did. I mean, I can just jump out and come back in a second.
Well, let's see. Elizabeth, could you, well, let me, is it in the Google Drive?
He just jumped off.
Oops, okay.
I'm here. I can
Okay.
I can find that. 1 second.
Let me just get there and see. While we're doing that, let me just make a couple of comments that I was going to make before the last talk anyway. First is a huge thanks to Elizabeth and Ryan Johnson for all the work they've done behind the scenes. Literally would not have been possible to have this meeting happen without their help. And to remind everyone to send in their slides. So, oh, he's back, or is he?
Oh, great.
We're not hearing you, Drew. We can see your slides. And seeing your mouse.
Okay, can you hear me now?
Yep.
Good.
Okay, good, thanks.
Sorry about that. This is my first time giving a Zoom talk to such a large group. Okay, yeah, thanks a lot for allowing me to talk at this working group meeting. It's been really great. And so my original title was related to a very specific project that we've been working on, but because there was more time, I decided to sort of talk a little bit more broadly. And just have to acknowledge that none of this work would have been possible without my collaborators, especially Chu Shao, who's a PhD student at NYU and who was really instrumental in the second part of the talk. And also Takaya Ushida, who's I've worked with a lot over the last few years, and a lot of the ideas that I'm presenting, he's kind of taken them forward and applied them to more realistic simulations and looking at like iron fluxes and stuff in the Southern Ocean. So check it out. And also to all my collaborators, more senior faculty who have allowed me to do this work. Okay, so getting in, Abigail set a really good sort of starting point for my talk. And so the central character of the work that I'm presenting are ocean fronts. And just to sort of remind everyone, oceanfront is a region where you have isopycnals that rise to the surface and they are kind of bunched up together. And this is this could likely be happening due to mesoscale strain that it's pushing these isopycnals together and in the surface layer. And when that happens, you form a really strong geostrophic jet that goes with it. In the process, what also happens is that because your isopycnals have risen up, there's a cross-frontal ageostrophic circulation that sets up to try and relax these. And if you have a case where the base of the mixed layer might not be as sharply defined as some of the idealized studies, consider it's possible that the downward part of this ageostrophic circulation can move fluid from the surface into the interior. And this is something that we see in observations. So these are some sections taken by a glider in the Mediterranean Ocean. So you see density. There's one isopycnal marked with this black line. You'd expect that there would be this ageostrophic overturning going on over here. And you see the signature in tracers. And so you see that in temperature, which is like a passive tracer in this case, filaments extending down to depth. And you see something similar in chlorophyll. And these are some snapshots of a front from a simulation that I'll discuss next, in which you have a front shown by these black isopycnals, and you kind of see the same thing, that you wait a few days, and at the front, the tracers have been pulled in to depth, significantly below the mixed layer. The mixed layer is about 100 meters in this case. So, this is some anecdotal sort of evidence that's been around for a long time, and it brings up two kind of big questions. One of them is that, while fronts are quite significant locally to pushing tracer from the surface into the interior, do they play any major role in setting the large scale budgets? and kind of more generally, what are the dominant scales and processes that are involved in ocean ventilation? So to address this, we run a suite of simulations where we have a very simple zonal periodic channel. This is kind of what people were doing before they had never world simulations. And so the channel itself is a beta plane set at about 35 degrees south to just give us a little bit more room to resolve eddies. It's 2,000 by 2,000 kilometers in the horizontal, 3 kilometers deep. It's forced by buoyancy restoring at the surface and a wind stress. And to add some realism, we also have a meridional ridge that extends through the entire north-south extent of the channel. So this basically gives you stronger eddies on the downstream side. When you run the simulation, you also have these sloping isopycnals that are rising to the surface in the interior. Once these, and we run these simulations at 3 resolutions, 20 kilometers, 5 kilometers, and 1 kilometer. And once the simulations have reached a steady state, we introduce a tracer. And the way the tracer is introduced is that you have a surface restoring condition. And it is very rapid. The tracer is restored with a restoring time scale of 72 minutes, which is very fast, but it gives you a gas transfer velocity that's very similar to what you have in the Southern Ocean at moderate wind conditions. And like I said, the tracer started after the physical flow fields have reached into equilibrium. So this is a slide where I'll be showing you a comparison of the 3 simulations. And just to kind of orient you, what you're looking at is, imagine yourself kind of sitting at the interior of the ocean, staring up at the surface, and the southern side is on your right, and the northern side's on your left, and the flow is going kind of from top to bottom in these projections. And what's being plotted is basically an isosurface of a tracer in 3D, and it's also colored by the depth up to which it's reached. So if you see red, it means that the tracer's near the surface. If you see blue, it means that the tracer's reached deeper into the interior. And just to kind of point out that in these simulations, because of flat vertical walls, we end up with very strong mixed layers in the south, and they're kind of just an artifact that we will disregard in the rest of the analysis. We basically don't consider that region. And so what you see is that as you are increasing the resolution, more smaller scale fronts form as you expect. Also, the mixed layers get shallower. But what's interesting is that even though the mixed layers are getting shallower, the tracer that's being there's more tracer being transported deeper and faster. And the way that you can see that is that all the simulations are running at the same time, And if you look at some fixed time, you see that there's more blue at the higher resolutions, indicating that the filaments have reached deeper. Okay, so that was qualitative. Can we say something a little bit more quantitative? So over here, what I'm comparing is the surface flux at a particular resolution relative to the surface flux at 20 kilometers as a function of time. And so for the 20 kilometer case, it's obviously just going to be 1. But when you look at the other resolutions, you see that the net surface flux increases by about 50% when you go from 20 to 1 kilometer. And this also has implications for tracer storage at different depths. And there's multiple lines, but focus on the dashed ones over here, which are accounting for the amount of tracer that's reaching below the mixed layer at different resolutions. And essentially, when you have a stronger surface flux, it is kind of being balanced by more tracer being moved under the mixed layer. So to ask the question of what scales are important, we did a spectral analysis. And so first, what I'm showing you is a wave number frequency spectrum of 2 quantities, the vertical velocity and the co-spectrum for the vertical flux, the frequencies on the y-axis and the wave numbers on the x-axis, and the resolution decreases as you go down. So let's look at the vertical velocity. So what you see, is kind of what you expect, that as you go to higher resolutions, you're resolving more scales. But there's something kind of very interesting that happens when you move from 5 kilometer to 1 kilometer. That there's this blob of energy that gets sort of energized at the highest resolution. And this signal looks very much like internal waves. And so essentially, most of the vertical velocity, or a dominant part of the vertical velocity at 1 kilometer, is due to the waves. But then when you look at vertical fluxes, that part of the vertical velocity has almost no signature. You are seeing that as you're going to lower resolutions, the scales that are sort of contributing to your vertical flux are becoming smaller and smaller, but the dominant part of the vertical velocity is not what is contributing to it. We can also look at this in wave number depth space, and you see kind of the same story where you go to high resolutions, and suddenly moving from 5 to 1 kilometer, you have the strong energization of waves, but that part of the vertical velocity variance has no contribution to the vertical tracer flux. And the other thing to take from this figure is that near the surface, there is a broad range of scales that are contributing to the vertical flux, including the large and the small scales. And as you go deeper, this range shrinks, and it shrinks towards the large scales, so kind of like around 100 kilometers. So that was all, that's all nice. And it is something that we wrote about in a paper a couple of years ago. The next thing that one of the comments that we got from the reviewers was that, this is all nice, but can you say something about the individual processes that are going on? So that's something that we have been digging on into since. And to do that, one of the first things that we needed to do is, come up with some sort of method that can help you distinguish between the different flow features kind of in an automatic fashion. So this is just a picture of the vorticity and strain, a single snapshot in a region that's about 1,000 by 1,000 kilometers. And as a human, I look at it, and it's very easy for me to find different flow features. So I see that there is some filaments of vorticity that are also associated with filaments of strain, and they're likely fronts. I see, these positive anomalies that are cyclones. I see some negative anomalies that are anticyclones. But how do you break this apart in an automatic fashion? And there was a method that was sort of, that I originally read about in a paper by Shervina et al. 2013, suggested that we should look at the joint PDF of vorticity and strain. And once we do that, there are different parts of the joint PDF, and we can break it up using the vorticity equal to strain line, which is actually also the place where the Okubo-Weiss parameter is 0, if you were paying attention in Benstock earlier in the morning. What they said is that, the regions that are strain dominated, that are up here, look more like fronts, and the regions that are vorticity dominated, depending on the sign, they are indicative of cyclones or anticyclones. And so we applied this to our simulation, and we essentially are making a map of the vorticity that field as shown over here, just that in this particular case, I'm only showing the regions that are in the part of this joint PDF that are fronts. So, strain dominated regions, these are cyclones. So these are vorticity dominated, but with a positive vorticity, and these are anticyclones. And you look at a movie of how this goes to show you that the method works, kind of amazingly well. Almost, it surprised us like how well this works as a function of time. And you can see that there are these cyclones spinning around clockwise in the Southern Ocean channel. There's these big anticyclones kind of spinning around in the other way, and then everything in the middle is fronts. Another takeaway from this is that just kind of look at how sort of robust this joint PDF is. It's varying, it's jittering around on the edges as time goes on, but essentially the shape, it just stays the same. And we could have done this for a much smaller region, maybe like 100 by 100 kilometers, and the shape still emerges. So then this is what I'm showing over here is kind of just the mean of the joint PDF and this distinct shape that it has. And we investigate how this joint PDF changes as a function of resolution. So in the top row are two simulations that were at 5 kilometers and 20 kilometers. And one of the first things that you notice is that the joint PDF has shrunk in size. And you can see that by the range on the X and Y axis has changed. It also becomes more symmetric as you go to lower resolutions. And you see the same thing if you coarse grain the 1 kilometer field. And so essentially, as you increase resolution, your vorticity strain joint PDF is expanding, likely because you're resolving the smaller scales, and you can have more of something like an entropy cascade, kind of pushing your gradients to higher values. And it also suggests that the outer extent of the joint PDF is associated with smaller scales. And so now that we have some understanding, what we'll do next is we'll condition different properties and find conditional means of those on the joint PDF. And before going forward, just one kind of side note is that one of the other interesting things that we found was that at the 1 kilometer resolution, if we consider instability criteria, which is very similar to the ones that we think about with negative PV that define like centrifugal instability and symmetric instability, with the addition of this consideration of curvature that was written about in this recent paper by Buckingham et al. 2020. So this instability criteria, when it's negative, it suggests that the flow is unstable. And what we see is that kind of on the edges of the joint PDF are the regions where you have the most sort of unstable regions. And there is this vorticity equal to strain line along which there's this very stable region. And so essentially how I view this is that there's all this turbulence that's trying to push the joint PDF out. And as it's getting pushed out at the edges, the points that are over there are becoming more and more unstable. And so they sort of collapse and kind of push it back in. And there's this balance that's going on. So let's start thinking about the vertical fluxes, which is what I wanted to talk about. So first thing we do is look at the surface divergence. So this is again for the 1 kilometer. There's a lot of words here, but basically this triangle down here is where we are saying anticyclones live. This is a triangle that we say cyclones live, and this top strain dominated region is where the fronts live. And if we condition the divergence on this, we see that the fronts have a downwelling side, which is where you have strong convergence, and they have an upwelling side, which is where you have divergence. So then what we can do is we can look at the tracer budgets in this sense. And before I actually show you the budget terms, I'm showing you what the conditional means of the different terms look like. So if I was looking at the tracer budget in the vertical direction, there would be a component that comes from the advective flux, a part that comes from the diffusive flux, and a part that comes from the surface flux, obviously depending on where you are in depth. And first I'm showing you the conditional means. And so that kind of tells you like, what is a region in this joint PDF doing on an average? And so if you look at, let's look at the surface and diffusive fluxes first. And if we look at them first, we find that regions that were associated with surface divergence are also regions where you have the strongest surface fluxes. And where you have the strongest surface fluxes, you also end up having quite strong diffusive fluxes. And that's because the mixed layer responds very quickly to what's happening at the surface, or essentially the surface responds very quickly to what's happening in the mixed layer. But then if you look at the advective fluxes, the picture is completely changed. Most of the downward flux is coming with the regions where you have strong convergence, or where kind of the downwelling side of the fronts live. Another point to take about this is that this axis over here is a log scale. So there's very strong variation in this space for the advective fluxes, but these are linear scales. And so even though, on this color scale, it looks like there's a strong variation, it's not quite as strong as what you're seeing over here. And what these are suggesting is that you have regions which are on the upwelling side of the fronts where you're bringing in low tracer anomalies. These get mixed quickly in the mixed layer, and the surface fluxes respond to these, and that's kind of happening on this side. And then you have these thin filaments that are being pushed in. So this was what the regions are doing on an average, but what we really care about is what they do in a summed or budget sense. And to do that, we need to take the average properties and combine them with the actual frequency of these events, or the probabilities of these events. And when we do that, we get this. So this is, again, the advective flux, the surface flux, and the diffusive flux. And as I noted before, the surface flux and the diffusive flux, they look very similar, and the variations are linear, and they're not very strong. And so what we find is that, the variation in surface and diffusive flux in this joint PDF sense looks very much like the joint PDF. What that means is that if you have more of a certain region, you'll have more diffusive flux coming from there. But when we look at the advective flux, the story is different. Okay, sure, you have more regions down, sort of more surface area down here, but there is this tail of strong fluxes that are kind of extending to on the, kind of giving it a very different shape than the joint PDF. To summarize it in a slightly different way, what we did is we took the joint PDF and we considered sort of isocontours of constant probability and integrate out in this joint PDF. And basically what we're trying to do is that we're saying that the largest scales are kind of sitting near the origin, smallest scales are sitting outside. And so if we integrate outwards, what we'll see is that later in the integration is where the small scales start to contribute. And this integration is shown over here. So the dotted line that you're seeing over here are the horizontal area fraction. And so what that tells you is that as you move outwards, you're very quickly covering all of the area. And by the time you're somewhere out here, you have sort of covered most of the surface area. And the surface and the diffusive fluxes follow the same pattern, telling you that, sure, even though there's some surface variations and inhomogeneities, on an average, it's really just how much surface you have exposed that matters. But when you look at the advective flux, the story is very different. This curve does not rise at the same rate as the surface area. And what that means is that because the curve is rising slower, it means that the smaller, sort of smaller parts of the surface area, or the regions with the strong vorticity strain, are contributing more strongly to the vertical flux. And just as a metric, so if you look at this point, you can see that less than 5% of the surface area is responsible for over 20% of the vertical flux. And this shows that fronts have an outsized impact on vertical tracer flux. And this is some work that we have just submitted to JPO. And so hopefully it'll get reviewed and come out soon. So kind of wrapping it up, the conclusions that we have is that as you increase the model resolution, tracer ventilation increases, and it increases by about 50% when you go from 20 to 1 kilometer. And this might increase even more as we go to higher resolutions, because these simulations are nowhere conversion in resolutions. Using the spectral methods, we were able to reveal that internal waves play a dominant role in increased vertical velocities at higher resolutions, but they play a negligible role in the increased vertical tracer flux. There's a wide range of scales that are responsible for contributing to vertical fluxes near the surface, and this range shrinks to larger scales with depth. And this might have something to do with kind of which modes are most active, and the decay rate of these modes that are active near the surface. And surface vorticity and strain can be used to decompose the flow into fronts, cyclones, and anticyclones. And when we do that and analyze in that decomposed sense, we can show that fronts have an outsized impact on tracer ventilation. And in our simulations, about 20% of the flux passes through about like 5% of the surface area. And this ratio would likely increase even further with the resolution. So thanks, and I'll take any questions.
Thanks, Dhruv. Okay, Ben?
Hi, Dhruv. So I really liked your joint PDF plots. So I had a question for you about those, because you mentioned that dashed line you overlaid is the cube of ice equals 0. So we were looking at cube of ice, we got that there was this gulf in between around 0, where there was basically no land or energy that more or less that was falling on this 0 piece. But it was admittedly the relative size of that compared to the magnitudes was very, very small. So I was wondering if maybe the difference here is that the gulf's maybe too small to show up on, say, a joint PDF, or if you think there's maybe a qualitative difference between with what's going on.
I'm sure I didn't catch your question entirely. What did you say you exactly observed on this line? What happens?
So when we do, so if we plot, say, kinetic energy as a histogram over a cube of ice, we get that there's a division around 0 where there's kind of a very close to 0. There's actually a clear break between the positive and the negative. There isn't anything really around 0, but that's if we spread out lots of orders of magnitude. So I'm wondering if, because on these plots, it looks like there is a lot of stuff happening around 0. So I'm wondering if it's just that the gulf is narrow enough, this kind of 0 energy band that doesn't really show up here, or do you think that there's something qualitatively different going on?
Yeah, I actually, that is not something that I've looked at. I haven't, looked at what happens exactly at that line. I'm a little bit surprised that the kinetic energy kind of drops off at that line, because sort of, one of my concerns with this method has always been that this line is almost like an artificial break. And you can see that in some regards over here, that, if you play this movie, that sometimes regions kind of like jump back and forth between these, and they would, if you really stare at these, you can see them like appearing and reappearing. But this line is where these different panels break, and it doesn't look like the eddy kinetic energy should be smaller over there or anything.
Yeah,
we can talk about it more offline. I'd be interested to see what you guys found.
Okay, yeah, that sounds good. Thank you.
Great. I don't see any other. Oh, Hemant. Hemant Khatri, go ahead.
You're muted, Hemant.
Hi, sorry, I was unmuted. Hi, Dhruv, it was really nice talk. Hello, can you hear me?
Yes, go ahead.
Yes, so just backing up on, could you please explain why were you confused about this eddy kinetic energy breaking up on this zeta by f naught and strain line equal to 1? I didn't get get your point.
Is this a question to me or to Ben?
To you.
Because I don't see any break.
You said there's some jumping off and off here.
Oh, I mean, that's all that I was saying, was that, this line is to some degree like a little bit artificial, right? Like you could have a point that quickly jumps between a front and a cyclone. But there is no but on an average, right? Like the fact that these plots are so coherent suggests that that doesn't happen very much, at least kind of on these bigger scales that we are looking at. I don't see or expect why there should be any break happening at those lines in terms of the kinetic energy. I haven't looked at it.
All right, thanks.
Okay, thanks. I think we need to move on. Thanks, Dhruv.
Yeah.
The next speaker is King Lee.
Yes, can you hear me?
Yep.
Share my screen. Can you see the screen? Great. So here I'm just want to give a very brief update on the laminar turbulence parameterization in CESM 2.2. This is actually just an update on the implementation of this long overdue parameterizations in CESM 2.2. So on the implementation work, I would like to thank our Antonius and Mike Levy for a lot of help and many discussions with a lot of people in the audience. And since this is a really a very brief update, I think we could also maybe use this time to discuss some of the issues we are working on the wave coupling. So first, let's briefly review what we mean by laminar turbulence parameterization. So we know for quite a long time that from the observation, when you have ocean surface waves, so by the way, laminar turbulence is a physical processes that results from the interactions between ocean surface waves and background ocean current and turbulence. So its effect is primarily in the ocean surface boundary layer. So we know from the observations that when we have ocean surface waves, especially when we have this kind of laminar circulation structure, the vertical mixing is enhanced. So on the left, we have a plot showing you the vertical profile of the normalized vertical velocity variance. So the thick lines are measurements taken at open ocean, but the thin lines are taken from the laboratory wind tunnel. So the difference is in the ocean, you have a free surface, right? In the wind tunnel, it's a solid boundary. So you see enhanced vertical velocity variance. And actually, when you do the measurements at different ocean surface waves conditions, so on the horizontal axis, it's the Stokes force. It's a lambda number to the -2, which is basically just the Stokes drift. So the bigger this number, the stronger the wave effect is. And you can see that there is a quite nice correlation with the normalized velocity variance versus the Stokes forcing. So this is what we mean by laminar turbulence enhanced vertical mixing here. This is the first one effect. The other effect we want to discuss is the laminar turbulence also enhances the mixed layer entrainment at the base of the mixed layer. So here I plot the normalized vertical buoyancy flux in the ocean surface boundary layer. So this is profiles from different larger simulations forced by different Stokes forcing. As you can see there, with stronger surface forcing, you have surface Stokes forcing, you have stronger normalized vertical buoyancy flux. And actually, if you do a lot of larger simulations, you can get a really nice scaling for the laminar turbulence contribution to the normalized vertical buoyancy flux. So basically, we want to parameterize these two effects in CSM. And I just want to note here that so laminar turbulence can affect the vertical mixing in the ocean surface boundary layer through other effects, which I will not talk about here, but I encourage you to take a look at this paper for more discussions on these effects. So how is the laminar turbulence parameterized in CSM? It's parameterized in KPP. So here is basically just a brief review of KPP. So in KPP, we parameterize the vertical turbulent flux via a downgradient component and a non-local component, whereas where the eddy diffusivity is rated as a length scale times the velocity scale times the shape function. And this length scale, which is taken at the boundary layer depth here, is determined by the bulk richest number. Basically, you have a buoyancy contribution and the shear contribution, which is has a resolved term and an unresolved term. So we want to parameterize these two effects, enhanced vertical mixing and enhanced mixed layer entrainment by laminar turbulence. So the first effect is we just apply an enhancement factor to the turbulent velocity scale in the eddy diffusivity. And this enhancement factor, the scaling is derived from a set of large eddy simulations. And this also match the available observations as well. And for the second effect, we are modifying this unresolved shear term in the bulk richest number. Again, we have this scaling derived from larger simulations. So the first effect, it's already, so this has been incorporated into CSM quite early. So this is in CSM 2.1, it's already there. And the thing I want to update here is just this entrainment effect, which is just incorporated in CESM 2.2. So here are some test cases. So this is just ocean and sea ice only simulations forced by atmospheric data set. So these 4 panels shows the summer mean mixler depth in both hemispheres. So here is the observation. It's an Argo-based observation. And these 3 panels are the simulation results using CSM. So this is using GRA 55 DO dataset, and versus this is a Core 2. And the panel on the bottom right is the we add the laminar turbulence enhanced entrainment. Note that in both of these two, the first effect, the laminar turbulence enhanced mixing, is already there. So we are just adding the second part of the parameterization here. So basically the results is as expected. It's consistent with our tests in when we first developed this parameterization in CSM1. So this is consistent. And there is one interesting thing I wouldn't go into further, but just want to point out that the GRA 55 and Core 2 can give you quite different results. And also for the winter mixler depth, this is also as expected. So this is we got by adding the laminar turbulence enhanced entrainment, we got slightly deeper mixler depth. This doesn't necessarily fix the mixler depth problem in CSM, but it's an additional physics. So yeah, so I think another thing I want to talk about here. Okay, so these so I think the takeaway message of here is these parameterizations is already in CESM 2.2, and currently it's only in POP, but we are going to put it in MOM6 as well, which should be very straightforward. So another thing I want to talk about is this, we call it theory wave. It's basically just an empirical estimate of the Stokes drift to, like, when you don't have an prognostic wave model, you can use this estimate to do the laminar turbulence parameterizations. So basically we derive it from some empirical wave spectrum plus some the directional spreading effect of wind waves, and also the empirical relations between wind and waves. If you put them together, you get these this formula, which is the surface layer average Stokes drift. But this can also give you the Stokes drift profile if you use different depth. So this is basically an estimate of the full Stokes drift profile from the wind. And from there, you can compute the laminar number, or you can compute the laminar enhancing factor to do the laminar turbulence parameterizations. So we have tested this in CSM1 forced by Core 2. So the important, again, this is the summer mean mixer depth as I showed you before. But the important thing here is the bottom panels. These two, one is we're doing laminar mixing parameterization with WaveWatch 3. The other one is we are doing the parameterization using the theory wave. And the point here is they are almost identical. So I think this is an indication that the theory wave, at least for the laminar turbulence parameterizations, the theory wave estimate works pretty well. So I also have an example of looking at this theory wave estimate at the ocean station Papa. So basically, I looked at an annual cycle at the ocean station Papa. So I divide the full annual cycle into 4 stages. So based on the like the observed SST, SS, and mainly the SST and also the Mixler depths, to divide it to roughly 4 regimes. Then you can, because at the ocean station Papa, we have the wave buoy data from where we have the observed ocean surface wave spectrum, and we can compute the Stokes drift from the observed wave spectrum, which is the black line here, the profiles. And we can also put together we can also estimate the the Stokes drift from the theory wave estimate using the wind speed, and which is the blue lines here. And to compare with it, I also have a very idealized exponential decaying Stokes drift profile here. Note that these are the normalized Stokes drift, normalized by the surface friction velocity. So as you can see that although this is not a perfect estimate, but it's quite close, especially it can somehow account for the seasonal variation of this normalized Stokes drift. And on the figures on the right, on the 2 top panels, it's basically the surface Stokes drift and the surface layer average Stokes drift. And you can see, well, it's for a large part of the annual cycle, the theory wave can, well, reasonably estimate the Stokes drift. And if you do the do KPP, this is the results from a single column simulation using Gotham. It's the general ocean turbulence model. So you can see that the theory wave can give you somehow pretty good results. So the point here is the theory wave estimate is useful, and I believe that I think this theory wave is also used in at GFDL by Brandon in the EPBL framework. So I think it works also very well there. So that brings me to the discussion of wave coupling. I would like to discuss with you guys. And so the first thing is the wave component in CESM. In addition to coupling with WaveWatch 3, I think the theory wave could be a very useful option. For example, by implementing it into the data wave mode. This is very computationally efficient. So I think it will be useful for a lot of testing purpose. And right now, the theory wave only estimate the Stokes drift profile. This is good enough for the laminar to estimate the laminar number, laminar enhancement factor for the laminar mixing parameterizations. But I'm thinking if we want to include the effect of other effects of waves, we can probably take a similar approach, maybe by combining an empirical relations with some climatologies. So that could be useful for testing at least. So another thing I want to discuss about is the wave coupling interface. So I think for the wave components to be useful, we will need to have a list of wave statistics to pass to the coupler so that we can get the output and also can be used in the wave parameterizations, wave effects parameterizations. So on these wave statistics, of course, the Stokes drift is the thing I'm most interested. So, but the Stokes, the Stokes drift is a vertical profile, but I think there is already some ways to reduce the amount of data exchange between the wave model and the coupler. So for example, I know the latest version of, maybe Brendan is more familiar with this. So we can do some surface Stokes drift partitions, which greatly reduce the amount of data exchange between the coupler and the ocean surface wave model, and then we can reconstruct the Stokes drift profile where needed. And another statistics I'm interested in, the momentum fluxes between the atmosphere and the waves, and between the waves and the ocean, and as well as the energy fluxes, and also the some estimate of the breaking waves, which will be used for some other parameterizations. And also in order to look at the ocean surface waves climate, I think the CalClip wave statistics. So CalClip stands for Coordinated Ocean Wave Climate Project. So they are interested in a lot of these standard wave parameters like significant wave height, mean wave period, mean wave direction, and swell wave height. So I think that the standard way they did is to diagnose using the 6-hourly output of these 4 wave parameter variables. They can diagnose the mean, the maximum, different percentiles by monthly or seasonal or annual, to look at the extreme events. So I guess we can put at least get some of these statistics in the CSM wave output. That'll be very useful for the ocean surface wave community. And for the output of the data, I think we can output the data in the CSM standard format, probably from the coupler, but I also want to point out here that we want to keep the option to turn on the WaveWatch 3 output in the native format, which will include a long list of useful wave parameters, but that might not be very useful for some general users of CSM, but that'll be useful for the ocean surface wave community. So moving forward, I think as Frank mentioned yesterday, I think doing laminar turbulence parameterizations in MOMP6 via a CIVMX, I think this is quite straightforward. It should be very easy to do because it's everything is in CIVMX, so it is very easy. And also the theory wave, I think we can put, I think the plan is we want to put the theory wave as an option in the data wave mode. So we can, so we can do some very fast simulations without using WaveWatch 3. And then I think this is actually an ongoing work led by Helen Kershaw at Brown University. So we want to update WaveWatch 3 to the latest version, and this will have a new OPSI cap. And also we are thinking about different wave grid. And also the wave coupling interface. So there are a lot of interesting wave variables for parameterizations of the wave effects, but also variables for, to look at for the wave climate analysis. So I think I want to maybe just leave the slides here for discussion, and I'll stop here to take any questions.
Thanks, King. Yeah, so discussions or questions to King. I think, from my perspective as the co-chair, I think thinking about pragmatics, how do we actually implement this? I think the first bullet, is a fairly straightforward recipe. As you say, we can sort of get back to where we were with POP with the MOM6 base cases. The rest of them, I don't know. King, maybe you can suggest how this is going to work. Can we form a small task team to design these new options and assist in the implementation? We do have, a fraction of Alper's time to participate in this, but having the people who are actually doing the science here would be useful to have that outside involvement in this process.
Yeah, I think the first two bullet is really straightforward, because this is the first one is through CivMix. It should be straightforward. The second one is because the theory wave this is already also in CivMix, so it's, I think we can
moving
just
it from CVMix out to the data model. Yeah.
Yes.
Yeah. Okay.
And but the third one, so I think Helen maybe is better here, maybe not, but I think she is leading to update the WaveWatch 3 code in CESM, and especially having this new neopsy cap. So I think she is doing a lot of tests. And I think it will be really helpful to, so the third one and the fourth one, I think they are related, because we want to have this wave coupling interface. So I would like to hear about, for example, Brandon's opinion on what is done in GFDL model for the coupling.
Conveniently, Brandon has his hand up. So.
Hey, very nice talk, Ching. Enjoyed it. So the one thing I wanted to just make clear here is that I have actually done some of this work already on getting the Langmuir parameterizations, including your latest parameterizations in MOM6. So I haven't done this via CVMix. I have it in our wrapper to CVMix. So we'll definitely want to tag up at some point. Hopefully this will be pretty easy for you guys to do. Taking advantage of some of that. As you said, the theory wave is already there. We're using it in EPBL, so it'll be straightforward to use it in KPP as well. And we've also done work for the coupling side of it for importing these Stokes drift terms, as you mentioned. So hopefully, a lot of the pieces are already in place for you guys. So I'll, definitely feel free to reach out when the time is right.
Okay, so. But in terms of the, are you outputting the wave variables for like the wave climate analysis?
We don't necessarily have all of that set in stone. So one of the things is when you get up to you'll need to have the latest version of WaveWatch 3 to have the right wave outputs for importing Stokes drift into the model. As far as like the calclip parameters and things, is that?
Yep.
I think that should be pretty straightforward to set up. A lot of that's, again, already in the most recent version of WaveWatch 3. So I think there won't be too much more than just turning these on.
Right. I think the thing is we want to have what variables are necessary to output, because there are so many wave variables. What variables are most useful for the community? That'd be nice to discuss.
Sure. Yeah. I don't know if I have an opinion to bring forth right now. Obviously, wave height is a very important one, and a lot of people are looking at wave period and how those are related. But I'm sure some of the other parameters you mentioned will be interesting to look at too. So it'll be a good conversation, I think, to sit down and think carefully about.
Yep.
Bill, I see you're unmuted. Did you have something?
Yeah, as I say, my raise hand doesn't work somehow. Yeah, Ching, on your list of moving forward, my impression always has been that you focused much more on the buoyancy flux than the momentum flux. Where do we really put some more effort onto the momentum flux as opposed to just the buoyancy and the wave effects on the momentum flux? Should that be lower than anything you've got on here, or in the middle, or where would you put it?
I'm not sure using the KPP framework is gonna.
Well, it doesn't matter. I mean, your
path.
enhancement factor, for example, you've got the same for both momentum and buoyancy, and that's
Yes.
not true. And there's also a question of what waves do to the direction the momentum flux goes into, which we don't have. So where on this list of moving forward would you put ideas on the momentum flux as opposed to the buoyancy flux? Would it be lower, higher, middle, that kind of idea? Where would you put it?
So I think so that's the next step of these, for example, laminar turbulence parameterization, right? So this is only a very early version, so we can certainly improve that. So that's certainly come after this, the first, right?
Sounds good.
Yes,
Yep,
and
okay.
I'm looking forward to like whether you are planning to have your parameterizations ready for this.
Yeah.
Okay. We sort of run the discussion a little long here. We have more discussion time after 3:30 for those who want to hang on, so we can bring this back up if need be. But I think we should go on to our last talk of the day and the last talk of the meeting, Deepak Cherian. Thanks for hanging in there, Deepak.
Yeah, thanks for everyone listening, hanging in there. So I was initially going to talk about parameterized turbulence at the equator, but I've been talking about that a lot recently, and I've really enjoyed listening to all the eddy diffusivity, eddy mixing, eddy energy talks at this meeting. So I thought I should also talk about eddy diffusivity. So my name is Deepak Cherian. I'm in the ocean section at NCAR, and this is some work I'm just spinning up now with my co-Is, Emily Schroyer at Oregon State and Jonathan Nash, also at Oregon State. And what we're trying to do is estimate eddy diffusivity from microstructure measurements. The reason we want to do this is that, you know, it's all of you know, it's a very important quantity in the models, and there's very limited observational estimates. So here's a sample. There are a few estimates that come from trajectories of various sorts or surface drifters. There's a few from advecting particles in flow fields that are derived from satellite altimetry. So Ryan Abernathy and colleagues have done a lot of work there. And then Sylvia Cole has a pretty unique estimate where she uses the Argo data set and mixing link theory to come up with an estimate of eddy diffusivity. In addition, there are two estimates that come from microstructure. I'll talk about the kind of methodology, but you know, the point is that there are very few estimates, and it's especially true for microstructure because there's so few microstructure data from the ocean. And by microstructure, I mean turbulence data, right? So there's two experiments. One is NATRI, the North Atlantic Tracer Release Experiment. So that's Ferrari and Polzin. And so I'll show you their estimate soon. And the second one is this estimate by Alberto Navarra Garabato and colleagues. You'll notice that Polzin and Ferrari are also in there, where they try and, again, estimate eddy diffusivity across the Drake Passage using shipboat microstructure. So like I said, microstructure is the measurement of microstructure in the ocean. So you're really talking about two quantities, epsilon, which is the rate of dissipation of turbulent kinetic energy by really microscale motions in the water column. Those are usually measured by something called a shear probe, which this arrow is pointing to on the right. You'll see these two, the yellow tip and the white tip. So those things are airfoils. And as you deploy them in the water, turbulence moves the airfoil up and down. It's basically a vibration sensor. It senses those vibrations. You get a bunch of voltages and you do a lot of processing and you get to an estimate of epsilon. So this is the rate, it's like this turbulent friction. And it's one of the best ways to measure that quantity. The second thing that we measure is chi, which is the analogous quantity to epsilon, but for temperature. So this is the rate of dissipation of temperature variance. And this is sensed using a fast temperature sensor. So here, this particular instrument has two of them. So you'll see them with this white tip and little blue color. So these sensors, they record at pretty high frequency. So generally 100 hertz is what the rate the data is coming in. And they usually get processed to one estimate of chi and epsilon for a second of data. So that's a really, really small scale epsilon and chi quantity. How do we get from that to eddy diffusivity? So it involves a lot of assumptions. But it's a pretty interesting theory, and I really like it. So we think about the pathways of variance and how you start with the mean field, stir that somehow to generate variance that is eventually dissipated at the microscale, which is what we are measuring with our microstructure measurements. So the theory for this, there's a few papers that kind of go into the details. So I'll just give you a quick summary. The idea is to do a triple decomposition and make some very big assumptions where you end up ignoring 11 out of 16 terms so that you can make some progress at estimating quantities. The idea is there is a mean that very vaguely you would call this like a basin scale field that has horizontal smoothing of something like 1,000 kilometers, and time scale would be years. The second scale is the mesoscale. Again, this is kind of very loosely defined as something like a 100-kilometer scale of variability. And kind of in months. These are just representative scales. And the final thing would be this microscale turbulence that we think we're measuring with the microstructure, where you think is everything that is faster than 10 minutes, so outside the internal waves, and maybe has a vertical scale of like 10 meters or something. And so you can go through a lot of math, which is very nicely explained, in especially Ferrari and Poulsen and this Chris Garrett paper. And this is very nice schematic that tries to show these pathways. So you start off with a mean there. So if you imagine some kind of basin scale gradient, that gradient is being stirred in this framework kind of by mesoscale, which is kind of, again, vaguely defined. So you do that stirring, and mesoscale eddies tend to stir along isopycnals. So you generate a lot of TS variance along those isopycnals. And then that variance is stirred by microscale eddy motions. And eventually all of that variance gets down to dissipation scales, which is where we measure chi. The microscale is also acting on the basin scale mean gradient, generates a variance through, again, some stirring, which is, again, finally cascades down to dissipation. There are no arrows on this because sometimes you can get upscale transfers. For example, from double diffusion, you would upscale from microscale stirring to thermal hairline staircases that you would see in the mean. So that's that. But the simple equation that's kind of the basis for this is written out here in terms of this decomposition. After you get rid of a lot of terms, it says the first term is UT theta t long-term average. This would be the turbulent stirring by microscale eddies acting on the gradient of the mean field. So that's generating some variance, some of which is dissipated at the microscale. And the second term is this eddy stirring, again, acting on the mean gradient. So this is what you would think of as mesoscale eddies stirring filaments on isopycnal surfaces, generating intense theta gradients that get dissipated as chi. And so that's the equation. And the idea is you can rearrange these things. So you have something like an eddy diffusivity. So the numerator here has the amount of variance that is dissipated at the microscale. And we think we can estimate this first term, which is the stirring of the mean gradient, by those turbulent eddies that we're sensing at the microscale, so that you would write it as a diffusivity times a local gradient. Take the long-term average, and you multiply this by some estimate of this mean that is very vague. And then here you have this U prime, UE theta E angle bracket. So that's kind of a U prime theta prime bar for the mesoscale eddies. So you could assume that you can write that as a diffusivity times a lateral gradient squared. And so that would give you a definition of eddy diffusivity. So fundamentally, what we think is we know chi. We think we can get a good estimate of this quantity in the angle brackets here. And so as long as we plug in an estimate of this mean field, which we have to get from some external source, say Argo or Echo, we can get an estimate of something that may be interpreted as an eddy diffusivity. You could be really conservative and say, what we're really doing is having, we think we know how much variance is being dissipated. We think we can characterize the amount of variance that is generated by the microscale stirring of the mean. And then everything else, we are attributing to mesoscale eddies in this case, but there could be other processes that act to generate that variance. So, I give that's a really quick kind of tour of how we think we're going to do it. These are our sources of data. They're called chipods. And they're basically, remember I told you there was a fast temperature sensor and a fast shear sensor that gets you epsilon. The shear sensor is very sensitive to vibration, so it cannot be deployed on these platforms that I show here. So all you see are here, the temperature sensor deployed on a mooring. So this is usually on moorings at the equator. And so there are a long time series of chi and associated quantities on the tau moorings. Another data set that is especially useful for this project is what's called the CTD chipods. Again, because the temperature measurement is not so sensitive to vibration, it can be deployed on a CTD cage and has been deployed on ghost ship cruises for about 5 years. So again, those are only T sensors, and we think we can get a good estimate of chi from these. And the idea is we take that estimate, plug it into our little framework, and try and estimate eddy diffusivity. Again, I'm just starting to spin up, so I don't really have any new results at this point. What I've done so far is try and verify that our method works by comparing with an existing estimate. So here's data from the North Atlantic Tracer release experiment. So on the left is this panel, longitude, latitude, showing where the survey was made. So basically they took a grid, I think it's 400 kilometer by 400 kilometers, 100 stations with microstructure data all the way down to 2000 meters. And then on the right are their estimates in solid lines. So the red is the chi average. So that's the dissipation of temperature variance. In black is their estimate of how much the microscale is generating. Oops. And so the key point here is that you can see that the red is always greater than the black. That's very nice. You want that. And the second is you see a large gap between those two estimates. So in here, there's a bunch of variance that's being generated by some process. In this case, they think that this is the signature of the Mediterranean outflow being stirred on these neutral density surfaces that are approximately these depths. And so you can think of this as mesoscale stirring. And so you can go from here, plug in a estimate of the horizontal gradient of theta, and get to an estimate of eddy diffusivity. I was really excited this morning because the black crosses are our way of doing things coming straight from chi. Little technicality, but basically we think if we used our slightly different method from theirs that only uses temperature data, you get the black crosses, which agree really well with their estimate. So we think as long as we know we are working in a place where there is a signal, like in this case, we know there is a signal of Mediterranean medis basically stirring along isopycnals, we think we can recover that signal with our method. And so, like I said, we have two different data sets. Here's where we have data. On the left are ghost ship CTD transects. So, there's just a few. But what's really interesting is we have 5 sections that cross the ACC, which is somewhere you would expect to see a lot of signal in terms of mesoscale eddy stirring. And we know in the past that Alberto and colleagues have made a good estimate across Drake Passage there. So I am personally pretty excited to get started on this work and make that estimate, at least in the Southern Ocean. We also have a bunch of moorings on the equator. These are slightly more challenging because you have intense equatorial upwelling, which is again going to be a source of variance that is going to be hard to constrain. So I still don't know how we'll deal with that, but if someone has ideas, I'd be interested to hear. This is just another kind of quick estimate we made when we submitted the proposal. On the left is the actual microstructure data. This is from the P06 section. I'm just going to go back to show you where it is. It's this purple one. So it's not really clear that there would be a big signal there. You see some spread in the TS diagram along these isopycnals, so maybe there is some eddy stirring. And so that's the microstructure data processed and averaged across the basin. I have a profile of eddy diffusivity on the right. This is a very crude estimate. We can definitely do better. That think the microstructure data has been cleaned a lot more now. But in general here, the blue is our estimate. I'm comparing it with Sylvia's Argo fine structure, which is in orange. And there's Ryan Abernathy's and Abernathy and Marshall numbers that are right on the top. So you can see some pretty impressive agreements near the top. There's some disagreement around 500 meters, and then maybe some agreement between 1,000 and 1,500. Again, I wouldn't place too much importance on these numbers, but just the takeaway point is we have this pretty unique data set, and we have a pretty unique method of trying to get to this eddy diffusivity quantity that is independent of every other point that's on this figure. And so with that in mind, my question is, what I'm really looking to get from this group is, how do you think such a measurement would be useful for all the modeling and all the parameterization efforts that are going on? Because like I said, these are kind of sparse measurements, but they're very rare. And this is a pretty rare way of trying to use those microstructure measurements. In the best case, I might be able to come up with profiles of eddy diffusivity in quotations in a few isopycno bins in places where we think there's a good stirring signal that we can get. Maybe we may be able to do something at the equator. I'm still skeptical because we need to do something about equatorial upwelling. A kind of conservative way of interpreting what we're trying to do is we can try and quantify the variance that is generated by everything other than the microscale stirring of the mean vertical gradient locally, right? So at the equator, maybe the dominant term is the upwelling, in which case you could get to, here's how much variance is generated by equatorial upwelling. One way to use the stuff would be just to kind of ground truth estimates, such as stuff from Ryan Abernathy and colleagues, and also Sylvia's Argo estimate, which has the advantage of being global and a lot more coverage. But I'm only just starting, and so I'm hoping that somebody has good ideas for how we could work together or collaborate on how to link this up with all the other efforts going out there. So thank you.
Thanks, Deepak. Good job with the dynamic talk selection there.
Yeah.
Okay, Kelvin.
Sorry, just unmuting. An added complication at the equator is that there are features on intermediate scale, such as interleaving of water masses, that one can estimate do contribute a large lateral eddy diffusivity. Can you include these intermediate scales in the analysis that you are looking at?
I mean, in principle, you can keep including scales, right? So you don't have to just do a triple decomposition, you can go quadruple, but then you always have these cross stones that are basically impossible to get. So yeah, I don't have a good answer. The only thing that keeps me kind of optimistic is that it's been attempted twice and you can kind of get a good signal that you think there should be a good signal. But I would be skeptical of further decomposition with very sparse observations.
Okay, thank you.
Okay, Sylvia Cole. We're not hearing you, Sylvia. Looks like you're unmuted, but your volume is way down.
Could type in the chat, I guess.
Can you hear me now?
Good.
Okay. I was gonna say, I guess I would be cautious about trying to compare to too many other estimates, because in some sense you have a snapshot of the diffusivity versus a long-term average. So it's not gonna surprise me at all if there are some differences.
Yeah, fair point.
And I also think if this actually works in the equatorial region, that would be interesting, because that's sort of a big question mark for all of the reasons just mentioned, as to whether some of the other methods would as well.
Yeah, I view it as more a kind of interpretation, which is what my second bullet point is this is kind of the unexplained variance that is not generated locally. So, yeah.
Okay, Drew.
Hey, Deepak, that was a great talk. One question that I have is there any, so it seems like everybody's kind of, estimating diffusivity in their own way, right? There's all these different methods. Each paper kind of has its own. Is there any work using maybe like idealized simulations or something that tries to compare these methods in a more realistic flow? Because I know that Ryan has a paper where he compares a few of the methods in 2016, I believe, or something. But this was not one that was part of it. And so like the question is that, we're all estimating these parameters, kind of like what's the, which ones work, what are we looking for?
Yeah, so this is an interesting question. I don't think anyone has tried this, as you point out, but I don't remember what, I've read Ryan's paper, but I don't remember what methodology he used. But this stuff is basically the tracer variance budget equation. There's no reason you couldn't do it just to figure out how the model is closing the budget, and try and get it from there. Yeah, that's interesting. I haven't thought about that. But yeah, it'd be interesting to apply it to a model.
And then do you think that, a diffusivity estimate that we get from this or any other method, like, do we just plug it back into a model and see if that works? I haven't even seen that happen very often.
Well, I don't think you want to do that. I think you would mostly think of it, one way would be to have the model output its diffusivity fields and see how that agreed with, all of these various estimates. A stronger test would be to actually test the variance balance, right? So we know chi, we think we know chi, and as Sylvia pointed out, these are very sparse observations. So how much you believe them is something. But you could get like, okay, the model is dissipating so much, generating so much chi, and so dissipating so much variance at this point. And here are all the sources. Does that line up with what we think is happening in the real ocean, where we can make this estimate? But yeah, it's an interesting problem to think about. It's like, how do you use microstructure along with models in some sensible way?
Okay, Malta.
Yeah, thanks. Really interesting stuff.
Thanks, Malta.
I have a follow-up on what was just said, or wondered about comparing the different methods to infer diffusivity, and having a sort of more theoretical thought on and how far should they be the same. I think one thing that Ryan did in that paper, and that's sometimes done in general, is this effective diffusivity diagnostic, which I think is pretty closely related to this, if I understand it correctly, right? Because both what you're doing and that is at least related to the destruction of variance, which is actually a different term than what's flux gradient relationship, which most of us modelers think about, which is actually related to the generation of variance by the mesoscale. And so there's a variance transport, so the spatial patterns of those things, for example, should be different.
Yeah, I think you're right. I think of the effective diffusivity stuff. Yeah, I think
somewhat related. Yeah, I mean,
because they do it in tracer space, right? And so then.
Yeah, and it's basically, I mean, you can actually do it in the non-Lagrangian approximation is basically just the Cox diffusivity. It's just the gradient squared over the mean gradient squared mean over the mean gradient squared, which is certainly related to the destruction of variance.
Yeah, I agree. Yeah. That's a good, that's good perspective. I hadn't thought of it that way. Yes.
Really interesting, though.
Thanks.
Okay. Any other questions or comments for Deepak?
Yeah, I have one, Deepak. I mean, what in that equation that you had large scale gradient, which you had to use to get your diffusivity, right?
Yep.
And earlier today, we saw an awful lot of great attempts to get energy spectra as a function, wave number spectra. So do you think those would give you some idea of the scale of that gradient that you need to take, so you don't, and so you actually capture all the energy containing eddies, or is it something completely different?
I think yes, but there's kind of a practical problem in that the way you get that is from a mapped field, with Argo, basically, right? So there's inherent assumptions in that mapping that are also a big influence.
In making the maps themselves, you mean?
Yes.
Oh, that's true. Yeah.
So that's, yeah, I was thinking of this because, diffusivity has some inherent scale in it. And so in this case, that scale would be whatever the Argo mapping procedure, I guess.
There was a question in the chat from Brenda Zhang. Is there any chance you would get a negative diffusivity through this method?
Oh, totally. There's large error bars and all of these things in the top. But I wouldn't place any special importance to those negative values. It just says that we can't distinguish the numerator from zero.
Okay. All right. Well, that is a wrap on the talks. Thanks, Deepak. Thanks to all the speakers, all 3 days. As we said, we can stay on as needed for some follow-up discussion. I invite everyone to turn their cameras on if you like, since we're just sitting around chatting at this point. Let me just sort of bring up a couple of things that came up in the chats and sort of were left hanging in the previous discussion yesterday. Sort of the two things, I'm open to anything, but the two things as a co-chair I need to be thinking about are computing, and we started a discussion on an ASD experiment yesterday. And then the other, of course, as we were just talking about a half an hour ago, about priorities for how we invest our internal resources within CESM on our next steps. So let me just touch on the computing. We were talking about there is this big opportunity for an ASD, Advanced Scientific Discovery proposal, which will be coming. I'm sort of guessing with the solicitation might come out in early summer. And let me say that, it's not necessarily the case that we would have to have only one proposal from this working group, or that we might not want to team up with other working groups. Chuck Hakaranen, who is no longer on the call, was jumping back and forth between our meeting and the land ice, and apparently the land ice group also was discussing this opportunity and are talking about doing some simulation, some kind of an ensemble simulation involving atmospheric downscaling over Greenland, sort of high resolution Greenland experiments. So there's, maybe some possibility we could combine forces with them on something if there's a fit. And I'll follow up with Bill Lipscomb, the co-chair of the Land Ice Group, to see what they're thinking and can bring that back to this group. I also want to point out that these proposals are not limited to NCAR staff, that university groups can propose. I think with the same restriction as any other NCAR proposal, that there would have to be an NSF PI with a related proposal that could justify the use of the time as an NSF project. So I believe there are some NSF funded PIs under the CPT. So I think that would be a possibility that the CPT could bring forward an ASD proposal. So that's what I know about it. If anyone has some more thoughts on things they would like to discuss publicly at this point, that's certainly a possibility, or, we can certainly follow up by email or a later meeting if needed. Okay, not hearing a whole lot. Then I guess on priorities, we sort of talked a little bit about the wave stuff a minute ago. Let me just also give you a little bit of background on that and say that one thing that is sort of an urgent priority for us is that the atmospheric model working group is in the midst of a die-core shootout. They have 3 different dynamical cores they're considering for CESM3, and they want to begin testing those in a coupled configuration. So it's sort of the highest priority. I'll come back to Gokhan in just, but for the high, I think, and pragmatically, the highest priority for us is to get our MOM6 coupled integrations going and producing a reasonable climate in which to conduct that shootout. So Gokhan, go ahead.
Yeah, well, I just stepped out. We had an SSC meeting exactly on the timelines of this dynamical core and then getting the teams ready. So it looks like Peter and Isla will be leading that effort, and their timeline is that they would like to do the first AMIP type of simulations thoroughly. And according to their timeline, that is going to be completed by roughly October timeframe. So then they are going to start the fully coupled simulation. So there's a little bit more time, essentially.
We had been told they wanted it like right now.
I know, but yeah.
Okay, well, that's a relief.
Yeah.
But nonetheless, we would like to be able to start running coupled simulations sooner than later so that we can test our parameterization suite in a coupled context.
Maybe I shouldn't have said anything. So that's...
So then there were, and as I said earlier, and we talked about earlier, we have a fairly clear path, at least on the early part of bringing the waves in, and that will get us most of the way back to where we were with the POP capability. Bob brought up in the chat yesterday when we were discussing this, and we wrapped up about getting the estuary box model or some representation of river inputs in. That's a personal research interest of mine. I'd really like to work on that as I can find the time. There will be, and this is something I'm still learning more about MOM6 and how to do this. It was a particularly simple implementation in POP because of the virtual salt flux boundary conditions. Translating that into virtual salt fluxes was much easier than putting mass sources in the model. So I need, it will probably require, and maybe this is something maybe we could bring up in the MOM dev calls over the next months about how we would approach it as a mass source problem. But that's definitely something I have an interest in. And there are other, and then, go ahead, Bob.
Frank, on that point, just try it. I think it'll work. Just put in the mass source.
Okay. Subsurface, you think will work? You can inflate a layer, subsurface layer?
You can inflate any layer. The only thing you might need to do if you're inflating a layer in the interior is also make sure the barotropic mode knows about it so that it gets radiated properly and immediately. But my expectation is that if you get it wrong, you'll make some.
We'll know about it pretty quickly, yeah.
And if you don't get it wrong, it'll just work.
All right. And I guess that was more or less what I had. I guess I would like to hear from the CPT folks on, how they envision bridging into the realistic model world and having things that we could be testing over the rest of the period of the CPT.
Yeah, absolutely. I mean, I can jump in if Alistair is here. I don't know if Alistair is still around. Yeah, Alistair, you wanna chime in, then I can follow up.
So we have we've discussed this in the CPT. The emphasis on Never World was somewhat a consequence of the pandemic, as I mentioned when I spoke yesterday. And we have still in our plans that by the end of the first year of work that we will be evaluating these parameterizations in realistic models. And from the GFDL side, that would be the half-degree OM4 configuration, which uses a parameterization, whereas the quarter degree does not. Now, in the proposal, we also said we would be evaluating parameterizations for the intermediate eddy permitting regime, in which that would be the quarter degree. But we've, with the time that we have at this point, I imagine that will be saved for the second year. And I also imagined that the similar exercise would be happening at NCAR with the new CSM configuration at your 2/3 resolution. But we've yet to actually confirm that.
Well, this is the place to bring that up.
Yes, absolutely. So I can basically follow up on that. I guess so. This is part of the discussion we started having. I mean, again, due to all the issues that Alistair mentioned, because of COVID, there were some issues, accessing the computing, and of course, Neerja, who was sitting at GFDL, kind of left off. So there is a little bit of a gap right now. So we've been discussing on how to redistribute, the tasks and how NCAR will, basically kind of participate in some of those efforts. And so this is really happening as we speak. So again, I don't know if Scott is around. I don't want to put words in his mouth, but so on NCAR's side, according to Scott, and I think Gökhan is here, so he can confirm as well. The first step was focus on a subset of the parameterization when it concerns basically tracers and buoyancy. So that would be kind of the first step that NCAR seemed to want to pursue. So a subset of the set of parameterization. And as we do the evaluation in the more idealized cases, then we'll basically refine that subset that will then be tested in the workhorse of NCAR at 2/3 of a degree. So it's a bit of a two-step approach here.
Yeah, I think so. Gustavo, do you want to chime in with the latest plans?
Gustavo is here. Excellent.
Yeah, Gustavo is here.
Well, I'm not sure if I'm on top of the latest plans, but my understanding from our meeting in January is that we would pursue the ready type of evaluation, and then we're going to also help with the running the idealized cases that remain to be run. That's something that Laura and I talked about last week or so.
Correct, yes. And Alistair and I are literally working as we speak on updating that list, because we actually wanted to see this meeting and see new progresses, not just from our CPT, right, where we all know what we're working on, but also the rest of the community, so we could actually update that list. So yeah, so exactly as you said, so that will be finalized in the next few hours.
All right.
I hope that answers your question,
Yeah.
Frank, or if you had any other comments.
No, that's very helpful. All right. Well, thanks again. Does anyone have any other closing thoughts?
Yeah, I'm thinking back to this ASD run. It's not too soon to start planning for what we would do. I know that there is this, you got this idea from Chuck on the other, to join up with another group, but it is advanced scientific discovery. So it really is an opportunity to just do that, advanced scientific discovery in a unique way. And they are going to be relatively competitive. So we really do need something that advances scientific discovery. So it's not too soon to start thinking about it, because by the fall, they're going to have to be shovel ready, actually have run whatever you're going to do, at least in a trial mode. So I just, let's not let that discussion drop too far.
Right.
And if the CPTs might have some ideas, but they don't seem to be quite ready to tell us what we should do for that. But let's keep thinking about it.
Yep. Okay. All right. It seems like it's a wrap. I know it's getting pretty late on the East Coast, and I don't know if Takaya is still on. It's really late in France. Oh, he's dropped off. He went to bed. All right. So thanks a lot, everybody. It's been a fantastic week. I really appreciate it. Hope to see some of you back in June to the annual workshop, and we'll be talking to you. Bye.
Thank you very much.